Okay. All right. Very good evening, all. So in the last class also, I made the announcement regarding the resuming of the offline classes at the Hyderabad, right? And those who have already taken the admission for the offline classes, they can attend or they can continue through the online mode also. But one change is there. You are supposed to send the mail to the head office. Okay, right. Otherwise it will be difficult for you because one after sending the mail, after receiving the mail from you, then only they will switch your batch from offline to the online, right? Okay. So in the last session we discussed about single phase half wave controlled rectifier with the R load, L load, C load. Okay. After that, the RL load with freewheeling diode. Okay. RE load also we discussed. Now we are going to discuss the RLE load, right? And after that, we will discuss the numericals, right? Okay. So RLE load. So let us put the heading single phase half wave controlled rectifier with the RLE load. So single phase half wave controlled rectifier with the RLE load. RLE load, right? So RLE load is nothing but it is like a motor load. Okay, it is like a motor load. So the circuit diagram similar to that of the previous case. The only thing is the load branch will be the RLE now. So, right. So we're having a supply voltage Vs, which is equal to Vm into sine of omega t. Thyristor T, voltage across thyristor is a Vt. Current flowing to thyristor is a IT. Source current is a IS. RL and E here. This voltage is a V0 and current here is a I0, right? So this is the circuit diagram. Next, the waveforms. Vs is equal to Vm into sine of omega t. Already we discussed about the RE load, right? In the last session. This is a Vs. Next, the E. Okay, so this is the E we're having. IG get pulse to SCR. So this is alpha, and here it is a 2 pi plus alpha. V0 and I0. This is the E. This is same as the supply voltage. So this is like your alpha, pi, beta, 2 pi, 2 pi plus alpha, and 3 pi. And the I0 waveform so this is the I0, right? Same alpha, pi, beta, 2 pi, 2 pi plus alpha, and 3 pi, right? So if you compare here RLE load we are having with the RE load, if you compare RLE and RLE load, here we are having an inductor in the load branch. And as we know, the inductor is the element which stores the energy in its magnetic field, and in order to oppose the change in the current, it releases the energy. Are you getting the point? Okay. So that's why here we are having this type of waveforms, right? So now you can check here in the V0, we are having combination of EMF E and the supply voltage, right? If you compare this V0 with a RE load V0, then you will understand in a RE load also from 0 to alpha we had V0 is equal to E, right? But from alpha to pi minus theta, theta is like this one, right? Theta is like this one. This is like a theta, or this is theta actually, and this is like your pi minus theta, pi minus theta. Okay, so in the RE load, if you check from alpha till pi minus theta, okay, we had a V0 is equal to Vs, right? And after that pi minus theta till 2 pi plus alpha, again we had V0 is equal to E only. Okay, but here it is the different. Here it is a different. Why it is different? We are going to discuss. Okay, so yes, single phase half wave control rectifier with a RLE load. RLE load is like your electric motor load. Okay, electric motor load. So here we are having the supply voltage Vs, which is equal to Vm into sine of omega t, right? Next, during 0 to pi, Vs is positive, pi to 2 pi, Vs negative. EMF E, right? E is the EMF, right? That is the EMF in the load, right? So we are having here. Now I have taken the points here as theta. So corresponding to theta here we are having Vs and E both are same. Corresponding to theta we are having Vs and E both are same, right? Next, similarly at pi minus theta also Vs and E both are same. So if you check for omega t is in between 0 to theta, it is like a Vs is less than E. Between theta to pi minus theta, Vs is greater than E. Pi minus theta to pi, Vs is again less than E. And after that we are having Vs is a negative. Okay. So let us discuss here. Suppose initially our thyristor will be in an off state. Initially the thyristor will be in an off state. That is before t is equal to 0. It is like a circuit was at the rest position and our thyristor was in an off state. So if the circuit was at a rest position, so that's why current, yes, current will not be flowing from source towards the load. Okay. So that's why there is a no point like inductor has stored the energy before t is equal to 0. I'm saying, right? Next, after t is equal to 0, yes, what is happening here? Suppose if this point potential is 0 volt, definitely this point or after t is equal to 0, polarity will be plus here, minus here. Okay. So if I consider this as a 0 volt, definitely here potential will be equal to Vs volt. This Vs will appear here. So here it is a Vs volt. Okay. This 0 means here it is 0 volt. Therefore, here potential is a E volt. That is a plus E volt. Right? If it is E volt, as I said, initially it is like a thyristor is in an off state. So current in the circuit will be 0. So if the current in the circuit is 0, it is like a voltage across inductor, voltage across resistor will be 0. Right? So if this is E volt, definitely here we'll be getting a E volt and here it is a E volt. Okay. So now, yes, we can check here. Initially, okay, that is between 0 to theta. If you check, yes, voltage at the anode of thyristor is Vs, voltage at the cathode of thyristor is E volt. So between 0 to theta, Vs is less than E. So between 0 to theta, can we say that anode voltage of a thyristor is less than that of the cathode voltage? So our thyristor will be in a reverse bias mode only. Yes or no, right? So let me write between or for omega t is equal to 0 to theta. It is like a Vs is less than E. Okay. So if Vs is less than E, thyristor will be in a reverse bias mode. Reverse bias mode. Okay. So if thyristor is in a reverse bias mode, thyristor is in a reverse bias mode, and if we apply the gate signal, whether our thyristor will turn on? No, thyristor will not turn on at all, right? So that's why here we have applied the gate signal only after omega t is equal to theta, because this is like a point theta we are having, and this is alpha. We have selected alpha, okay, that is greater than theta. That is greater than theta. Okay. So now here, so between 0 to theta, thyristor is in reverse bias mode. So can we draw the equivalent circuit between 0 to theta? Yes, we can. Thyristor will be like an open circuit. Okay. So we can draw the circuit. Thyristor is in a open circuit. This is a R, L, and here it is a E, right? This is a Vs plus minus. This voltage is a Vt. Current is a It. Here it is a Is, right? R, L, and E. This voltage is a V0 and current is a I0, right? So thyristor is in a reverse bias mode, means it is in a reverse bias. We are having only one mode of operation, that is a reverse blocking mode. So thyristor will be acting as an open circuit here. Okay, that is a blocking mode, off state. So that's why current will not flow. So can we write here I0 is equal to 0 ampere. Okay, I0 is a 0 ampere. Also your thyristor current It and Is are also 0. Okay, so It is equal to Is is equal to I0. All will be 0 ampere only, right? Next, now if I0 is 0, what about the V0? V0 is equal to E, na, right? Because current is 0, but here we are in the EMF. You can apply KVL to this loop. You will understand. Plus V0 minus I0 are minus L into di0 by dt minus E is equal to 0. Okay. So from this we can write V0 is equal to E volt. Are you getting the point? V0 is equal to E volt. So I0 0, V0 is E, right? Next, what about the Vt here? Can we apply KVL to loop? Yes, KVL to loop. KVL to loop. So it is like a plus Vs minus Vt minus V0 is equal to 0, right? So therefore Vt is equal to Vs minus V0. But what is V0? V0 is equal to E. So can we write it as Vs minus E? So therefore Vt is equal to Vs minus E, right? So voltage across thyristor is a difference between supply voltage and a EMF value. Okay, supply voltage and a EMF value. We have not drawn the waveform of Vt. We'll draw it at the end. Okay, so Vt is equal to Vs minus E. Now, so you can check the waveforms here. Between 0 to alpha, V0 is equal to E, I0 is equal to 0, right? V0 is E and I0 is 0, right? Now, next. So it is like for omega t is 0 to, sorry, omega t is 0 to theta, not alpha. We have discussed only till theta. Only till theta. Okay. Next, from theta to alpha, what will happen? Let us discuss. So you can check after theta, it is Vs is greater than E. Okay. And alpha point means you can check. This is the alpha point we are having. Okay. So it indicates your point alpha, right? So between theta to alpha, Vs is greater than E. But we have not applied the gate signal to the thyristor. So our thyristor will be in a forward blocking mode. So forward blocking mode means again it is like a off switch only, right? So between theta to alpha, right? Between omega t is equal to theta to alpha. So for omega t is equal to theta to alpha. Theta to alpha, right? So if you check between theta to alpha, yes, thyristor will be in a forward blocking mode. Forward blocking mode. So equivalently, we can draw the circuit, right? Equivalent, we can draw the circuit as thyristor is in a off state, supply voltage R, L, and E. So this is a Vs, this is a Vt, It, Is, right? R, L, E, and this is a V0, and here it is a I0, right? So during this mode, yes, what is the I0? Again, I0 is 0. Okay, so we can write Is is equal to It is equal to I0 is equal to 0. Okay, Is, It, I0 is equal to 0. Next, now you can check V0 is equal to E, right? Current is 0 here, but voltage is equal to E. So V0 is equal to E. Next, we can write Vt again. Vt is equal to Vs minus E. Vs minus E. You can apply KVL and you can check. Vt will be getting it as a Vs minus E. Same as that of the previous case. Okay. So V0 is again E. I0 is 0 only. So you can check here. V0, 0 between theta to alpha. V0 is E. I0 is 0. Right. After alpha, what will happen? Let us discuss. At alpha, we are going to apply the gate signal to the thyristor. So as our thyristor is in a forward bias mode, as soon as we apply the gate signal, our thyristor will turn on immediately. Okay. So once thyristor turns on, what will happen? Our inductor go on storing the energy, because when thyristor turns on, current will flow from Vs, thyristor, load, and again back to the Vs. In this loop, the current will flow. So when the current starts flowing, it is like your inductor go on storing the energy. Okay. So till which instant the inductor will store the energy? Yes, you can check till which instant the inductor will store the energy. The inductor will store the energy till the instant just before the pi minus theta. Here we are having a pi minus theta. Okay, so just before pi minus theta means somewhat here. Till this instant inductor go on storing the energy. Okay, very close. This instant is very close to the pi minus theta. Why I am saying this instant is just before the pi minus theta? Let us discuss. Because we know inductor, when the inductor stores energy, right, that is when VL is a positive. Okay, so now you can check when this thyristor is in a on state. When this thyristor is in a on state, okay, we're having current flowing in this loop, right? So if you apply KVL to this loop, it is like a plus Vs minus VR minus VL minus E is equal to 0 now. So what is VL? VL is equal to Vs minus VR minus E. VL means voltage across inductor. I am saying it is like a difference of Vs minus VR minus E. Okay, so you can check here. After alpha, Vs is high value, E is this much value. Okay, and VR is very less now. VR is like your, yes, similar to that of your I0, because VR means what? I0 into R na, I0 into R. Okay, so let me write here for omega t is equal to alpha till this instant. Let me write this instant as a theta 1. Okay, alpha to theta 1. Okay, let me indicate here only. This is a theta 1. Okay, so it is like this instant we are having. Corresponding to this instant, it is a theta 1. Okay, so from omega t is equal to alpha to theta 1, for omega t is equal to alpha to theta 1. Yes, we have applied the gate pulse now. Okay, so thyristor will be in a on state. That is a forward conduction mode. Thyristor will be in a forward conduction mode. Okay, so when thyristor is in a forward conduction mode, equivalently we can draw the circuit. It is like thyristor is in a on state. Supply voltage Vs is positive or negative? It is a positive only, right? And this is a EMF E. So this is a Vs, right? This is a Vt, It, Is, RL, and E, right? This is a V0. Let me indicate here VR, VL as well. Okay, so now you can check here between omega t is alpha to theta 1. Okay, theta 1 is just before the pi minus theta 1. I am saying theta 1 is just before. This is theta 1 is just before the pi minus theta, just before pi minus theta. Okay, so now here, yes, in this circuit, if you check, Vt is 0. Vt is equal to 0 volt. Voltage across thyristor is 0. Next, if we current is flowing into the circuit, okay, if we apply the KVL, yes, it is like a plus Vs minus yes, plus Vs minus Vt minus V0 is equal to 0. Again, Vt is 0 now, right? Because thyristor is acting as a short circuit. So therefore, V0 is the same as that of the supply voltage. V0 is the same as that of the supply voltage. Now, how to write the VL expression? How to write the VL expression? You can check. Simply either you can apply KVL to this part or you can apply KVL to this part. Okay, right? In both the ways, you will be getting the same answer. Suppose I am applying the KVL to this part, KVL to this part. It is like a plus V0 minus VR minus VL minus E is equal to 0. So therefore, from this VL is equal to V0 minus VR minus E. This is your VL. This is the VL we are having. Okay. Now you can check here. VL is nothing but V0 is nothing but again Vs. So can we write it as Vs minus VR minus E? So if you check the waveform here, yes, Vs is this waveform. Okay. So Vs is greater than that of the E na, right? So Vs minus E nothing but this difference. And you can check the voltage across resistor also. Voltage across resistor is very small here. Voltage across resistor is very small. So that's why here you can check. Actually, in a RLE load, the thing is in a RLE load, the resistance of the motor or the motor winding resistance is very small. Okay, you can check the DC motor. Okay, armature resistance is generally very small, na? Right? So that's why in RLE load, the value of the voltage across resistor is generally very, very small. Okay, in most of the cases, generally they neglect it. But if we consider it as a non-zero, then our theta 1 is nearly equal to pi minus theta. If we neglect it, okay, then it is like our that theta 1 will be equal to pi minus theta. If we neglect the VR, I am saying, then theta 1 will be equal to your pi minus theta 1. Okay, so here the thing is VL is a positive. So VL is a positive. So if VL is positive, it is like inductor is storing the energy. Okay, so therefore inductor L stores energy. So here you can check the waveform. Vt0, V0, Vs, I0 is increasing slowly na, because inductor is storing the energy. Okay, so inductor is storing the energy. So here I0 is increasing slowly. This is not the sinusoidal waveform. Please be careful. This is increasing slowly. I0 is increasing slowly. And V0 is equal to Vs. V0 is equal to Vs. Okay. Next, after theta 1, what will happen? After theta 1, you can check from theta 1 to pi. Okay, from theta 1 to pi. It is like you are now, VL will be negative. After theta 1, what will happen? VL is negative, because after theta 1, you can check here, Vs is now, yes, after peak point, Vs is still decreasing only, na? Okay, but we are having the point theta 1, till that instant, it is like a VL was positive. Okay, now after this instant, it is like a VL will be negative. VL will be negative, means what? Our inductor will oppose the change in the current. You can check here at theta 1, what is the value of the current in the circuit? The current in the circuit value is a high value. It is a positive value. Means the current flowing through the inductor will be in a downward direction only, right? And after theta 1, what will happen? Yes, if your Vs minus VR minus E, if Vs minus VR minus E is negative, the meaning is this inductor will starts releasing the energy in order to oppose the sudden change in the current. You can check. Suppose if our Vs is, if the Vs becomes less than E and VR, if the Vs becomes less than E plus VR, then what will happen? It is like a resultant current should flow in the anti-clockwise direction. But whether our inductor will allow, and definitely this thyristor will not allow the reverse current. Okay, so ideally speaking, or in general way, suppose if this inductor is not opposing the change in the current, so it is like our current will suddenly falls to zero value. But whether our inductor will allow the current to become zero suddenly from this non-zero value to the zero value? No. So that's why our inductor will go on releasing the energy. After theta 1 only, our inductor will go on releasing the energy. And when inductor releases the energy from theta 1 to pi, I'm saying from omega t is equal to theta 1 to pi, when inductor releases the energy, yes, inductor energy and supply energy both will be adding. Are you getting the point? Okay, right? So now here let me write for omega t is equal to theta 1 to pi. For omega t is equal to theta 1 to pi. Yes, inductor releases energy. The inductor releases energy. So when inductor releases the energy, again thyristor will be in a conduction mode. Right? Vs. Right? Okay. Voltage across thyristor, Vt. Current flowing through thyristor, It. Here it is Is, R, L, and E. This voltage is a V0, and here it is a I0. Okay. So inductor is releasing the energy, right, through the thyristor. So our thyristor will be in a conduction mode only. And here Vs and yes, inductor, okay, both will be adding, okay, both will be adding, or energies of these two will be getting added. Okay, so that's why our thyristor will be in a forward bias mode only. Thyristor will be in a forward bias mode only. Means it is like when Vs is less than that of Vr plus E na, at that time our inductor is coming forward here to help the Vs, right? Because inductor has already stored the energy na, and in order to oppose the sudden change in the current, yes, our inductor is, yes, is helping the Vs here. Okay, so now if you check in this loop, Vt is again 0. Vt is equal to 0 volt. Next, what about the V0? You can apply KVL. You will be getting V0 is equal to Vs only. V0 is equal to Vs only, right? Next, so V0 is Vs, Vt is 0 volt. I0 decreasing because inductor is releasing the energy. I0 decreases. I0 decreases. Okay, so you can check here. From theta 1 till pi, I0 is decreasing. V0 is the same as that of the supply voltage. V0 is same as that of the supply voltage. Okay, Vt is a 0 volt. After pi, what will happen? After pi, you can check at pi, at omega t is equal to pi. Current flowing through the circuit is like a positive only, na? At omega t is equal to pi, current flowing through the circuit is positive. The meaning is current flowing through the inductor is again in the downward direction only. It has not yet reached the 0 value. So after pi, when the supply voltage becomes negative, na? So it is like supply voltage polarity will be minus here and plus here. So you can check here supply voltage and E will be adding now, na? Supply voltage and E will be adding now. Now the thing is what will happen, but whether our inductor will allow the sudden current to fall from non-zero value to the 0 value? No. So again, our inductor will continue releasing the energy in opposite of the supply voltage and the E. I am saying inductor is now releasing the energy in opposition to that of the supply voltage and the EMF E. You can check near to the pi, what is the value of supply voltage? It is a very small. Now you can check near to the pi, the value of supply voltage is very small. So here Vs is very small. So your Vs plus E, that value is nearly equal to E only, right? Vs plus E value will be nearly equal to E only. Okay, so that's why our inductor will successfully release the energy. Okay, yes, through thyristor T, and in opposition to that of the EMF E and the supply voltage, in opposition to that of the EMF and the supply voltage. So let me draw the circuit from pi to beta. For omega t is equal to pi to beta. Yes, for omega t is equal to pi to beta. Yes, inductor releases energy. But now inductor is releasing the energy in opposition to that of the supply voltage. So equivalent circuit will be like this. Minus plus, right? This is a Vs because supply voltage is negative na after pi. This is thyristor T. Here we are having a Vt, It, Is, R, L, and E. This is a V0 and here it is a I0, right? So inductor is releasing the energy in opposition to that of the supply voltage as well as EMF E, Okay, now, so when inductor releases energy, again thyristor will be in a conduction mode. So thyristor T is in a conduction mode. means I'm saying thyristor T is in a forward conduction mode only. Okay, conduction mode. So Vt is 0 volt. Vt is a 0 volt. Yes, V0 is equal to Vs, same measure of the supply voltage. Okay, or let me write it as minus Vs, if because we reverse the terminal, right? So minus Vs minus V0 is equal to 0. So V0 is equal to minus Vs. The meaning is V0 is a negative. Supply voltage also negative, right? V0 is also negative, right? So we'll be getting in the V0 the negative pulse. We'll be getting the negative pulse. Same as that of your REL load. Same as that of your REL load. Okay. Next, what about the I0? I0 is a decreasing. Inductor is releasing the energy, na? So I0 is a decreasing, and this will continue till beta only. After beta, what is happening in the circuit? You can check. This will continue till beta only. At beta, it is like inductor energy is less than that of supply energy and EMF energy. Are you getting the point? At beta, it is like inductor energy is less than that of supply energy and EMF energy. So that's why the resultant energy, yes, or the resultant current in the circuit will be in the anti-clockwise direction. But our thyristor will not allow the reverse current now. So that's why current will become 0. Right? Means after beta, you can check our circuit will be at like a rest position. From pi to beta, supply voltage is negative. I0 is decreasing. From beta till 2 pi, what will happen? From beta till 2 pi, it is like a circuit will be at a rest position. Okay, means thyristor is in an off state. Supply voltage will be reverse polarity, na? Okay, so from beta till 2 pi, from omega t is equal to beta till 2 pi. Yes, for omega t is equal to beta to 2 pi, from beta to 2 pi. Yes, if you check the circuit, it will be like this. Thyristor will be in an off state now. Thyristor will be in a reverse blocking mode. Vs minus plus. This is a Vt, R, L, and E. Right? Here it is a V0, and we're having a I0. This current is a IT. This current is a IS. Yes, you can check in this loop. What is V0? V0 is equal to E only, na? Right? Because current is 0. Current in the circuit is 0. So I0, IT, IS, all will be 0 ampere. V0 is equal to E volt. V0 is equal to E volt. Okay. Next, thyristor will be in a off state. That is the reverse blocking mode. Thyristor will be in a reverse blocking mode, I am saying. Okay. So you can check V0 and I0 values, or either we can, next we can apply the KVL to the loop. We'll be getting minus Vs minus Vt minus V0 is equal to 0 now. So therefore Vt is equal to minus Vs minus V0, which is equal to minus Vs minus E. The meaning is voltage across thyristor will be more negative. That is it is like a reverse voltage only. It is like an addition of supply voltage and a EMF. Supply voltage and EMF, right? So this type of will be getting. Okay. So whatever we discussed in the RE load also, we had the expression for Vt during that pi, from pi till 2 pi, right? Sorry, from omega t is equal to pi minus theta till 2 pi plus theta. We had this type of expression. Okay, minus Vs minus C. You can check, right? So now, so this is the circuit operation. So for that, you can check from beta to 2 pi, V0 is E, I0 is 0. So beta to 2 pi, V0 is equal to E and I0 is equal to 0. After 2 pi, again the same cycle will repeat. Again the same cycle will repeat, right? Okay. Yeah, Ramakrishna, all your doubts will be answered at the end of the session, okay? Yes, after this circuit, we will be discussing 2 more numericals, okay? And after that, we will be starting the full wave rectifiers, right? Okay. So, is this clear? So let me summarize this operation once again. If you check a thyristor between omega t is equal to 0 to theta, thyristor will be in a reverse blocking mode, theta to alpha, forward blocking mode, alpha till theta 1. Okay, from alpha till theta 1, it is like a forward conduction mode, theta 1 to pi forward conduction mode, pi to beta forward conduction mode only. Okay, here, yes, here you can check due to the inductor after theta 1 also, we are getting the voltage across the load is the same as that of the supply voltage. But if you remove this L, it is like we'll be getting the RE load. You can compare the V0 waveform in RE load and V0 waveform here, right? You will understand the difference. So due to the presence of inductor, what is happening? Actually, the inductor is the element which is having a tendency that it stores the energy and also it releases the energy. Why the inductor is releasing the energy? In order to maintain the same current through the load, same current through it actually, not load, because inductor is connected in a load. That's why our load current is having this type of nature, right? So inductor opposes the change in the current, right? Opposes the change in the current, right? Next. So now we are going to derive the expressions, right? Expressions. V0 average. So V0 average value of output voltage. So either we can find the V0 average by by using the waveform of V0. Okay, right? Sorry, by using the waveform V0 only we need to find it because we don't know the expression for this I0, right? Okay, so we're going to write the expression of I0 also. So V0 average, whatever the waveform we're having from omega t is equal to 0 to 2 pi, the same will repeat from 2 pi to 4 pi now, right? Whatever the waveform of V0 we're having from 0 to 2 pi, same will repeat from 2 pi to 4 pi. You can check between 0 to alpha it is a E, and from 2 pi to 2 pi plus alpha also will be getting E only. And next it is the same as the supply voltage, here also same as the supply voltage. So this waveform is a continuous waveform. This is a continuous waveform. Okay, right? So V0 average, let me write V0 average is equal to 1 by 2 pi. Okay, 1 by 2 pi. So during a 2 pi interval, we are having the 3 sub intervals, 0 to alpha, alpha to beta, and beta to 2 pi. Na? Between 0 to alpha, what is V0? It is a E. Alpha to beta, it is a Vs, and beta to 2 pi, it is again E. Okay, so let me write it as, yes, integration from 0 to alpha, it is a E into d omega t, plus integration from alpha to beta. What is the value of V0 during alpha to beta? It is a Vm sin omega t. Vm into sin of omega t into d omega t, plus integration from beta to 2 pi. Again, it is a E, na? E into d omega t, right? So you can write it as is equal to 1 by 2 pi into E into integration of d omega t. E is a constant, na? So we can write omega t. After putting the limits, we'll be getting E into alpha minus 0. So that is the E into alpha. Plus Vm into integration of sine is minus cos of omega t. Okay, so let me write it as minus cos of omega t here, and limit will be alpha to beta, plus E into it is like a 2 pi minus beta, right? Further we can put the limits here. Okay, so therefore V0 average is equal to 1 by 2 pi into E into alpha, right? Next, plus Vm into cos alpha minus cos beta. Okay, plus Vm into cos alpha minus cos beta, plus E into 2 pi minus beta, plus E into 2 pi minus beta. Okay, this is the one. Or further we can write 1 by 2 pi into E into, here it is E into this term, here also E into the angle we are having. So we can write it as 2 pi minus beta plus alpha, or it is a 2 pi plus alpha minus beta. Okay, plus Vm into cos alpha minus cos beta. This is your V0 average. No need to memorize this expression, right? Is this clear? So this is the V0 average we are having, right? Next, now important thing here, you can check here we are having angle alpha and angle beta, but before the angles we are having a trigonometric terms, na? But whereas you can check here, we are having directly angles 2 pi plus alpha minus beta. Okay, so always keep it in mind while performing the arithmetic operation on the angles. Okay, just like arithmetic means addition, subtraction, etc. Okay, so while performing the arithmetic additions, arithmetic operations on the angles alone, okay, then we need to keep the angles in a radian. We need to keep the angles in a radian. But whereas if the trigonometric term is there before the angle, then it depends on which mode is there in your calculator. Suppose in your calculator, if the degree mode is there in your calculator, if the degree mode is there, then you can put here, suppose alpha is 30 degree, then you can put cos of 30 degree. But suppose in your calculator, if the mode is radian, then we need to put that cos of pi by 6 here. Okay, suppose if the mode is radian and if you put cos of 30 degree, you will not get the correct answer, right? So keep it in mind always, right? So while discussing the numericals, so we'll discuss it again, how to simplify, right? So here we're having the direct addition and the subtraction of the angle, but here we're having the before angle, we're having the trigonometric term, right? Trigonometric means sine, cos, tan, cot, sec, and cosec, right? So this is the V0 average. Okay, next I0 average. I0 average. So you can check here in a V0, we're having resistor, inductor, and EMF. Na? Okay, so can I write V0 is equal to VR plus VL plus E? Out of that, what is the average voltage across inductor? It is a 0. We have discussed this term, right? Because inductor stores energy, at that time it is like a voltage is positive. When inductor releases energy, at that time it is like a voltage is negative. So average voltage is always 0, right? So therefore, we can write V0 is equal to VR plus E, or V0 average is equal to VR average plus E only, because average of E is E only, na? Right? So that's why we can write it as, therefore VR average is nothing but I0 average into R. I0 average into R, which is equal to V0 average minus E. So therefore I0 average is equal to V0 average minus E divided by R. I0 average is equal to V0 average minus E by R. Always keep it in mind. This expression is very important. This is valid for RLE load. This is valid for RLE load, right? But whereas for RL load also we discussed this type of expression. For RL load, it was like a I0 average is equal to V0 average by R only. Okay. And for RLE load, here we'll be having the E. E will be getting added in this case. Okay. So V0 average minus E by R, right? So this is the I0 average. Next, similarly, we can write the expression for V0 RMS. Okay. V0 RMS. RMS value of output voltage. Yes, it is equal to 1 by 2 pi. Yes. Integration from 0 to alpha. Okay. Yes. Integration from 0 to alpha. What is the value of V0? It is a E, na? So it is a E square into d omega t, plus integration from alpha to beta. It is a Vm square into sine square of omega t into d omega t, plus integration from beta to 2 pi. During beta to 2 pi, it is again E, na? So it is a E square into d omega t to the power 1 by 2, square root of mean of squared value. Okay, no need to simplify it, keep it as it is. Okay, so next, so this is a V0 RMS. Now, what is the conduction time of thyristor? Conduction time of thyristor, yes, is equal to, thyristor will be in a conduction mode from alpha till beta, na? So it is a beta minus alpha by omega. Yes or no? Beta minus alpha divided by omega, right? Next, what is the PIV rating of thyristor? PIV rating of thyristor So for that, we need to draw the waveform of Vt. Okay, so let us draw the waveform of Vt first, and then we'll discuss what is the PIV rating. Okay, so let me draw here waveform of Vt. This is omega t 0, right? So 0 to, we're having a theta, next theta to alpha, alpha to pi, and pi to beta, from beta to 2 pi we're having. Okay, so beta to 2 pi. So yes, you can check from 0 to theta and from theta to alpha. What is the Vt we have written? Vt is equal to Vs minus E only, na? From 0 to theta, Vt is equal to Vs minus E. And from theta to alpha also, Vt is equal to Vs minus E. But in that Vs minus E, if you check, between 0 to theta, Vs is less than E, na? So your Vs minus E will be negative. Okay, Vs minus E will be negative. So we'll be having the waveform like this. Okay, it will start from minus E. It will start from minus E, because from 0 to theta, Vt is equal to Vs minus E, and at omega t is equal to 0. What is the Vs? Vs is 0, na? So it is like 0 minus E. So that's why it is a minus E. After that, as omega t increases, your Vs increases. So Vs minus E difference decreases. So that's why it is decreasing. At omega t is equal to theta, Vs and E both will be same, na? Vs and E both will be same. So Vs minus E will become 0. After theta till alpha, Vs is greater than E. You can check the waveform. After theta till alpha, Vs is greater than E. This is a Vs, na? And this is E. So Vs is greater than E. Okay, so Vs is greater than E. So that's why here Vs minus E will be positive. This will continue till alpha. Okay, this will continue till alpha. So it will be like a Vs minus E, right? And this will continue till alpha, right? So this is a Vs minus E. Vs minus E, right? From alpha till beta, what is Vt? Vt should be 0, na? Because thyristor is in a conduction mode. So from alpha till beta, Vt is equal to 0, right? At omega t is equal to beta, at omega t is equal to beta, you can check. At beta means this instant. So corresponding to beta, we'll be having this point. This is beta, means here it is a beta. After beta till 2 pi, you can check. Vt is equal to this negative value minus this, na? Because supply voltage is reversed now. So Vt will be like this value, that is the negative value, and again this value will be getting added. Okay, so you can check corresponding to beta. The value of supply voltage is like Vs into sine beta. Beta is your greater than 180, na? So Vs into sine beta. Sine beta will be for angle greater than 180 degree. Sine beta will be negative value. So here we are having a negative value. In this value, this E will be getting added. So more negative voltage will be getting. Okay, so it is like a Vm sine beta plus E. That will be the negative voltage will be getting. Okay, so this will continue till 2 pi. This will continue till 2 pi. At 2 pi, it is again Vs is 0. So that's why the resultant will be your minus E. So let me show you. Yes, the waveform will be like this. At this instant, it will be Vm sine beta minus E. This is already minus E. Into that, this Vm sine beta will be getting added, getting added. Okay, and this will continue till, yes, 2 pi. At 2 pi, Vs is 0. So we'll be having the waveform like this. Again, this difference will become minus E. And after 2 pi, you can check whatever the waveform from 0 to alpha we're having, na? Same waveform will repeat from 2 pi till 2 pi plus alpha. Okay, so we'll be having this type of waveform. And again, it is like this. So we can say that this is like your, this point is like a 2 pi plus alpha, and this point is like a 2 pi plus theta. So what is the peak value? Peak value is your Vm plus E, right? This is your minus of Vm plus E actually. So peak inverse voltage is Vm plus E here. Okay, Vm plus E. Vm means peak value of the supply voltage, and into that EMF is getting added, right? EMF is getting added. Okay, so therefore let me write it as, it is a Vm plus E. Vm plus E, right? So Vm plus E. Next, what is the circuit turn of time for thyristor? Tc for thyristor. Tc for thyristor. Yes, can anyone? Yesterday we discussed how to find the Tc. Yes, Tc for thyristor. Come on. At which instant current flow through thyristor becomes zero? At omega t is equal to beta, current flow through thyristor becomes zero. After that, the reverse voltage is maintained till which instant? The reverse voltage across thyristor is maintained from beta till 2 pi plus theta. Na? Are you getting the point? Okay. So that's why it is 2 pi plus theta minus beta divided by omega. This indicates your Tc. This indicates your, this is actually angle. So let me write it as omega Tc. This term divided by omega is nothing but your Tc, right? So 2 pi plus theta minus beta. It is not a 2 pi minus beta. Please be careful. It is a 2 pi plus theta minus beta, right? For RE load and RLE load. Okay. So you need to be, yes, please check this circuit, this VT waveform specifically. Okay. So 2 pi plus theta minus beta. So let me write this 2 pi plus theta minus beta divided by omega. Now, how to find theta? How to find theta? Yesterday we discussed how to find this theta value. At omega t is equal to theta, Vs and E both will be same, na? Right? So can I write at omega t is equal to theta, Vm sin theta is equal to E, right? So now how to find theta? Let us check. Let me write here. At omega t is equal to theta, yes, Vs is equal to E. But at omega t is equal to theta, what is Vs? Vs is Vm sin theta. Vm into sine of theta is equal to E. So therefore theta is equal to sine inverse of E upon V max, right? Sine inverse of E by V max. Is this clear? So this is the theta. This is the theta, right? Next, now my question is, yeah, at the instant of triggering, my question is, at the instant of triggering, what is the voltage across thyristor? At the instant of triggering, what is the voltage across thyristor? Come on. Means when we apply the gate signal, triggering means when we apply the gate signal, at that instant, what is the voltage across thyristor? At that instant, I am saying. At the instant of triggering, yes, it is not a zero, okay? Once it turns on, then we can say it is a zero. But at the instant of triggering, yes, it is a Vs minus E. But what is a Vs? At instant of triggering, what is Vs? Yes, Ajita, you have, yes, correct answer you have given. It is a Vm sin alpha minus E. Vm sin alpha minus E. Let me write here. Yes, voltage across thyristor at the instant of triggering. Yes. Voltage across thyristor at instant of triggering. Instant of triggering. Okay, so instant of triggering means that is at omega t is equal to alpha. That is at omega t is equal to alpha. So now you can check from this waveform. Yes, at omega t is equal to alpha. What is the voltage across thyristor? This is a Vt, na? So what it indicates? Vs minus E. But what is the value of Vs at alpha? It is a Vm sin alpha. So that's why the at the instant of triggering, the voltage across thyristor is a Vm sin alpha minus E, right? Vm sin alpha minus E. So therefore, let me write Vt is equal to Vs minus E, which is equal to Vm into sine of alpha minus E. They have asked this question, okay? They will give you the circuit like, or they will directly, yes, state as single phase half wave control rectifier with RLE load. They will give the values of RLE supply voltage, etc. and the triggering instant also. And they ask the question, at the instant of triggering, what is the voltage across thyristor? Okay, so it is a Vm sin alpha minus E, right? Next, at the instant of turning off or at the instant of commutation, what is the voltage across thyristor? At the instant of commutation, what is the voltage across thyristor? Come on. So at the instant of commutation means what? At the instant of turning off. So at which instant thyristor is turning off? That is at omega t is beta. Yes or no? So at beta, what is the voltage across thyristor? This much voltage. What is the value of this voltage? Yes, can anyone? This is a Vm sin beta plus E na? Yes or no? This voltage is Vm sin beta minus E. Sorry, Vm sin beta minus E. You can put, if you put Vm sin beta, you will be getting negative value. And into that, E will be, yes, getting added as a reverse voltage. As a reverse voltage, right? So Vm sin beta minus E. Let me write it as voltage across thyristor at instant of turn off or commutation, you can write. That is at omega t is equal to beta. So at omega t is equal to beta, what is Vt? It is a Vm into sin beta minus E. You can check, it is not like a Vm sin beta minus E means it will be like a Vm sin beta and from that E will be getting subtracted. It is not like a difference between two. No, Vm sin beta, your beta is greater than 180 degrees. So Vm sin beta will be negative. This negative value minus E. So total voltage will be greater than your Vm sin beta. Are you getting the point? Okay. So it is a Vm sin beta minus E. Okay. Next, other expressions we already derived. Okay. So now let us discuss the numerical, right? Yeah. Yes. In the given circuit, a thyristorized converter is feeding a purely resistive load, that is a R. The power consumed by the R in the absence of SCR is P, capital P. In the presence of SCR, the power consumed by the capital R at alpha equal to 90 degree would be reduced by a factor of. Okay, means we are in the two cases. One is in the absence of SCR and second one is in the presence of SCR. In the absence of SCR, they have given the power consumed by the resistor is a capital P, and our task is to find in the presence of SCR and at alpha equal to 90 degree. Okay, what will be the power or how this power would be reduced by how much factor, that we need to find. Okay, so yes, this circuit we already analyzed. It is a single phase half wave controlled rectifier with purely resistive load. Okay, so now yes, let us discuss. In the absence of SCR means whether it will be open circuit or short circuit. In the absence of SCR means we are supposed to remove this SCR, and after removing the SCR, whether we need to put a short circuit there or we need to put an open circuit. We need to put a short circuit, not an open circuit. If you keep it as an open circuit, suppose if I remove the thyristor and if I keep that as an open circuit, so whether the current will flow from source towards the load? No. Then what is the meaning of this capital P? That capital P will be your zero now. Yes or no? Right? So keep it in mind. Try to understand the question first. They have given the power consumed by the resistor R in the absence of SCR is P. In the absence of SCR means we need to remove that SCR with a short circuit. Okay. So it is like the SCR is not there. I have directly connected the sinusoidal supply across the resistor R. Okay, I have connected the sinusoidal supply across the resistor R. So this kind of scenario will be there. Okay, so let me draw the circuit. In absence of SCR, so we'll be having circuit like this. So across the sinusoidal supply, a resistor is directly connected. Okay. If you remove it, if you keep it as an open circuit, then our power will be zero. Na power consumed by the resistor will be zero. Means we are having the single phase supply, and here it is resistor, but I have not connected these two elements. Then whether the current will flow through the resistor? No. So your power will be zero. The meaning is your capital P will be zero in this case. You will not get the answer for this question next. Okay. So that's why in the absence of SR means we need to connect a directly short circuit here. Next, this voltage is Vs, resistor R. Okay. So now what will be the expression for power consumed by the resistor in this case? It is a simple AC circuit, na? Single phase AC supply, and across it is connected across a purely resistance R, capital R. So what is the capital P here? Power consumed by the resistor in this case. It is a RMS voltage across the resistor. It's a square divided by R, na? Yes or no? Right? So because, or let me write it as a V0. Let me write it as a V0. If this is the sinusoidal supply, definitely the V0 will be your sinusoidal only, na? Right? So therefore now power consumed by resistor R. Okay. This is in the absence of SR we are discussing. Okay. Which is equal to what? V0 RMS square divided by R, na? But what is the V0 RMS now? V0 RMS will be same as of your Vs RMS, na? Yes or no? Right? So V0 RMS is same as of the Vs RMS. So therefore, but what is this power they have indicated? They have indicated this power with capital P. So let me write it as capital P is equal to V0 RMS is nothing but Vs RMS square divided by R, which is equal to Vs RMS is again, you can check Vs they have given. Let me write here, Vs is equal to √2 into V into sine of omega t. This value they have given, this expression they have given. So now, what is the peak value here? Peak value is √2 into V, na? So what is the RMS value for any sinusoidal supply? What is the relation between RMS value and peak value? Yes, RMS value is equal to peak by √2, na? So peak value is √2 into V. So RMS will be √2 into V by √2, na? √2 into V divided by √2. Yes or no? Right? So let me write it as, yes. Let me write it as P is equal to, so therefore P is equal to V0 RMS, now we are having, sorry, Vs RMS. Vs RMS is equal to √2 into V divided by √2. Let me write it as like this, or let me write it as Vm by √2. Okay. Square divided by R. Right? So I have replaced Vs RMS with the Vm by √2. Again, what is Vm? Vm is like √2 into V. Okay. So it is equal to √2 into V divided by again √2 as it is to the power or square divided by R. So √2 will get cancelled out. So it is equal to V square by R. So this is capital P, which is equal to V square by R. This is in the absence of SCR, right? How much power the resistor is consuming, which is equal to V square by R. Now let us discuss in the presence of SCR what is happening in the circuit. In the presence of SCR, in presence of SCR. So in presence of SCR means SCR will be connected in the circuit now. This is a Vs, thyristor T, R. Okay, suppose this is a V0 we are having, and this is a I0. They have given in the presence of SCR if alpha equal to 90 degree. Okay. So in the presence of SCR, if alpha equal to 90 degree, yes, how is the V0 waveform? From 0 to alpha, it is like a thyristor will be in a forward blocking mode. Yes or no? Right? So V0 is 0, I0 is 0. Right? Next, after alpha, that is at omega t is equal to, at alpha, we are applying the gate signal to the thyristor. Our thyristor will turn on. Once thyristor turns on, yes, current will be flowing here. So that's why V0 will be equal to Vs. So for omega t, for alpha equal to 90 degree, how will be the V0 waveform? If we recall, the V0 waveform is like this. Omega t, right? This is like alpha, pi, 2 pi, and so on. Okay, so how is the waveform? Waveform will be 0 to alpha, it is a 0. because get pulse we have not applied. Okay, from alpha till pi. Okay, it will be like this. From alpha to pi, it will be like this. Same method of supply voltage, na? Right? And from pi to 2 pi again 0 because reverse voltage, right? Thyristor will not allow the reverse current. So that's why it is a 0. And again after 2 pi, the same cycle repeats. What is this value? This is same method of the supply voltage here. So now for this, can we write the expression of V0 RMS? Because our task is to find the power consumed by the resistor, na? Okay. So can we find, yes, V0 RMS here? Yes, V0 RMS. V0 RMS. Square root of mean of squared value, right? So it is a 1 by 2 pi integration from alpha to pi Vm square sin square of omega t d omega t to the power 1 by 2. Okay. So it is a 1 by 2 pi integration from alpha to pi Vm square into sin square of omega t into d omega t to the power 1 by 2. Right? If you simplify it, you will be getting it as Vm upon 2 root pi into, it is like a pi minus alpha plus sine of 2 alpha divided by 2 to the power 1 by 2. Right? Simply we need to, yes, simplify this integral. Okay, so that we'll be getting this expression. Already we have simplified this expression. Okay, so which is equal to Vm by 2 root pi. So what is the Vm? You can check here. Vm is nothing but the peak value of the supply voltage. What is the peak value of supply voltage? Root 2 into V, na? So let me write it as root 2 into V divided by 2 root pi into, it is like a pi minus alpha means pi by 2 plus sine of 2 into alpha, that is 2 into alpha. Now I am putting it as a 90 degrees here, right? So here I have, yes, put alpha as the in radian, pi by 2. Here it is, I am keeping it is in degrees. Okay, so divided by 2. So because after, if alpha is after trigonometric term, then that's why I am putting it as a degree, because in my calculator the mode is a degree. Okay, so and while the arithmetic operation between the angles, okay, we need to take it in radian only, right? We need to take it in radian only to the power 1 by 2. So you can check here. What is the sine of 2 into 90? That is a sine 180. Sine 180 is a 0, right? So this term will become 0. So it is like a root 2 into V, or let me write as V upon root 2 pi. Okay, into it is like a pi by 2 to the power 1 by 2, right? Pi minus pi by 2 is a pi by 2. So root pi will get cancelled out. This root 2, it will become 2. Okay, so that's why it is equal to V by 2. This is the V0 RMS. It is a V by 2. So what is the power? Power consumed by the resistor. So power consumed by resistor means your, it is P0 average, which is equal to, we know, V0 RMS square divided by R, na? Right? Same thing we already discussed. So what is V0 RMS? V0 RMS V by 2. So it is a V by 2 square divided by R. So it is a V square divided by 4R. Can we write it as 1 by 4 into V square by R? What is V square by R? You can check. V square by R is, V square by R is nothing but capital P, na? So can I write it as 1 by 4 into P, 1 by 4 into P. So by how much factor it is reducing, or reduced to? Reducing by 1 by 4. So final answer will be your 1 by 4. Is this clear? Are you getting the point? Right? Okay. Okay. So some of the students are having problem. I will repeat in short once again. So first thing is, we need to understand this question. Here it is given that the circuit we are having, and in the absence of SCR, the power consumed by the resistor is capital P they have given. So first thing is, in the absence of SCR, we have drawn the circuit. In the absence of SCR means the thing is, either we can remove the SCR and keep it as an open circuit, or we can replace that with a short circuit. But if we keep it as an open circuit now here, then your load power will become 0. So this capital P will not be having any meaning now. Yes or no? Right? So that's why here we need to keep it as a short circuit only, right? If you replace it with open circuit, you will not get the answer at all. Okay. Next, so power consume. Now this is a simple single phase AC circuit. Now, if we connect the pure sinusoidal supply across a resistor, then whatever the waveform of the supply is there, the same waveform will appear across the resistor, right? So for that, we have written power consumed is equal to V0 RMS square by R. So V0 is like your Vs only. So in this case, the V0 means what? You will be getting a sinusoidal supply, same method of the supply, right? Same method of the Vs. Are you getting the point? Here V0 will be like your sinusoidal waveform you will be getting. It is same method of the Vs. So again, that power consumed is equal to V0 RMS square by R. But V0 and Vs both are same, na? So that's why it is Vs RMS square by R. So next we have calculated Vs RMS. How we have calculated Vs RMS? From this expression. This is the instantaneous value expression of Vs, na? So that's why it is Vs is equal to Vm into sine of omega t. So what is the peak value of supply voltage? It is a root 2 into V, right? So that's why I have written here peak value of supply is root 2 into V. Divided by root 2 means your RMS. Please try to understand. I have replaced this Vs RMS na, with Vm by root 2. And in the next step, I have replaced this Vm with root 2V. Why it is a root 2V? Because it is root 2 into V given. Okay. So that's why it is a, yes, here root 2 into V divided by root 2. So that's why we will be getting P is equal to V square by R. Second, in the presence of SCR, means when the SCR is present, then it is like our single phase half wave controlled rectifier. In the absence of SCR, if you check in the absence of SCR, it is not a rectifier circuit, na? It is like simple single phase AC circuit. But in the presence of SCR, we will be having the circuit like a thyristor. It is like a controlled rectifier circuit. Single phase half wave controlled rectifier. They have given alpha is 90 degree. So for alpha 90 degree, we'll be having the waveform of V0 like this. Okay. And from this waveform, we have calculated the V0 RMS. Okay. And from this V0 RMS, we have calculated P0 average because they asked for the load power. Na? So it is a P0 average, right? So final answer is 1 by 4. Okay. 1 by 4. Next. Now let us discuss the second question. Yeah. A single phase one pulse. This question is very important. Okay. This is for REL E load. Okay. So from this question, you will be getting all your doubts cleared. A single phase one pulse converter. So one pulse converter means what? It is a half wave rectifier, na? Right? One pulse means corresponding to one input cycle. In the output, will be getting only one pulse. So that's why it is a half wave rectifier. A single phase one pulse converter with REL E load has the following parameters. Supply voltage 230 volt at 50 hertz. So whether this 230 volt is a average value, RMS value, or peak value, come on. Whether this 230 volt is a average, RMS, or peak value. RMS, right? By default for AC supply, okay, whatever the value you are having, it is a RMS value. Okay, so 230 volt and frequency is 50 hertz. Resistor load is R is 2 ohm, L is 1 millihenry, and E is 120 volt. Extension angle beta is equal to 220 degree. Firing angle alpha is 25 degree. Calculate the voltage across SCR at the instant of triggering. Yes, we discussed the same thing. Okay, at the instant of triggering, what is the voltage across SCR? Second, find the voltage that appears across SCR when current decays to 0. Current decays to 0 means at omega t is equal to beta, right? We need to find the voltage across SCR. Find the PIV for the SCR. Average output voltage and current, V0 average, I0 average, and circuit turn off time. Okay, these things we need to find, right? So let us first note the data. Very important question. So Vs RMS is equal to 230 volt here. Frequency is equal to 50 hertz. Load resistor R is equal to 2 ohm. L is equal to 1 into 10 to the power minus 3 Henry. E is 120 volt. Extension angle beta is equal to 220 degree. Firing angle alpha is equal to 25 degree. Our task is calculate the voltage across SCR at the instant of triggering. Yes. What is the voltage across SCR at the instant of triggering? Yes, it is a Vm into sine alpha minus E na? Yes or no? Right? So voltage across SCR at the instant of triggering. So first bit, voltage across SCR at instant of triggering. This is a RLE load. We have already discussed this, right? Voltage across SCR at the instant of triggering. It is a Vm into sine of alpha minus E na. So Vm is, what is Vm? RMS is 230 na. So peak value will be 230 root 2 into sine of alpha. What is alpha? It is 25 degree. Sine of 25 degree minus what is the EMF E? It is a 120. So if you check, it is equal to into sine of 25 minus 120. Yes, it is 17.46, right? 17.46 volt. Okay. So this is the answer for the first bit. Now, this voltage is positive. This voltage is positive. The meaning is whether our alpha is greater than theta or less than theta. Come on. Here we are getting voltage across SCR at the instant of triggering is positive na, 17.46. So whether our alpha is greater than theta or less than theta, alpha is greater than theta na, right? Yes, alpha is a greater than theta, right? Alpha is a greater than theta. Good. Okay. So alpha is greater than theta. So therefore our thyristor will be in a forward bias mode and we have applied the gate signal. So definitely our thyristor will turn on, right? Next, second bit, find the voltage that appears across SCR when the current decays to 0. Okay. Voltage across SCR when current decays to 0. Second bit. So current flowing through thyristor becomes 0 or decays to 0 at omega t is equal to beta na, right? So next, voltage across thyristor when current decays to 0. Current decays to 0. Okay, that is at omega t is equal to beta. That is at omega t is equal to beta. Okay. So what is Vt? Vt is equal to Vm into sine of beta minus E na. So Vm is 230 root 2 into sine of beta they have given. It is 220 degree. Minus E is 120 volt. So if you check, it is equal to 230 root 2 into sine 220 minus 120, right? So it is a 329 minus 329.079 volt. Na? This is Vt, right? Means the reverse voltage will appear. Okay. So, and this is what we require na? In order to successful turn off the SCR, we need to maintain it in a reverse bias mode na? Right? So same thing. Next, third bit, PIV for the SCR. PIV rating of SCR. Yes. PIV rating of SCR. Yes, what is the PIV rating of SCR? Vm plus E na. So Vm is 230 into root 2. That is the peak value of supply voltage, and plus E is 120. So it will be, I think, 325.27 plus 120, 445.27 something. Okay. Right. 445.27. So this is your PIV rating. Correct. Next, average output voltage and current, V0 average and I0 average. Okay. So fourth bit, V0 average. Now for V0 average, we need to again write that expression here. Okay. because if you check the V0 average expression, okay, it is a very big, very long expression. Okay, you cannot memorize that expression. Okay, so we need to write it. So recall the V0 waveform. From omega t is equal to 0 to alpha, V0 is E na, right? Alpha to beta, same as of the supply voltage, beta to 2 pi, again E. Okay, so V0 average 1 by 2 pi, yes, integration from 0 to alpha, it is a E into d omega t, plus integration from alpha to beta, same as of the supply voltage. So Vm into sine of omega t into d omega t, plus integration from beta to 2 pi, it is again E into d omega t, right? This is your V0 average. Now we need to simplify it. So is equal to 1 by 2 pi into, let me write it as E into alpha plus Vm into, what is integration of sine, minus cos of omega t na? So I'm writing directly here. So minus cos beta plus cos alpha. This is the one thing, plus E into 2 pi minus beta. Okay. So further we can write it as 1 by 2 pi into E into bracket alpha plus 2 pi. 2 pi plus alpha minus beta plus Vm into cos alpha minus cos beta. No? Is this clear? Now we need to put the values here. Okay, so V0 average. So therefore V0 average is equal to 1 by 2 pi into, what is the E? E is a 120, na? Right? So it is a 120 into bracket, it is a 2 pi as it is, plus alpha. Now alpha here and beta, we need to put it in radian only. Don't put the alpha and beta in degrees. Okay, you will not get the correct answer, because here your 2 pi, na, this 2 pi is in radian. Okay, and while performing the arithmetic operations, okay, you need to put it in radian only. Okay, next. So alpha is 25 degree, right? So how to convert that degree into radian? So it is plus 25, right, into pi by 180. Okay, pi by 180. Simply multiply that angle with the pi by 180. You will be getting the radian. Next, minus beta. Beta is a 220, na? So it is a 220 into pi divided by 180. This is the one thing. Next, plus Vm. Vm is 230 into root 2 into cos alpha minus cos beta. So it is a cos of 25 degree minus cos of 220 degree, right? Beta is 220, na? So if we simplify it, please simplify it and check the final answer. Please check the final answer. $141.57, correct? 141.57, right? Okay. 141.57 volt. Okay. Yes. So this is your V0 average. Okay. Next, the second is our average output current, na? So I0 average. How to find the I0 average? We have discussed it. It is a V0 average minus E by R, na? V0 average minus E divided by R. So it is a 141.57 minus 120 and divided by R. R is a 2 ohm. Okay, so divided by 2. Yes, so it is 141.57 minus 120 divided by 2. 10.785 na. Right? Yes, yes. Okay, okay. And the last bit, circuit turn off time. We already discussed circuit turn off time, right? TC. I think it is a 5th bit. Okay, so TC for thyristor or for SCR, you can say. Yes, what is the circuit turn off time? Recall it. At omega t is equal to beta, current flowing through thyristor becomes 0 na, and after that the reverse voltage is maintained till 2 pi plus theta. Yes or no? So it is 2 pi plus theta minus beta divided by omega, right? 2 pi plus theta minus beta divided by omega na, divided by omega. Now we know beta omega is okay, it is 2 pi f. How to find theta? First thing is we need to find theta, then and only then we can simplify it, right? So how to find theta? At omega t is equal to theta, Vs is equal to E na? Yes or no? Right? So it is a Vm into sine of omega t. Yes. Vikrant, it is not 2 pi minus beta, 2 pi plus theta minus beta. Please check the Vt waveform, you will understand. Okay. So Vs is equal to E. So it is a Vm into sine of theta is equal to E. So therefore theta is equal to sine inverse of E by Vm na? Correct? So it is equal to sine inverse of E is 120. What is Vm? 230 into root 2. This is theta. So from this we can write theta. Therefore theta is equal to, yes, how much? Shift sine inverse of 120 divided by 230 root 2. 21.65 na? 21.65 degree. This is the theta na? Right? Next. Now theta we know. Now can we find TC? So therefore TC is equal to 2 pi plus, here we are having the arithmetic na operation. So that's why again theta we need to put in radian. So it is a 21.65 into pi by 180. Minus beta also we need to put in radian. Okay, beta also we need to put in radian. So into 220 into pi by 180. This is the one bracket divided by omega means 2 pi f. 2 pi into f. F is the supply frequency. They have given it is a 50 hertz na. So we need to put this, replace this f with a 50 hertz. Okay. So please check the TC value here. Circuit turn off time for thyristor. .98 millisecond na? Right. 8.98 millisecond. Right. This is a TC. Is this clear? Right. So this is about the numerical number 2 from your booklet. Okay. Next. So now we are going to discuss the full wave controlled rectifier. Okay, full wave controlled rectifier. Right. Single phase full wave controlled rectifier. Controlled rectifier. Single phase full wave controlled rectifier. Right. So in the single phase full wave controlled rectifier, we are having two configurations. One is the center tapped transformer configuration, or it is also known as a midpoint tapped transformer configuration. So first one is a midpoint tapped transformer configuration. Transformer configuration. And second one is a bridge configuration. Bridge configuration. Yes. Both will be the full wave control rectifiers only. Now, till now, whatever we discussed, these were the half wave control rectifiers. Now we are going to discuss the full wave control rectifier. In the half wave control rectifier, corresponding to one input cycle, we'll be getting only one pulse in the output, right? We'll be getting only one pulse in the output. Means corresponding to the positive half cycle of the supply, only we'll be getting the output as a non-zero. You can recall all the circuits, whatever we discussed under the half wave control rectifier, right? Corresponding to the positive half cycle of the supply, only we were getting the non-zero output, right? So that's why it was a half wave. Now here in a full wave control rectifier, corresponding to the positive half cycle as well as corresponding to the negative half cycle of the supply, okay, we are going to get the positive V0 only. We are going to get the positive V0 only, right? So that's why the another name for these circuitries or these converters are single phase two pulse rectifier. Okay, previously it was a single phase half wave, means single phase one pulse. Now it is a single phase two pulse, means corresponding to one input cycle. In the output, now we are going to get the two pulses. So that's why it is a single phase two pulse, right? So again, in the single phase half wave, we discussed if the input supply frequency is 50 hertz, then the output pulse frequency also equal to 50 hertz in the half wave. But here we'll be getting the, if corresponding to one input cycle, we are getting the two pulses na. So for a 50 hertz frequency, we'll be getting 100 pulses in 1 second, right? So the frequency of the output pulse is equal to 2 times the supply frequency. From waveform you will understand. Okay, so next we're having the two configurations. One is a midpoint tapped transformer configuration. It is also known as the center tapped transformer configuration, and second one is a bridge configuration. Okay, the difference between the two is, in a midpoint tapped transformer configuration, we require only 2 thyristors, whereas in a bridge configuration we require 4 thyristors. In a midpoint tapped transformer configuration, we require a specially designed center tapped transformer. Okay, but whereas the specially designed transformer is not required in a bridge configuration, right? Next, the major drawback of the midpoint tapped transformer configuration is the PIV rating of the thyristor. In a midpoint tapped transformer configuration, the PIV rating of a thyristor is a 2 times Vmax, whereas in a bridge configuration, the PIV rating of the thyristor is only Vmax. So you can say, if in a midpoint tapped transformer configuration, if the PIV rating is a double that of the bridge configuration, okay, so we require the thyristors which are having a more PIV rating. Are you getting the point? Okay, so as the PIV rating is more in a midpoint tapped transformer configuration, so generally these configuration, midpoint tapped transformer configuration or the converter, is generally not preferred. Okay, generally not preferred. Okay, so now let us discuss one by one. Let us put the heading midpoint tapped transformer configuration. Okay, midpoint tapped transformer configuration. Midpoint, or you can say the center tapped. Okay, okay. So midpoint tapped transformer configuration. Right? Okay. right? So midpoint tapped transformer configuration. Let us discuss for purely resistive load. Okay, R load circuit diagram. Is having a center tapping at the secondary side. Load is a purely resistive. Supply voltage Vs, and it is a 1:2 turns ratio. Thyristor is T1, T2. This is a VT1. Here it is a VT2. Let me write as a V0 and a I0, right? V0 and I0. Let me write it as a IT1. This is a IT2, right? So now in this is your IS, right? So the waveforms. Vs is equal to Vm into sine of omega t. Ig get pulse to thyristors 1 and 2. So this is Ig1. This is also Ig1. This is a Ig2. So it is alpha pi plus alpha 2 pi plus alpha, right? V0 and I0. There was the supply voltage. Okay. Yes. And the I0 in phase with V0 because load is purely resistive. We'll draw the waveform for the Vt at the end. Okay. So alpha pi plus alpha 2 pi, and here it is a 3 pi. That will be a 2 pi plus alpha. Okay. Now the red one is a I0 waveform and the blue one is a V0 waveform. Okay. So V0 and I0. Right? So now let us discuss the circuit operation. So here midpoint tapped transformer configuration. It is a single phase full wave controlled rectifier. Load is a purely resistive we are going to discuss. So in the circuit we are having a single phase AC supply, and what we expect, the expectation is output should be the flat DC. But let us discuss whether our thyristor is giving a flat DC or not. In a half wave rectifier also our expectation was the output should be a flat DC, but we observed the rectifier is not giving the flat DC output. Okay. Now, yes, this is a Vs which is equal to Vm into sine of omega t. Pure sinusoidal supply. Vm into sine of omega t, that is a pure sinusoidal supply. It is connected across the primary winding of the transformer. This is the transformer we are having. Okay. So across primary winding, we are having a Vs. The turns ratio of the transformer is 1:2, right? The meaning is it is like a step up transformer. Primary side voltage is Vs, so definitely the full secondary side voltage will be 2 times Vs. Yes or no? So can we say that the potential difference between, yes, this point and this point at the secondary side is equal to 2 Vs. Okay. So here Vs, so therefore here it is a 2 times Vs. Next, we are using a 2 thyristors T1 and T2, right? So one thyristor will be in a forward bias mode during a positive half cycle. Second one will be in a reverse bias mode during a negative half cycle. So which thyristor will be in a forward bias mode during positive half cycle? Which one will be in a reverse bias mode? Which one will be in a forward bias mode during the negative half cycle of the supply? We'll discuss. Okay. Here the load is a purely resistive. Voltage across thyristor is a VT1. Thyristor T1 voltage. This is the anode. Here it is a cathode. Na? So voltage across thyristor will be positive if anode is at a higher potential than that of the cathode. So this is a VT1. Voltage across thyristor T2 is a VT2. Current flowing to thyristor T1 is a IT1. Current flowing to thyristor T2 is a IT2. Okay. And here we are having a load voltage is a V0 with a polarity plus here and minus here. If the load current flowing to the load direction is like direction will be from right to left, then we are going to consider that I0 is positive. Otherwise, it will be negative. So this I0 indicates the positive direction or the direction of the, if the I0 is in this direction, then we are going to consider I0 is positive. Otherwise, it will be negative. Similarly, the V0 polarity, okay, for the positive values of V0, right? Next, now let us discuss the circuit operation. Okay, so Vs is, we are having 0 to pi positive, pi to 2 pi negative, 2 pi to 3 pi positive. So Vs is alternating positive, negative, positive, negative. Okay. So when Vs is positive, so when Vs is positive, consider the polarities plus here and minus here. Okay. So when Vs is positive, we are considering that the upper terminal is at a higher potential compared to that of the lower terminal. Okay. So that's why this higher potential will appear at the upper terminal of the primary winding of the transformer. Lower terminal, yes, this lesser potential will appear at the lower terminal of the primary winding of the transformer. So can we say that whatever the potential difference here, the full potential difference, that is the Vs, will appear across the primary winding? Yes or no? Right? So voltage across the primary winding is a Vs with this upper terminal is at higher potential compared to that of the lower terminal. Okay, this is we are discussing during Vs is positive. Okay, so it is a plus here, plus minus. Next, so function of the transformer is to transfer electrical energy from one electrical circuit to the another electrical circuit. Yes or no? Right? Without changing the frequency. Okay. So this transformer is transferring this Vs voltage. Okay. At the secondary side as a 2 Vs, because turns ratio is, we are having 1:2. Turns ratio is 1:2. Okay. So primary turns 1, secondary turns 2. Okay. So across full secondary winding, we will be having the voltage is equal to 2 Vs. Primary voltage is Vs, so therefore secondary voltage should be 2 Vs, na? Because it is a step up transformer. Okay. So now as the secondary winding is having a center tapping, so can we say that this voltage is equal to Vs, this voltage also equal to Vs. Across the full secondary winding, the voltage is 2 Vs, and we are having the center tapping, okay, at the secondary winding of the transformer. So can we say that out of these 2 Vs, this voltage will be Vs and this voltage will be Vs? Yes or no? Right? Because secondary winding is having a center tapping, na? So across full secondary winding, the voltage is 2 Vs. So that's why upper terminal and the midpoint of the secondary winding, the voltage is Vs, and from the midpoint and the lower terminal, the voltage is Vs. Okay. So that's why the total will be your 2 Vs. Now you can check here. Yes, in this case, here it is a higher potential point, here it is a lower potential point. Okay. So the windings, we are having the polarities, relative polarities, such that if the upper terminal is positive here, so here also the upper terminal will be positive. If here it is a lower terminal is negative, so here it is also lower terminal is negative. So you can check between these 2 points, the potential difference is 2 Vs. Now the meaning is, here it is plus, here it is minus. The meaning is from this point to this point, the potential is decreasing. Na? This is a higher, this is a lower. So can we say that from upper terminal to the lower terminal, the potential is decreasing. Okay, so as the potential is decreasing from upper terminal to the lower terminal, can we say that compared to the upper terminal, the center point potential will be lesser, because potential is decreasing now from upper terminal to the lower terminal. So compared to the upper terminal, the center point potential will be lesser. Again, can we say that compared to the lower terminal, the center point potential will be higher? You can check across the secondary winding. Suppose if I am having a 100-volt voltage, upper terminal minus lower terminal, the potential difference is 100 volt. So can we say that if this is 100 and if I consider the lower terminal potential is 0 volt, definitely the upper terminal potential will be equal to 100 volt. So here it is 100, here it is a 0 volt. So can we say that compared to that 100, the center point potential will be lesser, na? Center point potential will be like a 50 volt only, right? So compared to the upper terminal, center point potential will be lesser. But compared to the lower terminal, the center point potential will be higher. Are you getting the point? So that's why I've written plus, minus, and plus, minus. Is this very clear to all? This is very important. Otherwise, you will not understand which thyristor will be in a forward bias mode, which thyristor will be in a reverse bias mode. So please keep it in mind. When Vs is positive, it is like a plus here, minus here. So this plus will appear here, this minus will appear here. So this plus will be, yes, reflected at the secondary side like this: upper terminal positive, lower terminal negative. So from upper to lower terminal at the secondary side, potential is decreasing. So compared to this statement is very important. Please listen. Compared to the upper terminal, the center point potential will be lesser. Compared to the lower terminal, the center point potential will be higher. Because what the statement I have done, from upper to lower terminal at the secondary side, the potential is decreasing, na? So potential decreasing meaning is compared to this one, definitely the center point potential will be lesser. Compared to the lower, this potential will be higher, right? So that's why if Vs is positive, it is like a secondary side plus, minus, plus and minus will be having. Next. So now this is plus, this is minus, this is plus, this is minus. So can we say that this plus, that is a higher potential, is appearing at the anode of thyristor T1? And similarly, you can check this minus is appearing at the, it is like a lowest potential point. Huh? This lowest potential is appearing at the anode of thyristor T2. I'm saying when Vs is positive, it is like a thyristor T1's anode will be at a higher potential. Thyristor T2's cathode will be at a lower potential. So now can we say that initially both the thyristors will be off state, circuit will be at the rest position. Okay, so current will not flow in the secondary winding. So therefore what will happen? Current will not flow in the load also. So whatever the potential is, the same potential will appear here, same potential is, same potential is, same potential is. So can we say that this negative will appear here, same negative, and same negative? Means whatever the voltage here across the secondary winding, upper half part, that will appear across the thyristor T1. Okay, so thyristor T1 will be in a forward bias mode, right? So higher potential is appearing at the anode of thyristor T1. So definitely your cathode potential will be lesser than that of this higher potential. And the lower potential is appearing at the anode of thyristor T2. So therefore the cathode potential will be somewhat more than that of this potential. Or you can check, you can assume initially both the thyristors are in off state. So this potential will appear here, same potential. Means midpoint potential will be appearing at the anode of thyristor T2. Midpoint potential will appear at the cathode of, midpoint potential will appear at the cathode of thyristor T2. Midpoint potential will appear at the cathode of thyristor T2. T1, T2 cathode, the midpoint potential is appearing. So here it is higher, here it is lower. So thyristor T1 forward bias. Here it is higher, here it is lower, here it is higher. Thyristor T2 reverse bias. So this is where Vs is positive. When Vs is negative, what will happen? It is like minus here, minus, plus, minus, plus, minus, plus. Okay, means polarities will be reversed. So if the polarities are reversed, means minus here, plus here it is minus, here it is plus. So now here it is a plus. So this plus means thyristor T2's anode will be at a more potential. Okay, higher potential. So T2 will be in a forward bias mode. And here it will be minus now. So if this is minus, thyristor T1's anode will be at a lesser potential. So T1 will be in a reverse bias mode. So please keep it in mind. In this configuration, that is midpoint tapped transformer configuration, when Vs is positive, T1 will be in a forward bias mode, T2 will be in a reverse bias mode. When Vs is negative, T2 forward bias, T1 reverse bias. Okay, so let me write here. Yes. When Vs is positive, yes, T1 will be in a forward bias mode and T2 will be in a reverse bias mode. This is the one thing. Second, when Vs is negative, thyristor T1 reverse bias. And thyristor T2 forward bias. Okay, T1 reverse bias, T2 forward bias. Okay, so now you can check when Vs is positive, we know thyristor T1 forward bias. So that's why we are going to apply the gate signal to thyristor T1 only. We are not applying the gate signal to thyristor T2, right, during 0 to pi, because T2 is in reverse bias mode, na? Right? So when Vs positive, gate pulse is applied to T1. When Vs is negative, gate pulse is applied to T2 only, because T2 is in forward bias mode. When Vs positive, again we are going to apply the gate pulse to thyristor T1. Okay. So therefore at alpha, gate pulse is applied to T1. At pi plus alpha, gate pulse is applied to T2. At 2 pi plus alpha, gate pulse is applied to T1. Is this clear? Right? Next, now let us discuss the circuit operation. Okay, for different intervals like 0 to alpha, alpha to pi, and pi to pi plus alpha, and pi plus alpha to 2 pi. Okay, we are going to discuss the circuit operation. So let me write, for omega t is equal to 0 to alpha. So for omega t is 0 to alpha, thyristor T1 forward bias mode, but we have not applied the gate signal. So thyristor T1 will be in a forward blocking mode, na? Right? Thyristor T2 reverse blocking mode. Okay. So when Vs is positive, let me draw the circuit. It is like this. This is a Vs plus minus. Here it is plus, here it is minus. This is Vs. We're having a 1:2 transformer. Thyristor T1 is in a forward bias mode, but we have not applied the gate signal, right? So this voltage is Vs. So it is a minus here, plus here, minus here. Okay, this voltage is also Vs. Okay, so this is a R. This voltage is V0. Current is a I0. Here it is a VT1. Next IT1, IT2, and here VT2. Right? So this is the equivalent circuit during 0 to alpha. During 0 to alpha, what is happening? Thyristor T1 forward blocking mode, thyristor T2 reverse blocking mode. Okay, so let me write T1 forward blocking mode, and T2 reverse blocking mode. Reverse blocking mode, right? Next, so T1 is in a forward by blocking mode, T2 is in a reverse blocking mode. The meaning is both the thyristors are in a off state only. Okay, so whether the current will flow from, yes, a source to the load, source to load, no. So that's why I0 is equal to 0. Yes or no, right? I0 is 0. IT1 is also 0. Okay, so similarly your supply current is also 0. IS is also 0. Now in this case, supply current means we are going to consider this secondary part current. Secondary part current. Okay. Next, so I0 0, IT1 0, IS is also 0. Okay. So now here, what is the V0 according to Ohm's law? V0 is equal to I0 into R. Right? V0 is equal to I0 into R. Okay. So it is equal to 0 volt. So V0 0, I0 0, IT1 0. What about the VT1 here? Yes, VT1. Can we apply KVL to this part? KVL to the upper loop? Yes. KVL to upper loop. It is like a plus Vs minus VT1 minus V0 is equal to 0. Out of that, V0 is 0. So therefore, can I write VT1 is equal to Vs? Voltage across thyristor T1 is a positive. Okay. What about the VT2? We can apply KVL to this loop. Okay. Either you can apply KVL to the second loop, that is the lower loop, or you can apply KVL to the outer loop also, doesn't matter. Okay. In both the ways, you will be getting the same answer. So KVL to lower loop. KVL to lower loop. So it is the plus Vs plus V0, okay, plus Vt2 is equal to 0. Out of that, V0 is 0. So Vt2 is equal to minus Vs now. So Vt1 is Vs, that is a positive voltage because thyristor T1 is in a forward bias mode. Thyristor T2 is in a reverse bias mode. So voltage across thyristor T2 is a negative. So please keep it in mind. In this configuration, if both the thyristors will be in a off state, the thyristor which is in a forward bias mode or a forward blocking mode, across that thyristor the voltage will be Vs, and the thyristor which is in a reverse blocking mode, across the thyristor the voltage will be minus Vs. Okay, this same is going to repeat for other loads also. Okay, so please note it. For this configuration, that is a midpoint tapped transformer configuration, if both the thyristors are in a off state, the thyristor which is in a forward blocking mode, across that thyristor the voltage appearing is equal to plus Vs. The thyristor which is in a reverse blocking mode, across that thyristor the voltage appearing is a minus Vs. Okay, one is a plus Vs, second one is a minus Vs. Is this clear? Right? Next, so if you check the waveform, yes, from 0 to alpha V0 0, I0 is also 0. Okay, next, Vt1 Vt2 waveform will draw at the end, right? Next, so this is from 0 to alpha, so I0 0, V0 is also 0. Next, from alpha to pi, what will happen? For omega t is equal to alpha to pi. Yes, for omega t is equal to alpha to pi, what will happen? Let us discuss. Okay, alpha to pi. Right? Okay, okay. Terminal of Vt2. Why it is wrong? What is wrong in Vt2? Anode cathode na, so plus minus only, right? Okay, 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 okay. Yeah, single phase full wave uncontrolled rectifier. I will tell you what is the difference between that. Okay, for controlled rectifier, if you put alpha equal to 0 degree, you will be getting the uncontrolled rectifier. Okay, so here the operation is same steps we are going to repeat. Okay, so that's why I have directly switched to the full wave controlled rectifier. Right? Next, so Vt2 is minus Vs. Now for omega t is equal to alpha to pi, so now we are going to apply the gate signal to thyristor T1 na. Okay, so let me draw the circuit. I am drawing only the secondary side circuit. Thyristor T1 will be in a forward conduction mode now, right? Thyristor T2 reverse blocking mode only. Okay, so this is a Vt2, this is a Vt1, here it is IT1, here it is IT2. Okay, suppose this is a R, this is a V0, here it is a I0. This voltage is Vs plus minus Vs, here it is also plus minus Vs, right? So for alpha to pi, thyristor T1 is in a conduction mode, so current will flow into this loop. Yes or no? Current will flow into the upper loop. Okay, so what is the Vt1 here? Vt1 is equal to 0. Voltage across thyristor T1 is a 0 volt because thyristor T1 is in a conduction mode. Okay, now if you apply KVL to this loop, KVL to the upper loop, KVL to upper loop, we'll be getting it as a plus Vs minus Vt1 minus V0 is equal to 0. Out of that, Vt1 is 0. So therefore, what is V0? V0 is same as that of the supply voltage. Okay, it is a Vs only, it is not 2 Vs. Be careful, V0 is equal to Vs only. Okay, now, so V0 is equal to Vs. Now, can we apply KVL to either to the outer loop or KVL to the lower loop? Okay, in order to find the Vt2. Okay, you can apply either KVL to the outer loop or KVL to the lower loop. In both the ways, you will be getting the same answer. Okay. So suppose let us apply the KVL to the outer loop. So KVL to outer loop. It is a plus VS, na? Plus VS. Here it is minus to plus. So plus VS. Minus to plus VS. So that's why I've written plus VS. Minus VT1. Next outer loop we are applying, na? Plus VT2 is equal to 0. VT1 is 0, na? Thyristor T1 is in a conduction mode. So therefore, can we write VT2 is equal to minus 2 VS? Means voltage across thyristor T2 is a 2 times the supply voltage. Definitely it will be reverse voltage only, because thyristor T2 is in a reverse blocking mode, na? Right? So that's why VT2 is a minus 2 VS. So the statement here, whatever we discussed, for a center tapped transformer configuration, the PIV rating is a 2 times Vmax, na? So you can check if VT2 is 2 times VS. So what is the PIV rating? It is a 2 times Vmax. So this is the drawback of center tapped transformer configuration. Okay. So means here we require the thyristor or the switches with a high PIV rating. Okay, high PIV rating, right? So VT2 is a minus 2 into VS, right? The meaning is, or by observing this circuit also, you can write what is the VT2. No need to apply the KVL also. How to write? Please check. Once this thyristor is in a conduction mode, na? Once this thyristor is in a conduction mode, whatever the voltage across the full secondary winding will appear as a reverse voltage for this thyristor, na? You can check whatever potential is same potential here. T1 is in on state, so same potential will appear here. Same potential here. Whatever the potential at the lower terminal, same will appear at the anode. So VT2 will be like a voltage across the full secondary winding. Okay, so that's why VT2 is a minus 2 VS we are getting, right? So from alpha to pi, if you check the waveform for omega t is equal to alpha to pi, yes, V0 is a VS. It is not a 2 VS, it is a VS. And I0 will be in phase with the V0, na? So that's why it is a VS by R. Okay, so let me write a I0 also. I0 is equal to V0 by R, which is equal to VS by R, right? So same as that of the your VS, only thing is change in a magnitude. Okay, change in a magnitude, right? So I0 and V0. So we're having, yes, here it is alpha to pi. V0 is a VS and I0 will be in phase with the V0, right? So it is a VS by R, right? Next, so this is for alpha to pi. Next, from pi to pi plus alpha, what will happen? For omega t is equal to pi plus alpha. For omega t is equal to pi to pi plus alpha. Let us discuss pi to pi plus alpha. So now important thing before that, you can check this circuit. Previously, yes, we made one conclusion that when both the thyristors will be in an off state, the thyristor which is in a forward bias mode, okay, or the forward blocking mode, across that thyristor the voltage appearing is a plus Vs. The thyristor which one is in a reverse blocking mode, across the thyristor voltage appearing is a minus Vs. This is when both the thyristors are in a off state. Now from this now can we say that out of the two, if one thyristor is in a on state, if any one thyristor is in a on state, means what? Definitely that thyristor will be in a forward conduction mode only. Okay, then the thyristor which is in a off state, that is the reverse blocking mode, across that thyristor the voltage will be equal to minus 2 Vs. Okay, 2 times the supply voltage, right? Means if both the thyristors are in off state, what the thyristor which is in a forward bias mode, across the thyristor the voltage is plus Vs. Thyristor which is in a reverse blocking mode, across the thyristor voltage will be minus Vs. When one is in a on state, second one is in a off state, the thyristor which is in a off state, across the thyristor the voltage appearing is equal to 2 times Vs, right? So please note it, this is very important. Now, so for omega t is equal to pi plus alpha, for omega t is equal to pi plus alpha. Okay, so I think we'll take a break here. It's 7. Okay, and after the break we'll discuss the remaining two modes, pi plus alpha and pi plus alpha to 2 pi. Okay, yes. We'll start at 7:27. Okay, right. single phase half wave control rectifier with C load. Okay. So as long as your real life load is considered, we don't have the capacitive load, right? So that's for half controlled, for half wave uncontrolled rectifier. We considered only it as for understanding. Okay. For pure C load, how it behaves, right? So I have not skipped it. Let me tell you. You can check any of the book. You will not find the L purely inductive, purely capacitive. So next, for omega t is equal to pi plus alpha. Okay. So let us discuss the circuit operation. So for pi to pi plus alpha, we're having the supply voltage is negative. Okay. Supply voltage is negative. So now thyristor T2 will be the forward bias. Thyristor T1 will be the reverse bias. Okay. So Vs R V0 I0. Okay. This is VT1 and here it is a VT2, IT1 and IT2, right? So thyristor T2 forward blocking mode, thyristor T1 reverse blocking mode here, right? So T1 reverse blocking mode, and T2 forward blocking mode. So as both the thyristors are in off state, whether the current will flow from source to load? No, right? So I0 is 0 ampere. What is V0? V0 also equal to 0 volt, right? Next, as both the thyristors are in off state, so what is VT1 and what is VT2? VT1 is in a reverse blocking mode, na? So VT1 will be equal to minus Vs and VT2 is equal to plus Vs. You can apply KVL to the loop, you will understand, right? So for pi to pi plus alpha, V0, 0, I0, 0. So you can check the circuit waveforms. Pi to pi plus alpha, V0, I0, both are 0, right? Next, for pi plus alpha to 2 pi, what will happen? For omega t is equal to pi plus alpha to 2 pi. Yes. Again, supply voltage is negative, and now we are going to apply the gate pulse to thyristor T2, right? So gate pulse is applied to thyristor T2. Here it is thyristor T1. So this is minus plus. Here it is a Vs, minus plus Vs. Resistive load V0, I0, VT1, VT2, IT2, and here it is IT1. Yes. So now in this circuit, if you check thyristor T2 is in a forward conduction mode. T2 is in a forward conduction mode. And what about T1? Reverse blocking mode. Reverse blocking mode. Reverse blocking mode. Okay. Next. So what about VT2? VT2 is equal to 0 volt, right? Voltage across thyristor T2 is 0 because thyristor T2 is in a conduction mode, na? Okay. Now you can apply KVL to this loop, KVL to the lower loop to get V0. KVL to lower loop. You can check it is a plus Vs minus VT2 minus V0 is equal to 0 na. VT2 is 0. So therefore can we write V0 is equal to Vs. So please be careful. V0 is a positive here. Vs is your negative, but V0 is positive here. You can check because current is flowing into this loop na, and you can check the direction of the current in the load branch. It is from right to left, and whereas from omega t is equal to alpha to pi also. If you check when thyristor T1 was in a conduction mode na, at that time also the current flowing through the load, it was from right to left. So in both the cases, that is from alpha to pi or pi plus alpha to 2 pi, even though your supply voltage is reversed, but the direction of current flowing through the load is in the same direction only. Are you getting the point? So that's why even though your supply voltage is negative, but in the output voltage we are getting the positive value. We are getting the positive value. Is this clear? Right? So this is V0 is equal to Vs. What about the I0? I0 is equal to V0 by R. Okay, I0 is equal to V0 by R, which is equal to Vs by R, which is equal to Vs by R. So here I0 is equal to Vs by R. I0 is equal to Vs by R, right? Next, what is the VT1? Can anyone? What will be the value of VT1? Out of the two now, one thyristor is in on state, second one is in off state. So what will be the value of VT1? Yes, VT1 will be equal to 2 Vs. Yes or no? It is a 2 Vs, but it is a negative, na? Right? Because thyristor T1 is in a reverse bias mode. So that's why it is a VT1 is equal to minus 2 Vs. VT1 is equal to minus 2 Vs. Or you can apply KVL to this loop, outer loop or to the upper loop. You will be getting the same value. Okay, it is a minus 2 into Vs. Okay, minus 2 Vs. So this is for pi plus alpha to 2 pi. So please be careful. Pi plus alpha 2 pi, your V0 is a positive. I0 also positive. Even though the supply voltage is negative, but your V0 is a positive. Okay, because current flowing through the load is having the same direction, na? Right? Right to left only current is flowing. Okay. So here you can check the waveform. Yes, pi plus alpha 2 pi. Even though the supply voltage is negative, but I0 is V0 and I0 both are positive. Okay. So this is a till 2 pi. After 2 pi, what will happen? Again, the same cycle will repeat. Right? So you can check corresponding to the positive half cycle also we are getting the positive V0. Corresponding to the negative half cycle also we are getting the positive V0. So that's why it is a full wave rectifier. And the, as I said, the another name is single phase 2 pulse, na? Corresponding to one input cycle. In the output, how many pulses we are getting? So one input cycle means 0 to 2 pi. In the output, we are getting, yes, this is the one pulse and this is the second pulse. So we are getting the 2 pulses. So that's why it is a single phase 2 pulse. Okay, it is also known as a single phase 2 pulse SCR or a single phase 2 pulse rectifier. Okay, so now if the input supply frequency is 50 hertz, output pulse frequency is 100 hertz, na? 2 times. Okay, so now let us derive the expressions. Let us derive the expressions. So V0 average is equal to, yes, you can check the waveform. Whatever the waveform we are having from 0 to pi, the same is repeating from pi to 2 pi, na? Same is repeating from 2 pi to 3 pi. So what is the periodic angle here? Periodic angle is the pi, na? Yes or no? Periodic angle is pi, right? So corresponding to pi radian, we are having only one pulse. So it is a 1 by pi. Are you getting the point? Either you can write 2 by 2 pi. Yes. Either you can write 2 by 2 pi or you can write 1 by pi. Both are having the same meaning. Okay. But here you can check between zero, whatever the waveform we are having in the V0, from 0 to pi, the same is repeating from pi to 2 pi, same is repeating from 2 pi to 3 pi. So periodic angle is a pi, right? So it is a 1 by pi. Let me write it as a 1 by pi. Integration. So in the 1 by pi, if you check, the effective interval is alpha to pi only, na? Because 0 to alpha, V0 is 0. So effective interval is only alpha to pi. Okay, so it is a alpha to pi, right? What is the value of V0? Same as of the supply voltage, na, during this interval. So it is a Vm into sine of omega t into d omega t, right? So it is equal to Vm by pi into integration of sine is minus cos of omega t. limit alpha to pi. So if you check, it is equal to Vm by pi into 1 plus cos alpha. Okay, this is the V0 average. Whereas if you compare this expression with a single phase half wave control rectifier, in the single phase half wave control rectifier, it was a Vm by 2 pi. Now it is a Vm by pi. The meaning is here the average output voltage is doubled, right? Compared to that of the half controlled, full control to that of the half wave control rectifier. Full wave control rectifier, yes, will be giving the 2 times the output voltage. Okay, so Vm by pi into 1 plus cos alpha. Next, what is the I0 average? I0 average is equal to V0 average by R. Load is a purely resistive. Okay, so it is equal to Vm by pi R into 1 plus cos alpha. Right? 1 plus cos alpha. This is the I0 average. Right? Next, V0 RMS. RMS value of output voltage is equal to 1 by pi integration from alpha to pi. Output voltage is same as that of the supply voltage. So square it. Vm square into sine square of omega t into d omega t to the power 1 by 2. Square root of mean of squared value. Okay. So it is equal to Vm upon root pi into integration from alpha to pi. I have taken this Vm square outside. So it will become Vm. This pi also outside of the square root. So it is a root pi. Okay. Alpha to pi 1 minus cos of 2 omega t divided by 2 into d omega t to the power 1 by 2. So it is equal to Vm upon root 2 pi into, this can be written as a omega t minus sine of 2 omega t divided by 2 limit alpha to pi to the power 1 by 2. So it is equal to Vm upon root 2 pi into pi minus alpha minus sine of 2 pi by 2 plus sine of 2 alpha by 2 to the power 1 by 2. Right? So you can check here, sine of 2 pi is 0, sine 360. So that's why it is a Vm by root 2 pi. We can write V0 RMS. Vm by root 2 pi into pi minus alpha plus sine of 2 alpha divided by 2 to the power 1 by 2. Right? This is a V0 RMS. Okay, Vm by root 2 pi into pi minus alpha plus sine of 2 alpha by 2 to the power 1 by 2. Right? So, whereas if you recall it from single phase half wave control rectifier, it was like Vm by 2 root pi. Now it is a Vm by root pi. Right? So, next I0 RMS. V0 RMS by R. V0 RMS by R. Right? What about the load power? P0 average, that is the load power or the output power, is equal to, load is purely resistive. So it is a V0 RMS into I0 RMS, or which is equal to V0 RMS square divided by R, which is equal to I0 RMS square into R. Right? Same expression. Okay. Next, what is the conduction time of thyristor? Each thyristor. Conduction time of each thyristor. Yes, thyristor T1 will be in a conduction mode from omega t is alpha to pi na. So conduction angle is pi minus alpha. So it is a pi minus alpha divided by omega. Conduction time of each thyristor. Right? PIV rating of each thyristor. PIV rating of each thyristor. We discussed it. It is equal to 2 times Vmax. Na? Now, let us draw the waveform of voltage across thyristor. Okay. So, let me draw the voltage across thyristor T1. Omega T 0. Right. So, we're having the intervals like 0 to alpha, alpha to pi, pi to pi plus alpha, pi plus alpha to 2 pi. Okay. So yes. During 0 to alpha, what is VT1? During 0 to alpha, what is VT1? Yes, it is a VS, na? Thyristor T1 was in a forward blocking mode, so it is a VS. At alpha, thyristor T1 starts conduction. From alpha till pi, thyristor T1 is in a conduction mode. Pi to pi plus alpha, pi to pi plus alpha, both the thyristors will be in off state, na? Thyristor T1 was in a forward blocking mode. Thyristor T1 reverse blocking mode. Thyristor T2 forward blocking mode. Okay, so waveform will be like this. So it is a VS. This is also VS or minus VS, you can say. And from pi plus alpha to pi, it will be a 2 times VS. Please try to understand this waveform. We have already written the expression of VT1 and VT2. I have drawn only the waveform of VT1. Okay, this is like your minus 2 VS. This is will be your minus VS. So it is a combination of VS and 2 VS. Combination of VS and 2 VS. Okay, you can check na. 0 to alpha, both the thyristors are in off state na. So we are having the conclusion that when both the thyristors are in off state, the voltage across the thyristor which is in a forward blocking mode, across the thyristor the voltage is VS. The thyristor which is in a reverse blocking mode, across the thyristor the voltage is minus VS. So we are drawing the waveform of thyristor T1 na, right? VT1. So thyristor T1 during 0 to alpha, forward blocking mode, right? So that's why VS voltage is VS. Alpha to pi, thyristor T1 is in a conduction mode, right? Next, so voltage is 0. Pi to pi plus alpha, thyristor T1 and T2 both are in off state na. In that thyristor T1 reverse blocking mode, thyristor T2 forward blocking mode. So thyristor T1 reverse blocking mode, so voltage will be minus VS. And from pi plus alpha to 2 pi, you can check the circuit. Pi plus alpha to 2 pi. T2 is in a conduction mode na. So voltage across thyristor T1 will be double na. Voltage across full secondary winding. But from pi plus alpha to 2 pi, thyristor T1 reverse bias mode. So that's why it is a minus 2 VS. Okay. So what is the PIV rating here? PIV rating is equal to 2 times Vmax. Now this is equal to minus 2 Vmax, but PIV is 2 Vmax. Okay. So that's why here I have written it as a 2 Vm. Is this clear? Right. So this is from, yes, VT1. This is for VT1. We can draw the waveform for VT2 also, but not required. Okay. Because we use the word here, each thyristor. Na? Same waveform will be getting. The only thing is this interval will be shifting. Because for T2, pi plus alpha to 2 pi, T2 is in on state, na? Right? So for T2, pi plus alpha to 2 pi, VT2 will be 0. And for other intervals, the same waveform will be, only shifted waveform will be getting. Okay? So this is a VT1. Now, circuit turn-off time for thyristor T1. TC for thyristor T1. TC for thyristor T1. Yes, can anyone? Check the instant at which current flowing through thyristor T1 becomes 0. Check the instant at which current flowing through thyristor T1 becomes 0. Yes. Thyristor T1 current becomes 0 at omega t is equal to pi. After that, the reverse voltage is maintained till 2 pi. Na? So from pi till 2 pi, we're having the reverse voltage. So what is the circuit turn-off time? 2 pi minus pi divided by omega. Na? 2 pi minus pi divided by omega. That is equal to pi by omega. Is this clear? This is the circuit turn-off time for thyristor T1. Next, now can we draw the waveform of IT1? Current flowing through thyristor T1. How will the waveform of IT1? Yes, you can check. We are having the waveform of I0. This is 0, alpha, pi, pi plus alpha, and 2 pi. Okay. I0 is like this. 0 to alpha 0, right? Alpha to pi in phase with a V0, pi plus alpha to 2 pi. Again, it is like this. Okay, this is how we are having the waveform for I0, right? During this, we are having it is a Vs by R. Na? Yes, from this, how to draw the waveform for IT1, current flowing through thyristor T1? Come on. Thyristor T1 is in a conduction mode only from alpha to pi. Na? right? So 0 to alpha thyristor T1 off state. Okay, alpha to pi T1 conducts. So here it is a T1, and from pi plus alpha to 2 pi T2 conducts na. So you can check whatever the pulse here now we are having I0 for alpha to pi. The same will appear as an IT1, right? So IT1 waveform will be like this. And after that it will be 0 only, right? Alpha, pi plus alpha, and here it is a 2 pi, right? This is same method of load current. It is a Vs by R, or you can write V0 by R also, doesn't matter, right? Is this clear? Okay, so this is the IT1 waveform. So here it is IT1. Similarly, we can draw the waveform for IT2 also. For IT2 waveform, yes, only pi plus alpha 2 pi will be having the non-zero. Okay, because thyristor T2 will be in a conduction mode only from pi plus alpha to 2 pi, na, right? So I22 will be non-zero only during this interval, right? Next, can we draw the waveform of IS, supply current waveform? How it will be? IS waveform. Alpha, pi plus alpha, and here it is 2 pi. Yes, how is the waveform of IS, source current? You can check the circuit diagram. Yes, IS is nothing but secondary winding current. IS is nothing but your secondary winding current. So you can check here. Okay, so in this circuit, if you check 0 to alpha, these two thyristors are in off state now. So during 0 to alpha, what is the current in the secondary winding? That will be 0 only, na? Yes or no? Right? So 0 to alpha, these two are in a off state, right? So that's why your current flowing through the load is 0. So that's why your source current is also equal to 0. So 0 to alpha, it is a 0. Let me draw here. 0 to alpha, it is a 0. Alpha to pi, from omega t is equal to alpha to pi. Thyristor T1 is in a conduction mode. So if you check, when T1 conducts, only in the upper half part of the secondary winding the current will be flowing. Yes or no? Right? When thyristor T1 is in a conduction mode, what about the current flowing through the lower half part of the secondary winding? That will be 0, na? Because thyristor T2 is in off state. So when T1 conducts, the current will flow only in the upper half part. Okay. And what is the value of that current? It is same method of the load current, na? You can check. IS means this current I am saying, secondary winding current. Okay. So you can check I0 is equal to this current only. Okay. So I0 is equal to IS. But direction of this current is in the upward direction, na? Because current is flowing in the clockwise direction in this loop. So in this part of the winding, the current direction is in upward direction. Okay. Right. So what is the value? It is a IS. Okay. That is the same method of the I0. So we can write it as same method of the I0, and it is a positive. I0 is positive, right? And current is flowing in the upward direction. So let us consider it as a positive. Pi to pi plus alpha, what is happening? Pi to pi plus alpha. Again, both the thyristors are in off state. If both the thyristors are in off state, what about the current in the secondary winding? 0, right? So current in the secondary winding will be again 0 from pi to pi plus alpha. After pi plus alpha, what will happen? Yes, from pi plus alpha to 2 pi. Thyristor T2 is in a conduction mode now. Supply voltage polarity is reversed now. It is like a minus here, plus here. T2 is in on state. Current is flowing in the lower half part. Okay. Current is flowing in the lower half part of the secondary winding. And what is the current direction in this loop? It is in the anti-clockwise direction. If this current is in anti-clockwise direction, what is the direction of the current in the secondary winding? Direction of the current in the secondary winding is in a downward direction. So for upward direction, if we take the positive current, then for downward current, we need to take the negative, na? Right? So please be careful. The IS waveform will be like this. Try to understand this. This is very important. Right? This type of waveform means even though your load current is positive, but your supply current is a negative. Supply current is a negative. Is this clear? So if this is the nature of your secondary side current, then what about the nature of the primary side current? Again, the nature will be same, na? Primary side current, right? The only thing is it is a 1:2. So it is a step up for the voltage. So for current, it will be like a step down. Okay. Step down means this will be more current and this will be lesser current, means here we will be getting the double current actually. Okay, so is this clear? So this type of nature will be getting. I have drawn it as for secondary winding current, right? Yes or no? Right. So this is the IS. So now here, yes. Okay. Yes, supply current is also zero. Are you getting the point? 0 to alpha and pi to pi plus alpha. Supply current is zero. You can check the transformer operation. If the load current is zero, and in our circuit we have considered the ideal transformer, that is nothing but the transformer is not having any losses. Okay, so if the load current is zero, your supply current is also zero, or the transformer current is also zero. Okay, source current, right? So transformer will not draw any current from the supply. Okay, right? So you might be thinking that, sir, in a transformer we are having that when transformer is on no load, it is drawing some magnetizing current. Here the magnetizing current we have neglected. Okay, this is a power electronics. Okay, right? So next, so this is the source current. Now from this again we can find the IS RMS also, right? IT1 RMS also. They have asked the questions like this. Okay, they will not ask in the GATE or ES examination very straightforward questions, just like what is the I0 average, I0 RMS. No, they will ask the question like what is the IT1 average, IT1 RMS. So for that you need to understand this IT1 waveform, this IS waveform. Is this clear? Right? So let us draw, let us find the IT1 RMS also. Okay, IT1 RMS. This is only for understanding purpose. I am yes, how to find the RMS value we have already discussed. Okay, so this is we are discussing just like over and above here. Okay, so now again don't compare this with when we go for the next configuration or the next load. So at that time you have not in this load you have not explained that IT1. We are only explaining this to understand it. Once you get an idea how to find the IT1 RMS, how to find the IT1 average, how to draw the IT1. Okay, right? Then you can, for any circuit you can find it. Okay, so IT1 RMS, because for all the circuits and for all the configurations, if you want to discuss all the loads, okay, R load, L load, C load, RL load, RL with the freewheeling diode, RL E load, RE load. Okay, so you require more than 100 hours for power electronics alone, right? So here you can check from alpha to pi. Okay, IT1 is a non-zero, and again you can check whatever the waveform for IT1 from 0 to 2 pi, the same will repeat from 2 pi to 4 pi, na? Right? So it is like a 1 by 2 pi. Now the periodic angle is 1 by 2 pi. In the I0 case, we consider the periodic angle is, it is a pi, because the waveform was repeating from 0 to pi, pi to 2 pi, same was repeating. But in the IT1, if you check, the periodic angle is 2 pi, right? So it is a 1 by 2 pi. 1 by 2 pi. Integration from, yes, integration from alpha to pi. Alpha to pi. Yes, what is the value of IT1? It is Vs by R, na? Means it is a Vm sin omega t divided by R. Okay. So it is a Vm sin of omega t divided by R into d omega t, right? To the power 1 by 2. Now can we simplify it? It is very simple, right? So it is equal to Vm square divided by, or let me take yes, RMS, na? It's a square we need to put, correct? It should be a square. So now further what we can do, we can take this Vm square divided by R square outside. Okay, and this divided by root divided by 2 pi also we can take outside. So it is like a Vm upon root 2 pi into R. Okay, Vm upon root 2 pi into R into what? Integration of sin of omega t. So it is alpha to pi 1 minus cos of omega t, sin square of omega t, right? So it is a 1 minus cos of 2 omega t divided by 2 into d omega t, right? To the power 1 by 2. Is this clear? We have taken Vm square divided by R square outside. So it is a Vm upon root 2 pi into R. And it will be like sin square of omega t is 1 minus cos of 2 omega t divided by 2. Okay, into d. So it is equal to Vm upon root 2 pi into R into this 2 also we can take outside. So it is like a 2 root pi. 2 root pi. Okay, into R into this can be written as a omega t minus sine of 2 omega t divided by 2. Okay, limit alpha to pi to the power 1 by 2. So it is equal to Vm upon 2 root pi into r. Okay, into pi minus alpha minus sine of 2 pi 0 na. So it is like only thing is sine of 2 alpha by 2 to the power 1 by 2, right? So if you compare this expression with the I0 RMS expression, right? So in the I0 RMS, we are having a V0 RMS by R na. And what is the V0 RMS expression? It is like you can check V0 RMS expression. Yes, V0 RMS we have written. Vm by root 2 into pi. Okay. And if I want to find the I0 RMS, then it will be like V0 RMS divided by R. Right? So it is like Vm upon root 2 pi into R. Okay. And this term, you can check this bracket here. And whatever the bracket here we are having in the IT1 RMS, this bracket is same as the top. This bracket na. The only thing is here we are having a Vm by root 2 pi. This divided by R means into R will be there. Okay. Vm by root 2 pi into R. But in this case, it is a Vm upon 2 root pi into R. So can we say that IT1 RMS is equal to 1 by root 2 into I0 RMS? If I multiply this term, with a root 2, then it will be like 2 root pi. Okay, so same we are getting here 2 root pi, right? So let me write here. Yes, so here IT1 RMS is equal to I0 RMS divided by root 2. This is your IT1 RMS. Is this clear? Right? So this is I0 RMS by root 2, IT1 RMS. Okay, next. Now can we find IS RMS? IS RMS. Okay, whether IS RMS and I0 RMS both will be same or different? Yes, my question is whether I0 RMS and IS RMS both will be same or different. Come on. Yes, think on the definition of the RMS. Square root means square root of mean of squared value. Whether IS RMS and yes, some are saying same, some are saying different. Okay. It will be same only. Why? Yes, listen it. I0 RMS is we are having 0 to alpha 0, I0, IS is also 0. Alpha to pi, it is a positive. This is also positive. Pi to pi plus alpha, it is 0. It is also 0. Pi plus alpha to 2 pi, it is a positive. It is a negative. Okay. But now here, if you check, RMS means what? Square root of mean of squared value. So we are taking the mean of the squared value. So if I take the square of this I0, what is the square of I0? It is I0 square. So what is the square of this positive? It is a positive value. Square of this positive, it will be positive value. Yes or no? So if we take the I0 square waveform, we will be getting 0 to alpha 0, alpha to pi same positive, but it is an increase because square we are taking. Pi to pi plus alpha, I0 square will be 0. Pi plus alpha to 2 pi, I0 is a non-zero, that is a positive. So I0 square will be also positive. Now if we take the IS square of the supply current or the source current, if we take 0 to alpha 0, alpha to pi square of the positive value. So this square and this square, whether both will be same or different, both will be same. Pi to pi plus alpha square will be 0 only because IS is 0, so its square will be 0. Pi plus alpha to 2 pi, from pi plus alpha to 2 pi, if you check, IS is negative. So what is the square of this negative value? It is again positive na. So can we say that pi plus alpha to 2 pi I0 is like this and its square is positive. Pi plus alpha to 2 pi IS is like this, so its square will be again positive. So can we say that square of this term both will be same or different? Both will be same only. Are you getting the point? If you draw the waveform of I0 square and IS square, you will be getting the same waveform. Is this clear? So if I0 square and IS square both are same, then what about the average value? Average of this is equal to average of this square is equal to average of this square. So if you put it into square root, you will be getting the same value now. Are you getting the point? Right? So even though your source current is a AC, I am saying your load current is a DC, DC means only positive 0, positive 0. So source current is positive 0, negative 0, means positive as well as negative values. So it is a AC. Both are having the different waveforms, but yes, RMS value of the load current and RMS value of the source current both are same only. Is this very clear to all? Right? Try to understand the meaning of that term RMS. Root means square. Square root of mean of squared value. So first of all, we need to square it. We need to take the average and we need to put it into the square root. So square of this I0 and square of this IS, both will be same. You will be getting. Okay. So IS RMS will be equal to your I0 RMS only. Okay. So let me write. IS RMS is equal to I0 RMS only. Okay. Which is equal to V0 RMS divided by R. Right. If you want for this waveform, you can find, you can derive the expression of I0 RMS. Oh, sorry, IS RMS. You will be getting the same expression at the end as that of your I0 RMS. Okay. So yes, so this is the IS RMS. Next, what is the input power factor? Input power factor. Input power factor. Yes, it is equal to, input power factor is equal to P0 average divided by Vs RMS into IS RMS. Na? Yes or no? P0 average upon Vs RMS into IS RMS. You can take Vs RMS, IS RMS to the left hand side. It is like Vs RMS, IS RMS into input power factor, means supply power factor. Sorry, supply power, which is equal to load power, na? Because in the circuit, if you check, we're having a, yes, supply, we're having a transformer, that is ideal transformer, so losses will be 0. We're having the two thyristors T1, T2, losses will be 0. Ideal switches we're having, so only load. So whatever the power supplied by the source is equal to power consumed by the load. So it is a P0 average upon Vs RMS into IS RMS. What is a P0 average? It is a V0 RMS into I0 RMS. Again divided by Vs RMS into IS RMS. So whether these two are same or different, these two are same, na? Right? Just now we have written. So therefore, can we write input power factor? Input power factor is equal to V0 RMS upon Vs RMS. Okay. V0 RMS upon Vs RMS. Right? So this is the input power factor, right? So this is for single phase full wave control rectifier with purely resistive load, center tapped transformer configuration. Now we are going to discuss for RL load. We are going to discuss for RL load, right? Next. Single phase full wave controlled rectifier with RL load. Yes. So same circuit diagram. The only thing is in the load now we are going to add the inductor. Right? RL load we are having. Thyristor T1 voltage is VT1. Thyristor T2 voltage is VT2. Vs 1:2 transformer. Right? So the waveforms. Pi, 2 pi, 3 pi, right? Ig. As we know, when Vs is positive, thyristor T1 forward bias, na? Right? So here we can apply the gate pulse to thyristor T1 during omega t is equal to 0 to pi, and thyristor T2 during pi to 2 pi. Okay, so this is your Ig1. Red is Ig1. This is your Ig2. Ig2, right? So it is like alpha pi plus alpha 2 pi plus alpha and so on, right? B0
Yeah, hello, sir.
so
Sir, in the previous, you have drawn the current for secondary winding, sir, in the graph.
yes,
But in the input power factor, you have taken I0 RMS equal to I supply of RMS current. They would be I supply and I secondary winding current would be different, no, sir.
I supply and
I secondary winding current both are
Huh.
different, no.
you can check secondary current and secondary voltage and primary current and primary voltage, okay, for the transformer, right?
Okay, yes, sir. Yes, sir.
You will get an idea.
Yes, sir.
Right?
Both are equal, yes, sir.
Yeah, so that is the thing, na?
Yes, sir. Understood.
Yes, yes. Okay, so this is for highly inductive load. If the load is not highly inductive, what will happen? We'll discuss it after this circuit analysis. Okay, so yes, during let me write alpha to pi plus alpha, your T1 is in a conduction mode, pi plus alpha to 2 pi plus alpha, T2 will be in a conduction mode, right? So next, during this interval, V0 is equal to Vs only, I0 is a constant current, right? So single phase full wave control rectifier with REL load, as here we are having a full wave control rectifier, means corresponding to the positive half cycle, one thyristor will conduct, corresponding to the negative half cycle of the supply, the another thyristor will conduct. Okay, so due to that, here compared to the half wave control rectifier, the inductor is getting a lesser time to release the energy. So that's why in a full wave control rectifier, there is a high possibility or high probability to get a constant output current, or you can say the continuous output current. If you compare REL load in a single phase half wave control rectifier, right, and a REL load in a single phase full wave control rectifier, in the single phase half wave control rectifier, if you check, we had only one thyristor, okay, and that thyristor was triggering at omega t is equal to alpha, and the next instant was after 2 pi radian, right? Means if I apply the gate signal to the thyristor at alpha, then the next instant of triggering will be at 2 pi plus alpha. Okay, so there is a very a large gap, okay, between the two triggerings. But here if you check in this thyristor, in this circuit, at alpha we are firing the thyristor T1. Okay, so from alpha to pi, okay, from alpha to pi, or just before pi, means let us consider at theta. It is like our inductor go on storing the energy, and from theta till pi plus alpha, from theta till pi plus alpha only, inductor is required to release the energy, because after pi, at pi plus alpha again the next thyristor is turning on na, we are triggering the gate pulse, we are applying the gate signal to the thyristor T2 at pi plus alpha. So here as inductor is getting a very less time to release the energy, so that's why here the load current is a continuous one. If you compare the half wave control rectifier, right, in the RL load what we discussed, the inductor was storing the energy only from alpha to theta, but in a half wave control rectifier, yes, once thyristor T was triggered at alpha, the next triggering was at 2 pi plus alpha, yes or no? So whether the in order to get the continuous conduction in a half wave rectifier, half wave control rectifier, the thyristor was required to release the inductor was required to release the energy from theta till 2 pi plus alpha, and that is a very high time now. You can check, inductor was storing the energy only from alpha to theta, and if for the continuous conduction, for the continuous load current, yes, inductor was supposed to release the energy from theta to 2 pi plus alpha. So you can check, storing energy time is very less, and whereas theta to 2 pi plus alpha, that time is very high now. So that's why the conduction in the single phase half wave control rectifier, okay, is a discontinuous, but whereas in this case, yes, it is a continuous conduction. Why? Because alpha to theta, inductor stores the energy, and only from theta to pi plus alpha, inductor is required to release the energy, because at pi plus alpha again we are firing the next thyristor. Okay, so let us discuss what is the circuit operation, okay, for RL load. So here Vs we are having, it is a Vm into sine of omega t. So Vs is equal to Vm into sine of omega t. Vs is equal to Vm into sine of omega t. So Vs is positive, negative, positive, and negative, right? Next, so when 0 to pi, Vs is positive, it is like thyristor T1 forward bias mode. Pi to 2 pi, thyristor T2 forward bias mode. Same thing we already discussed. Okay, so that's why when Vs is positive, we applied the gate signal to thyristor T1. During negative half cycle of the supply, we applied the gate signal to thyristor T2. Similarly, thyristor T1, next thyristor T2, T1, T2. Alternately, we are going to apply the gate pulses to thyristors T1 and T2, right? Next, now let us discuss for omega t is equal to 0 to alpha, what will happen? For omega t is equal to 0 to alpha. Okay, so during 0 to alpha, okay, during 0 to alpha, yes, it is like before t is equal, suppose before t is equal to 0, circuit was at the rest position, okay, current was not flowing through the inductor, so inductor energy stored is equal to 0 before t is equal to 0, I am saying. Okay, so at omega t is equal to 0 till alpha, so omega t is equal to 0 till alpha means Vs is positive, so positive means plus here, minus here, here it is plus, here it is minus, plus minus plus minus, yes or no? T1 forward blocking mode, T2 reverse blocking mode. So let me draw during 0 to alpha, during omega t is equal to 0 to alpha, how will be the equivalent circuit? So for omega t is equal to 0 to alpha, yes, omega t is equal to 0 to alpha, we have not applied the gate signal. Okay, so I am drawing only secondary side circuit. Both the thyristors are in a off state. This is a R, this is a L. Thyristor T1, thyristor T2, plus minus VT1, plus minus VT2. Okay, so yes, supply voltage is positive, plus minus Vs, plus minus Vs. It is RL, this voltage is V0, right? And this current is I0. Okay, now yes, from omega t is equal to 0 to alpha, for very first cycle we are discussing what is the meaning of very first cycle, you will understand. Okay, so very first cycle means before that cycle of the supply, the circuit was at the rest position. Okay, so there was not yes, current was not flowing from source to the load, so that's why you can check very first cycle means for the very first cycle of the supply. Okay, means before that cycle inductor energy stored is equal to 0. Okay, so 0 to alpha, both the thyristors will be in off state, right? So it is like circuit will be like this, VT1, VT2, right? So both the thyristors are in off state. The meaning is current will not flow from source to the load. So in this case, your I0 is equal to 0 ampere. But if you check in the waveform, I have drawn it as a constant current. Why I have drawn constant current, I will tell you. Okay, so very first cycle I0 is equal to 0 ampere. Next, what is the V0 for very first cycle? It is a 0 volt. Very first cycle means, are you getting the point? The very first cycle means, suppose if I connected a switch here, and that switch we are going to close at t is equal to 0. So after closing the switch, what is the very first cycle that is coming? Okay, that is the coming out of the supply. That is nothing but your very first cycle. Okay, so for very first cycle means before that cycle, yes, it is like our circuit was not excited because switch was open. As circuit was not excited, therefore current flowing through the inductor will be 0, right? So as the current flowing through the inductor is 0, so during 0 to alpha, for very first cycle during 0 to alpha, there is a no point like a inductor releases the energy, because inductor has not stored energy now. So that's why there is a no point like inductor is releasing the energy. Okay, so that's why I'm using the word very first cycle. Please try to understand. Okay, and this circuit is valid only for very first cycle. For continuous cycle, how is the waveform? We'll discuss. Okay, so very first cycle. Okay, so now you can check during this interval 0 to alpha, both the thyristors are in a off state. Inductor has not stored energy prior, so that's why there is a no point like inductor is releasing the energy. Okay, so V0 0, I0 is equal to 0. Okay, what is VT1? Both the thyristors are in a off state now. Thyristor T1 is in a forward blocking mode, so can we write VT1 is equal to plus Vs? And what is VT2? Both the thyristors are in off state. Thyristor T2 is in a reverse bias mode, reverse blocking mode. So thyristor T2 is equal to minus Vs. So for very first cycle only, I0 and V0 both are 0. Okay, I0 and V0 both are 0. This rate is only for very first cycle I am saying. But for continuous cycle, if you check, whatever the waveform we are having from 2 pi to 2 pi plus alpha, na, the same we will be getting, yes, during 0 to alpha. I am saying for continuous cycle, the same waveform as that of the 2 pi to 2 pi plus alpha. But for very first cycle, it will be 0 only. V0 is 0, as well as your I0 is also 0. Red indicates the very first cycle. Let me indicate here. This is like a very first cycle. You can check. In India, we're having the supply frequency is 50 hertz. Okay, so supply is having the 50 cycles in 1 second. Okay, so can you imagine corresponding to the very first cycle, and the time corresponding to this 0 to alpha is very small now. 1 second 50 cycles, the meaning is time taken to complete one cycle. One cycle means it is like 0 to 2 pi, it is a one cycle. It is like 1 by 50, so it is a 20 millisecond time to complete this full cycle 0 to 2 pi. So 0 to alpha time will be very small. So you can check, if I even turn on the switch, and if you observe the V0 waveform and the I0 waveform on your CRO in your laboratory, you might be knowing the CRO. Okay, on the CRO, if you observe the waveform, you will not get this very first cycle waveform, because the time corresponding to very first cycle is very small now. And whether your CRO will show that 0 to alpha time period waveform, no, CRO will show the continuous only now, right? So that's why generally we are discussing only continuous cycle. But please try to understand, this is the very first cycle. What is happening in the very first cycle? Very first cycle means, again I am repeating, very first cycle means it is a first cycle, okay, of the supply after closing the switch. Okay, means suppose if I turn on the switch, okay, if I turn on the single phase AC supply switch, okay, then after that, what is the very first cycle that is coming out from the supply terminals? That is nothing but your very first cycle. So for very first cycle, V0 and I0 both are 0. Next, what will happen? Let us discuss. Okay, so from alpha to pi, at alpha we are applying the gate signal to thyristor T1. So definitely our thyristor T1 will turn on. Yes or no? Thyristor T2 will be in the off state. So from alpha to pi, thyristor T1 will be in the on state. Current is flowing like this now. Current will flow like this because Vs is positive, means plus here, minus here. Thyristor T1 is in on state. Current will be flowing into the upper loop. Okay. So from omega t is equal to alpha to pi. For omega t is equal to alpha to pi. Yes, thyristor T1 is turned on. So thyristor T1 is acting as a short circuit. Okay. This is a resistor R, inductor L, right? So strictly speaking, that should be alpha to theta, because inductor is storing the energy till alpha to theta only. Okay, right? So let me indicate it as alpha to theta. Theta we already discussed, okay, in a half wave control rectifier. Okay, so next, so this is a R here, L here. Okay, this is a V0, and here it is a I0. This is your VT1. This current is a IT1. This is IT2, and here it is a VT2, right? So this is like a plus here, minus here, Vs. This is like a plus here, minus here, Vs. Okay, so inductor go on storing the energy. Okay, alpha to theta, it is like inductor go on storing the energy. So inductor L stores energy. Inductor L stores energy. Thyristor T1 conduction mode. So what is the V0? You can apply KVL. V0 is equal to Vs. V0 is equal to Vs, right? So next, what is the I0? You can check I0 will increase slowly for very first cycle. For very first cycle, your I0 will be like this. It will be increasing slowly. Let me use the red one. It will be increasing slowly. This red one is for very first cycle only. But for continuous cycle, it will be like steady current. Okay. So for very first cycle, it will be increasing slowly. Next, V0 is equal to Vs from alpha till theta. Theta will be like your, yes, you can check the draw for the, you can draw the waveform of VR, and you can get the intersection point here. Okay. So from that you will understand this is like your theta. Okay. So till theta, V0 is equal to Vs, and I0 will be increasing slowly for very first cycle. Okay. But for continuous cycle, it will be steady value. It will be steady value. Next, after theta, what will happen? After theta, yes, after theta, or let me write VT1, VT2 also. VT1 is equal to 0 volt. VT2 is equal to minus 2 Vs. Na? One thyristor is in on state, one thyristor is in off state. Na? So the thyristor which is in off state, across the thyristor, the voltage will be 2 times Vs. Okay. So alpha to theta. Next, after theta till pi, what will happen? From theta to pi. For omega t is equal to theta to pi. Now inductor releases the energy. Supply voltage is positive only. Okay. So this is R. Here it is a L. Inductor will release the energy through thyristor T1. Supply voltage is positive only. Right. This is the VT1. This is like your VT2. Right, Vs, R, L, V0, and here it is a I0. So now inductor is releasing the energy. So inductor releases the energy through the thyristor T1, and Vs and inductor energy, okay, both will be what? Adding to each other, na? Both will be assisting. Okay, so you can check, means whatever we discussed in the single phase half wave rectifier, in the same way, right? In the same way, here inductor is go on releasing the energy. Inductor go on releasing the energy, right? So here inductor L releases energy, but inductor value is very high, na? Right? Inductor value is a high here. So that's why the current is a constant, na? That's why the current is a constant. Okay. So inductor value is high. So that's why opposition offered by the inductor to change in the current through it is a high opposition. So that's why we'll be getting the constant current. We'll be getting the constant current. So you can check from theta, right, till pi, we're getting the constant current. We're getting the constant current, right? Next, what about the V0 here during this interval? During this interval, if you check, V0 is equal to Vs only, na? Apply KVL and you can check. V0 is equal to Vs only. V0 is equal to Vs, right? Now here, what about the VT2? VT1 is 0. VT2 is 2 times Vs, na? It is a minus 2 times Vs. Okay, VT2 is a minus 2 times Vs. VT1 is a 0 volt. VT1 is equal to 0 volt. Okay. So what happened till now? Whatever we discussed, it is like a 0 to alpha for very first cycle, right? Circuit was at the rest position. Both the thyristors will be in off state. V0 0, I0 0. Alpha to theta, thyristor T1 is in a conduction mode. Inductor go on storing the energy. Okay. So for very first cycle, I0 was increasing slowly, right? Because before that it was 0 only, na? Right? So I0 was increasing slowly. Inductor was storing the energy. V0 was equal to Vs only. V0 is equal to Vs only. Vt2 is equal to minus 2 Vs. Okay. Theta 2 pi, what is happening? After theta, inductor go on releasing the energy. Okay. Right. And Vs energy and inductor energy, both will be adding here. Both will be adding because Vs polarity is like this only. Na? And when inductor releases the energy, right? VL will be your negative voltage. Okay. So that's why the same way will be getting. Right. So now Vt2 is minus 2 Vs, Vt1 is 0, and V0 is equal to Vs. So you can check from theta to pi. From theta to pi, V0 is same as of the supply voltage, I0 is a constant current. From pi to pi plus alpha, what will happen? From omega t is equal to pi plus alpha. For omega t is equal to pi plus alpha. For omega t is equal to pi plus alpha. Now supply voltage is negative. Yes or no? So supply voltage is negative. Supply voltage will try to circulate current in the anti-clockwise direction now. Yes or no? But whether our inductor will allow the sudden reversal of the current through it? No. So that's why inductor will go on releasing the energy in opposition to that of the supply voltage. It is like a minus here plus here. This is Vs minus plus. This is Vs. This is Vt1. Sorry, Vt2. This is a Vt1, right? So you can check here. Yes, at this instant, if we check current flowing through the inductor at pi, it is a non-zero current, na? Right? So I0, it is a positive current. So positive current means you can check. Yes, from theta to pi, current direction. Current flowing through the inductor is a positive, means current direction is right to left. Okay. So after pi, this supply voltage will try to circulate current in the anti-clockwise direction. But whether our inductor will allow the sudden reversal of current through it? No. So what is happening? Our inductor will continue go on releasing the energy in opposition to that of the supply voltage. Okay, inductor will continue releasing the energy in opposition to that of the supply voltage and through thyristor T1. Means even though after omega t is equal to pi, supply voltage is reversed, but inductor will continuously releasing the energy. So due to that, our thyristor T1 will be in a forward conduction mode only, because you can check near to the pi. What is the voltage across the, what is the value of supply voltage? It is a very small, na? You can check near to the pi. Supply voltage value is very small, and after that it is increasing, na? After that it is increasing, right? And still from pi till pi plus alpha, you can check pi to pi plus alpha is very small period, na? Right? So during that small period, yes, successfully our inductor will release the energy in opposition to that of the supply voltage. Okay. So inductor L releases energy. Inductor L releases energy here. Okay, releases energy. Now you can check thyristor T1 is again conduction mode. Thyristor T1 is in a conduction mode. So what is the V0? You can check or apply KVL. Minus Vs minus Vt1 minus V0 is equal to 0. But what is Vt1? Vt1 is 0 because thyristor T1 is in a conduction mode. So therefore V0 is equal to minus Vs. The meaning is load voltage is a negative. Load voltage is a negative. So you can check waveform from pi to pi plus alpha, your V0 is negative. V0 is a negative, right? Next, in the load variable, high inductor. So whether our inductor will allow the change in the current? No. So inductor will maintain the constant current. So that's why here, yes, that's why here we have shown the constant current I0 from pi to pi plus alpha also. Pi to pi plus alpha, right? So it is a constant current only. It is a constant current only. And what is the, yes, here inductor was releasing the energy. So pi to pi plus alpha, V0 will be your negative. Okay, V0 is a negative, right? Next, at pi plus alpha, what is happening? We are applying the gate pulse to thyristor T2 now. At pi plus alpha, we are applying the gate pulse to thyristor T2. So T2 will turn on. Once T2 turns on, yes, current will flow into this loop. Current will flow into this loop. Again, inductor go on storing the energy. Okay, so let me show. For omega t is equal to pi plus alpha. Yes, for omega t is equal to pi plus alpha. For pi to pi plus alpha. Yes, supply voltage is, sorry, pi plus alpha to 2 pi. Pi to pi plus alpha we already discussed, na? So pi plus alpha to 2 pi. supply voltage is negative only, right? Supply voltage is a negative. Thyristor T2 is turned on. Thyristor T1 is in an off state. So this voltage is minus plus Vs, minus plus Vs. Here we are having a R, here it is a L. This voltage is V0 and this current is a I0. Here it is a VT1 and this is a VT2. Okay, VT1 and VT2, right? So now you can check in this circuit. Once thyristor T2 turns on, current will flow into this loop. Na? So again, inductor will go on storing the energy. Inductor go on storing the energy. So inductor has released the energy only from theta till pi plus alpha. After pi plus alpha till 2 pi, again inductor is storing the energy. Okay, so inductor L stores energy. So here you can check when inductor L stores energy. Okay, that is when T2 is in an on state. So what is VT2? VT2 is equal to 0 volt, right? Next, what about the load voltage? You can apply KVL, minus V0 plus Vs. Minus V0 plus Vs is equal to 0. So what is V0? V0 is equal to Vs. V0 is a positive voltage. Even though your supply voltage is negative, but load voltage is a positive. V0 is equal to Vs. Okay. Load inductor will oppose the change in the current. So again, your I0 will be constant current. I0 will be a constant current. What about the VT1 here? VT1, one thyristor is on, second one is in off state. VT1 is minus 2 times Vs, na? Right? So it is a minus 2 times Vs. So you can check the waveform. V0 is a Vs. Okay. I0 is a constant current. So yes, V0 is Vs. Supply voltage is negative, but V0 is a positive. Okay, because V0 we are having the plus Vs here. Okay, so that's why the constant. Or you can check the I0 waveform. Direction of the I0, it is from right to left only, na? So I0 is positive, so your V0 is also positive. So that's why it is this type of waveform. Okay, so this is from pi plus alpha to 2 pi. Okay, next, and I0 is a constant current. After 2 pi, what will happen? After 2 pi, what will happen? So for omega t is equal to 2 pi to 2 pi plus alpha. Now you will understand in the continuous cycle and the very first cycle difference. Okay, 2 pi to 2 pi plus alpha. Okay, so supply voltage is positive here. So supply voltage is positive. So supply voltage will try to circulate current in the clockwise direction. Okay, so this is a R. This is a L, V0, and here it is a I0. This is plus minus Vs. This is plus minus Vs. Okay, so what is happening? This supply voltage, this is VT1. This supply voltage will try to circulate current in the clockwise direction. But if you check at 2 pi, current flowing through the load inductor, it was from right to left, na? So whether our inductor will allow the reversal of the current? No. So that's why whatever the energy stored by the inductor will release that energy through thyristor T2. Through thyristor T2, inductor will go on releasing the energy. Okay. So when inductor releases energy, VT2 will be 0. VT2 is equal to 0 volt. Okay. Inductor cannot release energy through T1 because we have not applied the gate signal to T1 yet. Okay. So that's why inductor will release the energy through thyristor T2. Next, VT2 is 0 volt. What about the V0? You can apply KVL, plus Vs plus V0 is equal to 0. So V0 is equal to minus Vs. So load voltage is a negative here. Load voltage is negative. Okay. So next, load inductor. So inductor is a high. So I0 will be your constant current. I0 is equal to constant current. So you can check 2 pi to 2 pi plus alpha. We are having the waveform. Yes. 2 pi plus alpha. V0 is a negative minus Vs. And I0 is a constant current. So my question is, for the continuous cycle, whatever the waveform we are in from 2 pi to 2 pi plus alpha, same will be repeating here, na? 0 to alpha. 2 pi means one complete cycle. So 2 pi to 2 pi plus alpha is like your 0 to alpha only. So for continuous cycle, this pulse, negative pulse will be appearing here 0 to alpha. And this constant current will be appearing as a constant here 0 to alpha. For very first cycle only, it will be 0. but for continuous cycle it will be like this only waveform will be getting. Okay, so please try to understand here. Inductor is storing the energy, and again it releases the energy for a short time actually. Okay, next the second thyristor turns on. Okay, so if you check the V0 waveform here, okay, V0 waveform in this case and the V0 waveform in a single phase half wave controlled rectifier, you are having the same type of waveform na. In the half wave controlled rectifier also, alpha to pi it is a positive and pi to pi plus alpha it was negative, or beta we had. Okay, we had that beta only na, instead of pi plus alpha we had in a half wave controlled rectifier that was beta. In a full wave controlled rectifier for continuous conduction, it is like beta means your pi plus alpha. Beta is equal to pi plus alpha. Okay, so that's why we're getting the continuous cycle. We're getting the continuous cycle. Now, whether your load current will be constant or not, whether your load current will be continuous or discontinuous, it depends on your load inductor value. If your load inductor is high, load inductor is high means what? L value is high. If L value is high means what? Inductor will store more energy. Na? It is half Li square. So inductor will store more energy. Inductor will store more energy means what? Yes, inductor will try to maintain the constant current by releasing the same energy. Okay, by releasing the same energy, because inductor opposes the change in the current. High value of inductor means high opposition to the change in the current. So we'll be getting the constant current. Most of the times they have asked the question like, in the booklet also we have given those questions. Okay, the questions like for a single phase full wave controlled rectifier, okay, with RL load, they will give you the value of resistor, and at the end they will give the statement like by considering the high value of the inductor. So high value of inductor means always keep it in mind. High value of inductor means always keep it in mind. I0 will be your constant. Okay, and your conduction is a continuous. Why I'm saying continuous conduction here? Because you can check alpha to pi plus alpha T1 is in on state, pi plus alpha to 2 pi plus alpha T2 is in on state. Means for all the time, your one switch will be in a conduction mode only, and your I0 will be non-zero for all the time. So that's why it is a continuous. I0 will be non-zero for all the time. So that's why it is a continuous one, right? Yes. Yes. Yes, do you have any question? Please ask. It's 8:40. Okay. So many hands are now raising. Okay. So we'll discuss. I will answer all your questions at the end. Okay. Because we have hardly 20 minutes, right? Let us finish the derivation here, right? Okay. Yes. So now V0 average. Come on, what is the V0 average? If you check the waveform, yes, V0 average. Whatever the waveform we're having from 0 to pi, same is repeating from pi to 2 pi, na? Yes or no? Right? So let me write it as a 1 by pi. Okay, let me write it as a 1 by pi. Now 1 by pi. Now instead of writing 0 to alpha and alpha to pi, I am writing it as a alpha to pi plus alpha. Please listen, this is important. Okay, you can check 0 to pi we are having pulse. The same pulse you can check, instead of 0 to pi I am considering it as a alpha to pi plus alpha. Why I am considering it as alpha to pi plus alpha? Because you can check alpha to pi plus alpha during this interval. Can I say V0 is same as that of the supply voltage? Yes or no? Right? So here let me write it as a alpha to pi plus alpha. V0 is same as that of the supply voltage, means Vm into sine of omega t into d omega t. Either I can write in this way, or second way is yes, you can check here. We're having the waveform here, right? Okay. Or how we can write 1 by pi integration from 0 to pi V0 into d omega t, but between 0 to pi we're having 0 to alpha and alpha to pi, na? 0 to alpha you can check supply voltage is positive, but our load voltage is negative. Means I need to write integration from 0 to alpha, it is a minus Vm sin omega t d omega t, plus integration from alpha to pi, same as that of the supply voltage, means Vm into sine of omega t. Means in this case, if I consider integration from 0 to pi, I need to simplify two integrals. Whereas instead of, in order to avoid that, what I am doing, I am simply writing alpha to pi plus alpha, because you can check na, 0 to pi means what? The time interval is pi minus 0 angle, that is a pi. Alpha to pi plus alpha also, where the angle is pi plus alpha minus alpha means again pi only na, right? So you can solve in both the ways, you will be getting the same answer. Are you getting the point? Either you can write integration from alpha to pi plus alpha, Vm sin omega t d omega t, or you can write integration from 0 to alpha. It is a expression of this waveform. It is a minus Vm sin omega t d omega t plus integration from alpha to pi Vm sin omega t d omega t. You can solve these two, you will be getting the same answer. Are you getting the point? Okay. So in order to avoid the solution of those two integrals, yes, I am writing it as a alpha to pi plus alpha only. Okay. Because alpha to pi plus alpha means again it is a pi radian na? And 0 to pi means again it is a pi radian only. Okay. So that's why here we are writing alpha to pi plus alpha. And you can check it is a 1 by pi. Pi plus alpha minus alpha means again it is a pi only na? So that's why this is a pi, right? So we can simplify it as Vm by pi into integration of sine is minus cos of omega t, limit alpha to pi plus alpha. So it is equal to 2 Vm by pi into cos alpha. This is a V0 average. V0 average is equal to 2 Vm by pi into cos alpha, right? So next, what is the I0 average? REL load we are having. What is the average voltage across inductor? It is a 0. Okay, so I0 average is equal to V0 average divided by R, right? V0 RMS is equal to 1 by pi integration from alpha to pi plus alpha Vm square into sine square of omega t into d omega t to the power 1 by 2. Okay. Yes, we can simplify it. It will be like a Vm upon root pi into integration from alpha to pi plus alpha. Sine square can be replaced with 1 minus cos of 2 omega t divided by 2 into d omega t to the power 1 by 2. Right? So it is equal to Vm upon root 2 pi into, let me write it as omega t minus sine of 2 omega t divided by 2, limit alpha to pi plus alpha to the power 1 by 2, right? To the power 1 by 2. Now we can put the limit. Okay. So it is equal to Vm by root 2 pi. It's a V0 RMS, right? Is equal to, okay, into, we can write it as pi plus alpha minus alpha. So it is a pi, right? Plus sine of 2 pi, 2 into pi plus alpha. Sine of 2 into pi plus alpha means what? Sine of 2 pi plus 2 alpha na? Sine of 2 pi plus 2 alpha means it is like sine of 2 alpha only. Yes or no, right? So sine of 2 alpha. Sine of 2 alpha divided by 2. Okay, minus, or let me write here minus for this term. And here it is plus, because we are having already minus here. Okay, so sine of 2 alpha by 2 plus sine of 2 alpha by 2 to the power 1 by 2. So you can check, this term will get cancelled. Root pi will get cancelled. So it is a Vm by root 2. What is the Vm by root 2? Vm by root 2 is nothing but RMS value of the supply voltage na? So it is like your Vs RMS. Means we are getting V0 RMS is equal to Vs RMS. Why we are getting V0 RMS is equal to Vs RMS? Yes, because you can check the V0 waveform. You can check the V0 waveform. It is a continuous waveform we are having. What is RMS? Square root of mean of squared value na? So if you take the square of this term 0 to alpha, negative na, square will be positive. Square of this term positive, square of this term positive, means between 0 to pi, if you take, the square will be like this. And if, what is the square of the supply voltage? It is again same na, positive. So supply of Vs, square of the Vs and square of V0, you can draw the waveform of Vs square and V0 square. You will be getting the same waveform, right? If V0 square and Vs square both are same, your average value of Vs square and average value of V0 square again same. So put it into square root, you'll be getting the same values. Okay, so that's what we're getting here. Yes, it is a V0 RMS is Vs RMS. Next, what is the conduction time of thyristor? Conduction time of each thyristor. Yes, thyristor T1 is in on state from alpha to pi plus alpha. Na? So it is like a pi plus alpha minus alpha divided by omega. So it is a pi by omega. Conduction time of each thyristor is equal to pi by omega. Next, what is the PIV rating of each thyristor? PIV rating of each thyristor. Yes. So for that, we need to draw the waveform. Okay. So actually it is a 2 Vm. I will draw the waveform. Okay. Yes. VT1 waveform we can draw. This is omega t, wherein the intervals like alpha, pi, pi plus alpha, yes, 2 pi, and so on. Okay. So how is the waveform of VT1? How will be the waveform of VT1? For continuous cycle, I am saying for continuous cycle. Yes, definitely from alpha to pi plus alpha, VT1 will be 0 because thyristor T1 is in a conduction mode. From pi plus alpha to 2 pi plus alpha, thyristor T2 is in a conduction mode now. So out of the two, one is in a conduction mode, one is in a off state. So voltage will be 2 times now. So we'll be getting this type of waveform. Right? So same 2 pi to 2 pi plus alpha will be repeated here during 0 to alpha also. 2 pi plus alpha. This is your 2 times Vs, negative here, and this is your positive. Vs is positive. Right? So what is the PIV rating here? PIV rating is equal to 2 times Vmax. 2 times or minus 2 Vmax. So PIV is 2 Vmax, right? So PIV is 2 Vmax. Next, what is the circuit turn up time? TC for each thyristor. Yes, TC for each thyristor. Current flowing through thyristor T1 becomes 0 at pi plus alpha, na? And after that the reverse voltage is maintained till 2 pi only. So what is the circuit turn-off time? 2 pi minus in bracket pi plus alpha, okay, divided by omega. So it is a 2 pi minus in bracket pi plus alpha divided by omega. So it is 2 pi minus pi. So pi minus alpha divided by omega. This is circuit turn-off time for thyristor. Now, can we draw the waveform for thyristor current and a source current? Yes. Thyristor current and source current waveform. We are having I0 waveform. Let me draw first I0 waveform. This is a constant. We are having intervals like alpha, pi, pi plus alpha, and it is 2 pi. Na? So how is the waveform of IT1? Yes, IT1, thyristor T1 is in a conduction mode. From alpha to pi plus alpha. Na? So from alpha to pi plus alpha, what is the IT1? Same as that of the load current. Na? So IT1 waveform will be like this. Always keep it in mind. Our thyristors, our switches allows current in only positive, only one day, only forward direction, na? Right? So IT1 from alpha to pi plus alpha, thyristor T1 is in a conduction mode. So that's why your load current will be same as that of your IT1 during this interval, right? Next till 2 pi it will be 0, and here it is also 0, right? What about the IS? Come on, IS. You can check alpha to pi plus alpha. From alpha to pi plus alpha, thyristor T1 is in a conduction mode, na? pi plus alpha to 2 pi plus alpha. Okay, so I'm writing instead of 2 to 2 pi to 2 pi plus alpha, I'm considering it as 0 to alpha actually. Okay, so let me write it as T2 is in a conduction mode now, right? So what is the IS now? When thyristor T1 is in a conduction mode, IS is positive or negative? Come on. When thyristor T1 is in a conduction mode, IS will be positive or negative. That is current flowing through second winding of the transformer will be in upward direction or downward direction. If it is upward direction, it will be positive. If it is in downward direction, it will be negative. Yes, come on. Positive, na? Yes, upward direction means it is a positive, right? So positive current means when T1 is in a conduction mode, your IS is positive. When T2 is in a conduction mode, you can check when T2 is in a conduction mode, the current in the second winding of the transformer is in downward direction. The meaning is your supply current is a negative, na? Right? Reverse. So how is the waveform of IS? It is like this. Okay, for continuous cycle, it will be like this till 2 pi to 2 pi plus alpha. And here also, whatever the waveform we are in 2 pi to 2 pi plus alpha, the same will be repeated here. Yes. This magnitude is a capital I0. This magnitude is a minus I0. Okay. So you can check supply current is your DC. But what about the, sorry, supply current is a AC, positive, negative, right? It is a square wave. They have asked the question in a single phase full wave control rectifier for a highly inductive load, what is the nature of the supply current? It is a square wave. It is a square wave. Are you getting the point? What is the nature of the load current? It is a constant, a flat DC, but it is a square wave here, right? Now, yes, this is like alpha here, right? This is like alpha here. Alpha, this is a pi. This is a pi plus alpha, right? So, yes. So now, what is the I0 RMS we have written? I0 RMS. Now, yes, in this case, what is I0 RMS? By observing the waveform of I0, can we write I0 RMS? Yes, if you understand the meaning of RMS, root means square, then definitely by observing the I0 waveform, you will understand what is the I0 RMS. Come on. What is I0 RMS? Square root of mean of squared value. Video uploading is not okay. Means they have not given the right to the faculty to upload the video. Okay, I can upload the notes immediately, right? For the video, you can contact the office, right? Yes. The power electronics is quite high. Tough. Yeah, power electronics is a tough. I know because it requires a very what I can say, good command on the network specifically, because power electronics is like only your transient and network. That's it, not more than that. Okay, so yes, you can check I0 RMS. I0 RMS means what? Square root of mean of squared value, na? So you can check if I do the square of this I0 square, what is the square will be? Capital I0 square. What is the average of that capital I0 square? It is a capital I0 square only. If I put it into the square root, under root I0 square, so it is I0 only, na? Right? So always keep it in mind. If you are having this type of waveform, I0 RMS, I0 average, both are same only. Are you getting the point? Right? Otherwise, you can simplify it. How to simplify? From omega, yes, omega t is equal to 1 by pi integration from alpha to pi plus alpha. Put it as I0 square into d omega t, d to the power 1 by 2. You will be getting it as I0 only. Okay, so yes, so let me write it as I0 RMS is equal to I0 average is equal to capital I0. If the waveform is DC, then average value and RMS value both are same only. Both are same only, right? After the class, yes, after this session, please simplify this and find the value of I0 RMS. Also find the value of I0 average. You will understand why both are same here. Are you getting the point, right? So because constant waveform, na? So RMS average both will be same. Next, what about the IT1 average here? IT1 average, IT1 RMS. Can we write IT1 average, IT1 RMS? Yes, IT1 average. So now by observing the IT1 waveform also we can write, you can check alpha pi plus alpha and it is 2 pi. Over 0 to 2 pi, we are having only alpha to pi plus alpha, that is 50% non-zero value. And for remaining 50% it is zero value. So what is the average value? It is I0 by 2 na? Suppose we are having a 10 numbers. In that first 5 numbers are same, 5, 5, 5, 5, 5, let us consider. And next 5 numbers are 0. So what is the average value? 5 by 2 na? In the same way, this is I0, here it is 0, here it is 0. So what is the IT1 average? It is a I0 by 2. Or you can simplify it like 1 by 2 pi integration from alpha to pi plus alpha. It is a I0 into d omega t. Okay, you can simplify it, you will be getting it as a I0 by 2 only. Right, this is IT1 average. Next, what is the IT1 RMS? IT1 RMS. Yes, RMS value of thyristor current. Yes, 1 by 2 pi integration from alpha to pi plus alpha, I0 square into d omega t. Okay, so 1 by 2 pi integration from alpha to pi plus alpha, I0 square into d omega t to the power 1 by 2 na. So square root of mean of squared value. So it is like a I0 upon root 2 pi into what? You can check omega t and put the limit pi plus alpha minus alpha. So it is a pi to the power 1 by 2. So root pi cancel out is equal to I0 by root 2. This is IT1 RMS. Right? I am writing the expression and simplifying it. That's it. Next, what about the IS RMS? Yes, can anyone IS RMS? Square of this will be I0 square, square of this I0 square, square of this I0 square. Okay, so RMS value will be I0 only, right? IS RMS is equal to capital I0. IS RMS is equal to capital I0, right? Or you can write, yes, if you want, you can write it as 1 by 2 pi integration from alpha to pi plus alpha, I0 square d omega t plus pi plus alpha to 2 pi plus alpha minus I0 square into d omega t, right? You will be getting the same answer. Okay, so it is IS RMS is equal to I0. Is this clear? So keep it in mind. If we are having a constant current, if we are having a highly inductive load, then RMS value of the load current is equal to average value of the load current. Okay, how to find the average value of the load current? Because some of the examples they directly don't give the capital I0 value. So in that case, we need to find I0 average. What is the I0 average? It is a V0 average by R. Now we have written I0 average is equal to V0 average by R. And that I0 average is again we have equated to capital I0, right? So this is about a single phase full wave control rectifier with a REL load, okay, and a highly inductive load, okay, in a highly inductive load, right? So if the load is having some lesser value of inductance, okay, then what will happen? Let me show you with the load current waveform, okay, and the load voltage waveform. So, case 2. If load current is discontinuous, load current is discontinuous. The meaning is load inductor L, okay, is not high. L is not high. Whatever we discussed just now, it was for high value of inductor. Now it is a low value of inductor. Okay, so the waveform will be like this. Let me draw it as a V0. Here the word important is discontinuous. Yes. Alpha, pi, pi plus alpha, 2 pi, 2 pi plus alpha, right? So V0 waveform will be like this. alpha to theta, inductor stores energy. After theta, inductor releases the energy till pi, and after pi till beta only inductor releases the energy. So you'll be getting this type of waveform. This is like your beta now. This is equal to Vs, and I0 waveform will be like this. It will be increasing till theta. After that, it will be decreasing till beta. Again, beach mein 0, right? Next, increases till theta. After that, increases till this pi plus beta. And again 0. This type of waveform will be getting. You can check, you can compare this waveform of V0, I0 with whatever just now we discussed. Just now, whatever we discussed, in that case, it was like a inductor was releasing the energy till pi plus alpha. Na? Now, in this case, what is happening? We have reduced the value of inductor. So, due to that, what is happening? Our inductor is releasing the energy till beta only. And from beta till pi plus alpha means none of the thyristor will be in a conduction mode. So that's why current will not flow from source towards the load, right? So your load voltage will be 0. Load current is also 0. Why it is a discontinuous? Because your load current is a discontinuous. So that's why it is a discontinuous. Just now, whatever we discussed before this, it was a continuous conduction, means your load current was constant. Is this clear? So at that time also, I commented one thing, that is, if beta is equal to pi plus alpha, you will be getting the continuous conduction. Are you getting the point? Okay, so let me write. For discontinuous conduction, beta is less than pi plus alpha, right? For continuous conduction, beta equal to pi plus alpha. For continuous conduction, beta equal to pi plus alpha, right? Beta is equal to pi plus alpha. Okay, in some of the cases, right? Suppose where just now I have discussed two cases. One is a beta is very high, second one is a beta is low. Okay, so suppose we are having a where in one case we discussed the L value is very high, and in this case we consider that the L value is very less. Okay, so that we are getting the discontinuous conduction. Okay, L is not high, that is L is low. Now suppose if we are having a L value in between the two, means L value is neither that very high or nor this, it is a very less. Okay, so let us consider the moderate value of L. What will happen? Okay, so moderate value of L. Moderate L. So it is like we'll be getting the continuous conduction only, but continuous conduction only, right? But here your load current is not a flat DC. Okay, it is like this: V0, I0. So it is alpha pi plus alpha, 2 pi plus alpha, and so on. So if L value we have increased, okay, compared to that of your discontinuous conduction, right? So waveform will be like this. V0 waveform will be same as that of your continuous conduction only. This is also continuous conduction only, but the thing is here your I0 is not a constant. I0 is not a constant. It means I0 will be like this. It is a decreasing from this instant, again it is increasing, okay, till theta, and again it is a decreasing, again increasing, again decreasing, again increasing. Okay, so we'll be getting this type of I0. Now you can compare this I0, right? Whether it is a continuous or discontinuous, it is a continuous only, because you can check I0 value is always non-zero. But whereas if you check this one, In this case, I0 is having, yes, in between 0 intervals, na? So it is a discontinuous. And whatever we discussed in this case, that is during the waveforms, yes, it is a flat DC. So this is for very high value of inductor, right? This one is for, yes, moderate value of inductor. And here, this one is for low value of inductor. Is this clear? Okay. So for low value of inductor, beta is less than pi plus alpha. For high value of inductor as well as your moderate value of inductor, beta is equal to pi plus alpha only. Beta equal to pi plus alpha means inductor will go on releasing the energy till we fire the next thyristor. Till we fire the next thyristor. Is this clear? Right? So this is the actual difference between continuous conduction and discontinuous conduction and high value of the inductor. Okay, right. So stop here. If you are having any doubts, please ask.
Hello, sir.
Yes.
39th slide, sir. Same question that.
Okay. Let me allow the others also. Just a minute. Slide number
39, sir.
39. Yes.
Same one, sir. The secondary winding current and the source current. How did they become equal? I didn't know.
I0 RMS and IS RMS, how they become equal?
Yes, sir.
Yes, sir.
Same doubts are here.
Okay. We have drawn the waveform, na? Yes, here
Yes,
you can
sir.
check.
This is 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 secondary winding current, no, sir.
Yes.
So how IS and ISO source current are equal? Source current will be double the value of secondary winding current, no, sir.
Otherwise, sir, it means source voltage is Vs now. So
Source
current will
voltage
be Vs for supply primary side, sir.
Source voltage primary side is Vs. Yes.
Yes. Then current will be double because 1:2 turn ratio. So in the primary side, the current will be double.
2 times IS. Yes.
Then in the denominator, we should write Vs into 2 times of IRMS, ISRMS.
Just a minute. Here you are saying.
Yes, sir. Because you have written VSRMS directly, ISRMS and I0RMS cancels, but in the denominator, 2 times of a VSRMS,
Let me clear. Okay. So if you check here, the secondary voltage is Vs. V0 RMS, na?
Yes, sir.
At upper half part we are getting Vs, lower half part we are getting Vs, right?
Yes.
So here what we are doing, we are considering this IS RMS means secondary winding current, not your primary winding current.
Okay.
Are you getting the point? Because anyways it is current which is flowing in the transformer winding, na?
Yes, sir.
So we are considering it as a secondary winding current, IS RMS. And
But okay.
yes.
But in a transformer, if we are dealing with a KVA rating, means it is the total voltage and the current.
It is nothing but
the KVA rating is the total, means 2 Vs into that source current RMS. The KVA rating will be.
Okay.
We are writing like this. Here
so
also
you can check the secondary winding KVA rating and the primary winding KVA rating of the transformer. Whether both will be same or different in our case.
In our case, it will be for a transformer always it will be equal.
In our case.
In our case, this is IS.
Secondary winding voltage is 2 Vs. And
yes,
secondary
sir.
side current is like your IS RMS, this one.
And
primary side you are saying voltage is Vs. And primary side current is 2 into IS RMS.
Yes.
So both the sides volt ampere ratings are same, na?
Same. Here but if that thing will be calculated in the secondary winding, how we will calculate? This is the primary side, okay. That same KVA rating, if we will calculate in the secondary winding, how? Means it should be equal, na? KVA rating, both the primary and secondary for a transformer.
No. But you think here VS RMS, IS RMS we are having. Okay.
Yes.
Okay, this is like your secondary winding current.
Yes.
Your doubt is regarding, suppose if I replace this VSRMS into ISRMS with a primary volt ampere, na, you are saying? Yes or no?
Yes, sir.
So primary side your voltage is VSRMS. Primary side current is ISRMS.
Okay. Because in the
Because
okay.
yes or no?
Yes.
Because you are saying VSRMS, both the sides volt ampere are same.
Okay.
So both
Okay.
are same we are getting. Okay, doesn't matter actually. It because the thing is, in the case of transformer, if the voltage is step up, it is like current is step down. So that's why the product will be same.
Actually, sir, I am continuously means done wrong with one calculation, that is transformer utilization factor.
Okay.
Means that also that concept is also valid there, na?
Transformer utilization factor. Okay. Okay. Means in this case, it is like 50% utilization we are having.
Means here also we are dealing with the KVA ratings.
Yes, we are dealing with the volt ampere rating.
Volt ampere rating. Then, sir, here actually KVA for both primary and secondary always equal, na, valid. It will be in power electronics. It may be in the machine.
Yes.
Then here also it is valid because
It is also
VSRMS.
valid, right? The thing is, what is happening in the, if you check the upper part of the secondary winding of the transformer,
Yes.
if you want to find the VA rating of that part, only upper part I am saying. Definitely your voltage is non-zero for all the time for upper part.
Yes.
And what about the current? Whether the current will be non-zero for upper part all the time? No. Current will be non-zero only from alpha to pi plus alpha, na?
Pi plus. Okay.
So it will be 1/2 actually there, right? And that 1/2 into that VSRMS into your IS something. Okay. And
Means
plus the lower part.
Means in the secondary winding, if we will calculate then individually, then 2 times will be multiplied for part.
What?
If the secondary winding for the upper part, if we will deal with VSRMS into that current, means for alpha to pi plus alpha.
Yes.
That is something by 2 coming, means I0 by root 2. I0 by 2. And
that is like your IT1 RMS, na?
But for the lower part, again it will be same, and it will be double.
Yeah. That VA rating into 2.
Okay.
That is
Then also it.
That is nothing but this one, na? VSRMS into ISRMS.
2 times. Okay.
Right?
Then some answer will come. Okay.
Yes, same answer. They will not change, right?
Thank you, sir.
Sir, in circuit, please once explain the turn off.
Hello.
Which?
The circuit turn off time, sir.
For this circuit?
Yes, sir.
Circuit turn off time. Just a minute. We have written, na?
Yes, sir.
Okay. Here it is, right? So TC for each thyristor means either you can find for T1 or you can find for T2. Okay. So current flowing through thyristor T1 becomes 0 at which instant? At pi plus alpha. Yes or no?
Yes, sir.
And after that, the reverse voltage will be maintained till 2 pi, na?
Yes, sir.
So what is the circuit turn off time? 2 pi minus pi plus alpha divided by omega.
Yes, sir.
Right?
Okay.
Is this clear?
Okay, sir. Yes, sir.
Okay.
Sir, but
Yes, please.
I would conduct only from alpha to pi plus alpha, sir.
What? Please repeat.
Thyristor conducts from alpha to pi plus alpha, na, sir.
So
remaining time completely off, na, sir. That's like that we don't consider, sir.
remaining time means
Means
that remaining time is nothing but your pi plus alpha. No, it is
alpha,
not like that.
pi
We
plus
need to consider
alpha.
only reverse voltage.
only reverse voltage we want to consider, sir.
Yes, we need to. Yeah, whatever till now, whatever the circuits we discussed, in those circuits also we calculated the circuit turn off time in the same way, na?
Sir, only
The
reverse
circuit
voltage
turn
at
off time is related to your dynamic characteristics of the device.
Okay, sir.
During turn off, there we are having the concept like TC na, chapter number 1.
Yes, sir.
Yes, so there actually we maintain the reverse voltage na, so that's why we need to consider only reverse voltage part, right?
Okay, sir. Okay, sir. Understand. Thank you, sir.
Okay.
Sir, in 12F, sir. 12F.
Yes, sir.
Hello,
Yes,
sir. 12F, sir. 1, 2, 12F.
12F. Okay. Yes.
Sir, previous page, I think so, sir. For RLE load, we have find I naught average, no, sir.
This previous page.
No, I
not
didn't
average.
note.
I not average.
Yes, sir. Sir, is this valid for RE load also, sir?
For RE load also. Yes, it is valid for RE load also.
Sir, another doubt I have, sir. You said if inductance, if load is highly inductive, means it is continuous, sir, and it will be current will be constant, sir. But if it is highly inductive, means it will take more time to release the energy, no, sir. Then how it will be continuous, sir? It will be excess than pi plus alpha, no, sir.
No.
It will be.
It is not like that. Think in a steady state operation. In a steady state operation, what is happening?
Okay, sir.
Over a one cycle, that is from alpha to theta, it is like inductor storing the energy.
Yes,
And
sir.
from theta to pi plus alpha, inductor is releasing the energy again. So in a
Okay,
steady
sir.
state operation, if you check in a steady state operation, it is like a inductor is storing the energy, and same energy the inductor is releasing actually.
That means we are having two thyristor. So the triggering angle is minimum. So that we are giving the triggering back to back. So storing time of the energy stored by inductor time is very less. So releasing time also very less. So it's becoming continuous. Am I right, sir?
Yes.
Sir, but how the current become constant by high inductive load, sir?
No.
Voltage, I understand.
No, you can check. In network, we are having the concept like constant current source.
Yes, sir.
We are having a voltage source, current source. Suppose I am having a one circuit, right? And across a 5 ohm resistor, if I connect a current source, what that current source indicates? That current source is nothing but your constant current source.
Yes, sir.
And how we manufacture that constant current source? Your constant current sources are generally manufactured with the help of high inductor only. Always keep it in mind, if value of inductor is high, definitely current flows to the inductor. Hello?
Okay, sir. Okay, sir.
Right?
Yeah, yes, sir. Yes, sir. Thank you, sir.
In power electronics, we are when they mention that highly inductive load, we need to consider the constant current only, because think about the tendency of the inductor. Inductor opposes the change in the current, na?
Yes,
So
sir.
higher the value of inductor means what? Higher the opposition.
Yes, sir.
Higher opposition means the change in the current will be 0.
Okay, sir.
So that is like current change in the current is 0 means what? It is like a constant current.
Okay, sir.
Right? Okay.
Thank you, sir.
Yeah.
Hello, sir.
sir.
Yes, please.
Sir, full wave control rectifier with RL load waveform, sir.
Full wave controlled rectifier with RL load, na?
Yes, sir.
Just a minute. Do you know slide number?
No, sir. Slide number.
Just now it is. Yes, RL, na? Okay.
Yes, sir. RL load.
Yes.
Sir, in this, sir, the VO value from 0 to alpha, sir, why we taken it negative, sir?
During 0 to alpha, why were taken negative? This one,
Yes. Yes, sir.
because in a continuous cycle,
Yes.
whatever the waveform we are having from 2 pi to 2 pi plus alpha, na?
Yes, sir.
The same will be getting here 0 to alpha.
Sir, but initially our inductor is we have considered in discharge.
Initially it is a 0. Initially
Zero,
it is a 0. Initially means very first cycle I am saying.
Yes, sir. Yes, sir. Very first.
Continuous cycle it will be like this, and generally very first cycle means what? It will occur for only one time, na?
Yes, sir. Operate on.
So that's why generally we are neglecting this one. We were concentrating on continuous cycle only.
Okay, okay, sir.
And from 2 pi plus alpha, it is negative. So that's why it is negative here, right?
Okay. Okay, sir. And sir, one more doubt.
Yes.
Sir, if you have the very high value of inductor, so that before releasing the complete energy of inductor, we have given the gate pulse to the next thyristor in the negative half cycle. Then what will happen, sir?
Nothing will happen, because the thing is, in a steady state operation, for
Yes.
very first cycle, if you check, for very first cycle, we'll check, it is like a suppose, let me show you. Yes. Just a minute. Yes, let me show you here. Okay.
Yes.
Suppose I am having a circuit like this, same circuit. Suppose we are having a highly inductive load, right?
Yes, sir.
Suppose I am turning on. Initially, the current will be like this. Suppose the we applied the alpha equal to 0. We maintained alpha equal to 0. So initially, your current flowing through the inductor, let me write it as a IL. It will start increasing slowly. Okay.
Yes, sir.
And suppose at this instant, till this instant, it is like inductor has stored the energy, right?
Yes.
And suppose after that, the next half cycle will start, okay, of the supply. And again, we are turning on this thyristor, or before turning on this thyristor, it is like inductor will release the energy. So it will be like this.
Yes.
And suppose if according to whatever you are saying, inductor has stored the energy like this, from here to here, inductor has stored the energy. Means
Yes.
currently inductor energy is proportional to this current.
Yes.
But suppose inductor is not getting the time to release the that much energy, so it will decrease to till this instant. Further, suppose if again I turn on the thyristor, then again inductor will go on storing the energy. Then again, suppose it is decreasing, again it go on storing the energy, again it is decreasing. If inductor is not getting the sufficient time now, then we will be getting this type of waveform actually.
Okay, sir.
But at steady state, actually the thing is, I am firing this as at alpha, and I am firing this at pi plus alpha na.
Yes, sir.
So you can check what I told, pi to alpha to theta, inductor stores energy,
Yes, sir.
and from theta to pi plus alpha, it is like inductor releases energy na.
Yes, sir.
So whether inductor is getting the same time, same angle here corresponding for all the intervals, yes. You can check now, when T1 is in the on state, it is like alpha to theta, inductor stores energy. And next theta to pi plus alpha means whatever the angle here and whatever the angle here, the same angle is repeating now for all intervals.
Yes, sir. For all
So
intervals.
that's why we're getting the steady state operation. But here, if you check in this case, if you, yes, suppose if we are varying the value of alpha and
Yes.
we are not giving the sufficient time for the inductor to release the energy, then we'll be getting this type of waveform. This is not the steady state, right?
Sir, but there is
Huh.
any concept of saturation of inductor. Then, if continuously it is storing energy, then one time it will come, then it will completely charge.
Yes, it will be fully charged.
Yes, sir.
But this is not happening in our case,
Okay.
because you can check for storing the energy, we are giving the time from alpha to theta na.
Yes, sir.
Again, you can check this is for, when T1 is in on state na.
Yes, sir.
Suppose when T2 is in on state, then what is happening in the circuit? From pi plus alpha to, it is like a pi plus theta. Inductor stores energy.
Yes, sir.
Yes or no?
Yes,
So you
sir.
can check storing time alpha to theta and this pi plus alpha to pi plus theta, whether both are same or different. Both are same.
Yes, sir.
Similarly, what will happen? Pi plus theta to 2 pi plus alpha. Further, inductor will release the energy again.
Yes.
So you can check this time and this time, whether both are same or different. Both are same.
Both are same, sir.
So in steady state, we are having the waveform like inductor stores energy, releases energy. So in the steady state, both are same. Storing energy is equal to releasing energy. Because these intervals are same. This interval is equal to this interval. This interval is equal to this interval.
Okay, sir.
But
Sir,
if you will not give these two intervals as the same na, then
Yes.
you will be getting the waveform like a unstable or steady state will not reach, right?
that means we are discussing all the circuits in a steady state analysis.
Yes. Only steady state, because in power electronics, what is happening? if I turn on the, if I apply, maintain the get pulse at alpha na for thyristor T1, then
Yes.
we need to maintain the, apply the get pulse to thyristor T2 at pi plus alpha only. Then and only then we'll be getting the balanced waveform na,
Yes, sir.
right? Symmetrical waveform will be getting then and only then. Otherwise, suppose if we are firing thyristor T1 at alpha by keeping alpha 30 degree and to thyristor T2 by keeping alpha equal to 60 degree, whether we will be getting the symmetrical waveform? No. And that waveform, suppose if that whatever the output power of, whatever the output of that rectifier, if I give to the load na,
Yes.
what will happen to the load performance? Your load performance will degrade. So that's why we need to give the symmetrical only, right?
Yes, sir. Sir, one more doubt in a waveform
Yes.
of RL loads.
Waveform of RL load, no?
Yes, sir. Previous.
Just a minute. Yes.
Sir, you are told about the when we see the waveform at CRO, then it
Yes.
will show a continuous waveform of
Yes.
wave. Then, sir, how we will identify that the inductor is giving continuous and discontinuous waveform if the instant 0 to alpha is giving means showing the same waveform in both cases?
No. If you get the waveform like this,
Yes, sir.
negative, positive, negative, positive, na? This
Yes.
zero is your continuous one,
Yes, sir.
and I0 is also continuous.
Yes.
Then you can say that your inductor is what I can say, the conduction is continuous.
Yes, sir. Continuous conduction, but sir, in case of I0 also, sir, the current is completely continuous in waveform at CRO. Then how we will identify it? It is in either continuous or in discontinuous mode of operation. Means our inductor.
Will you please repeat? Will you please repeat?
Sir, if our I0 waveform is continuous,
Ah.
showing CRO is showing continuous,
Hmm.
then sir, how can we identify that our load is a continuous means our waveform is continuous or discontinuous? If it's continuously showing if it's continuously showing the continuous waveform.
Though your I0 is continuous in nothing but the continuous operation, na?
Yes, sir, continuous operation, but in a discontinuous, if my inductor value is less, and then from 0 to alpha instant the I0 waveform you again zero, sir.
Just a minute.
Yes,
If your inductor value is less, na,
yes, sir.
then you will be getting this type of waveform. There I shown you. This type of waveform,
Okay, sir.
whether it is a continuous or discontinuous.
Then discontinuous, sir.
Now you can compare this V0 with whatever we discussed in the previous case. This I0 with the previous case, you will yes, you will get an idea whether it is a continuous or discontinuous.
Sir, but in a moderate case, sir, in third one we have discussed, you are told about
In-
sir, in case
In
3,
which case?
sir, case 3, first case and
This
third
one.
case, sir.
This one.
Yes,
This one. Yes. In this,
yes, sir. So, sir, the current is here also continuous and there also continuous.
yes, here your mode of operation is a continuous only.
Yes, sir.
It is not a discontinuous, it is a continuous only. But the thing is, here the value of inductor is lesser compared to that of your first case.
Okay, sir. Okay, sir.
It is a continuous only,
Okay, sir.
right? If
Sir,
you observe this type of waveform on a CRO for current,
Yes.
by observing the V0 waveform, you cannot tell.
yes, sir. I am asking about visual waveform.
Okay, by observing the V0 waveform, you cannot even comment whether it is a for a high value of or low value of inductor. But it doesn't matter whether it is a high value of low value of inductor, because the thing is both are continuous. Case 1 and case 3 both are continuous.
Both are continuous. Yes.
Yes, both are continuous.
Sir, means by identifying the waveform I0, we can determine. whether
Yeah,
the-
by observing, the identifying the waveform of yes, we can determine, right?
Okay, sir. Okay. Thank you, sir.
Okay.
Hello, sir.
Hello, sir.
Sir,
Yes,
in-
please.
Full wave RL load, sir.
Full wave RL load. Yes. 40. Yes, here it is, I think.
46, I think, sir.
REL, na? 46. Huh.
Can you once
Right?
explain that I naught waveform, sir?
Which waveform?
I naught, sir.
I not waveform. Okay. I not waveform for a continuous cycle. It
Yes,
is a
sir.
constant only because of the inductor. If value of inductor is high, we'll be getting this type of waveform,
Oh.
right? The thing is, what is happening in the circuit from alpha to theta. Theta actually I have not indicated here because the same thing we already discussed, na?
Yes, sir.
Right? So till theta inductor stores energy. After theta till pi plus alpha inductor releases the energy. So when inductor stores energy and releases energy, at that time we are having a constant current only. Why? Because here value of inductor is very high. But if you reduce the value of inductor, we'll be getting this type of waveform, whatever we discussed in the case 2 and case 3, na?
Yes, sir. Yes, sir. Low value and medium.
Yes. This is for high value. Just a minute. Yes, here it is. This is for somewhat less value. If we
Moderate.
further reduce the value, okay, of inductor, then we'll be getting this type of waveform. Because
Yes, sir.
more the value of inductor, it is like a more will be the time taken by the inductor to release the energy, because more will be the energy stored by the inductor. Okay.
Yes, sir. Thank you, sir.
Right. Okay. Yes, please. Yes.
Sir, after observing the graph, we can say that it is continuous or discontinuous, sir.
Which graph?
You said that here it is continuous, so that the first cycle we have considered here, no, sir. In RL load.
This is case 2 you are saying?
No, sir. Case 1, 41F.
41. Yeah. Okay. In this.
How you are saying that is continuous waveform, sir? By observing V naught only, no, sir?
No. By observing V naught and I naught, we can say it is a continuous. Continuous meaning is, please try to understand. Continuous means if your load current is not having the zero interval, na?
Yes, sir.
Then it is a continuous.
Okay. Sir,
You can
first
check here.
cycle.
Yeah. No. First cycle it is like a transient, na? It is for very short time, and it will occur only for the first time. But if you check for repetition for the continuous operation, whether we'll be getting this first cycle again? No, na?
No, sir.
This I have told you only for understanding purpose, because for very first cycle it will be like this. But for continuous cycle means what? After 2 pi you can check again, after 2 pi to 2 pi plus alpha, during this interval we are having negative pulse. So the same pulse you will be observing here, na?
Okay, sir. We will consider this first cycle only for continuous, sir.
Consider first cycle only for
Continuous.
no. First cycle is only for very short time period. So we have started operation. I have explained operation from very first cycle. But you can check for the second cycle of the supply, for third cycle of the supply, whether you will observe this waveform.
No,
Zero.
sir.
No, na. So that's why what simply it is neglected.
Okay.
Are you getting the point?
Yes, sir.
Right. So this is only for understanding purpose we discussed, and we have started with the very first cycle. You cannot get this waveform in any of the book, right? They have directly explained about the steady state operation. Steady state means this operation.
Yes.
But for very first cycle you will be getting, definitely this will be zero. Very first cycle I am saying. But that very first will occur only one time, na?
Yes, sir.
So that's why it is generally neglected, right?
Okay, sir.
Now simply you can observe this waveform here, and you can check or you can tell whether it is a continuous or discontinuous. It is a continuous only, na?
Yes, sir.
Right? Okay. Either you can, by observing the waveform of I0 or by observing the waveform of V0, you can comment on the continuous or discontinuous, right?
Okay, sir. Thank you, sir.
Okay.
Hello, sir.
Yes, please.
Sir, my doubt is in RLE load, half wave rectifier.
RLE load. Just a minute.
Yes, sir.
Yes. In this,
Sir, in waveform.
okay. Yes.
Sir, here why we have considered that point θ1 and why not pi minus theta only?
θ1 why we considered? Okay. Listen. At alpha, we are applying the gate pulse to the thyristor.
Yes, sir.
Our thyristor is turning on.
Yes, sir.
What is the voltage across inductor? Only inductor. VL voltage I want. What is the voltage across inductor? Vs minus VR minus E.
Yes, sir.
Okay. So now you
Yes,
can
sir.
check after alpha, VL is equal to Vs minus VR minus E. Na? At alpha, definitely your Vs is high. After
Yes,
that, again
sir.
Vs is increasing. So Vs minus VR minus E, difference is increasing. Your VL will be positive only. Right?
Yes, yes,
Now
sir.
near to this pi minus theta, that is at θ1, you can check that θ1 is like your Vs is equal to VR plus E. Means your VL is like a 0.
Okay, sir. Sir,
You can
but-
check. Now can you please tell me corresponding to this point, Vs and E both are same, na?
yes, sir.
At pi minus theta, Vs and E both are same.
Yes, sir.
Now corresponding to this point, check now θ1. At θ1, can I say that this Vs is greater than E?
Yes, sir. It's greater than E.
Now Vs is greater than E means I am considering this θ1 is like a Vs is equal to VR plus E. Are you getting the point?
Sir,
Hello.
I didn't get the
Huh.
last line. It was stuck. Can you
Yes.
repeat?
Please listen.
That
please
Vs is
listen,
greater
please
than-
listen.
Yes, sir.
Yes. At pi minus θ1. Now my first question is okay. At pi minus θ1, Vs and E both are same or different?
Same, sir.
At this instant, both are same means Vs value is equal to E value. You can
Yes,
check
sir.
now compared to this point. Now here we are having a θ1. At θ1, Vs is greater than that of this value or less than that of this value?
Greater than E.
Vs is greater than θ1. So now that θ1 means we are indicating it as Vs is equal to E plus VR. Are you
Yes,
getting the
sir.
point? Means in the E we have added a VR. So definitely your Vs should be greater than that of this magnitude or this point.
Yes, sir.
That's why this point indicates your corresponding to this point Vs and Vs is equal to E plus VR. Now Vs is equal to E plus VR means your VL will be 0 na?
Yes, sir.
So VL 0 means before this instant it is like inductor was storing the energy. After this instant inductor will release the energy.
Then, sir, I note is maximum at θ1 point.
I naught is maximum at θ1 point.
Okay, sir.
It is not pi minus theta. I naught will be maximum at pi minus theta only in case of no. We cannot comment like that. Only in case of like, because in RE load we are having a different case, na. In
Yes,
RE
sir.
load we don't have this type of slope, right?
Sir, if VR is equals to 0.
If VR
Then-
is 0, then your θ1 is equal to pi minus theta.
Okay, sir.
Are you getting the point? Means
Yes, sir.
that difference of Vs, na, difference of Vs, that is Vs at θ1 and Vs at pi minus theta. The difference between those values of Vs is nothing but your VR,
Yes, sir.
right?
Okay, sir.
Okay.
Got it. Thank you, sir.
But nearly that θ1 is equal to your pi minus theta only, na? Approximately
Yes, sir.
both are nearly same, right?
Okay, sir.
Because R value is generally very less. Okay.
Yes, sir.
Right. Okay. Next.
Hello,
Yes.
good evening, sir.
Good evening.
Sir,
Yes.
sir, in the first topic of the power electronics, I have doubt in that. Sir, what is the mean of the junction capacitance of thyristor?
What is the meaning of junction capacitance of a thyristor? Okay. Actually,
Yes.
the thing is when your junction J2 is in a reverse bias mode, na?
Yes, sir.
So it is like across that junction, at one side we are having a layer of positive charges, at second side we are having a layer of negative charges.
Yes, sir.
So it is like our junction has stored charges, na, positive, negative. Means
Yes,
it is
sir.
like your junction is behaving as a capacitor. In a parallel plate capacitor, what we are having in a capacitor, at one plate we are having a positive charges, at second plate we are having negative charges.
Yes, sir.
So same scenario is there, right? So that's why we have considered that Cj is nothing but the junction capacitance, and your junction J2 is behaving as a capacitor.
Yes, sir. Sir,
Ah,
sir, I have one question in that I stuck in that. There is
okay,
given the junction capacitance of the 15 picofarad.
okay.
The limiting
Ye-
value of the charging current to turn on the thyristor is 5 milliamps.
Okay.
The critical value of dy by dt is 200 volt per microsecond.
Di by
And
dt,
dv by dt.
dv by dt. Okay.
Yes, sir. The value of the capacitance Cs, so that thyristor will not to be burned on due to the dv by dt. With this,
Will you please repeat that? Please repeat that. Whether they have given dv by dt, they have given.
yes, sir. dv by dt is given.
Capacitance
The
value
junction.
we are required to find.
Yes, sir. Cs we need to
Okay.
find. He is given the
Next.
only junction capacitance is 15 picofarad. He is not given the value of the Vs. How can we find the Vs?
Okay, okay. Vs value they have not given.
Not given. They are given the
Cj
hint
they
as
have
the
given. They have given Cj.
yes, sir. 15 picofarad.
Okay, okay. Will you please send me that photo? Right?
Hi, I sent, sir.
Whether they have given circuit diagram?
Yes, sir.
So please send me the photo so that we will discuss. Okay.
Hello,
Please
sir.
WhatsApp me.
Hello?
I will answer your doubt. Okay. Yes. Next.
Hello, sir.
Yes.
Sir, sir, my doubt is about the theta one only. Sir, why the inductor gets short circuited?
When during
Here,
SCR that snubber circuit design.
No, sir. In this slide, sir. RLE load.
In this RLE load, what we have done?
Sir, inductor mean, how the inductor gets short circuited. That's the point.
Where we have shown the inductor has short
Means
circuit?
theta one at theta one.
At theta 1, it is not like inductor is short circuited. Inductor voltage is 0.
Sir. Inductor voltage 0 means it
Okay,
will
okay.
short circuit. No?
Now you
sir.
listen. Have you studied the network?
Yes, sir.
In the network transient theory we are having.
Yes, sir.
Suppose initially at t is equal to 0, switch is closed. Before that, it is like inductor current was 0. So at t is equal to 0, your inductor acts as an open switch, open circuit.
Yes, sir.
At t is equal to infinity, what happens? Inductor acts as short circuit.
Yes, sir.
Same is happening here. You can check at alpha, inductor is like an open circuit.
Yes, sir.
At alpha,
Sir,
what
for
triggering,
Yes, sir. So for the positive cycle, it is storing the energy, sir, for the whole positive cycle.
for one positive cycle, it is no, it is not like that. Inductor is
Sir.
storing the energy only from alpha to theta 1. And the value of
Alpha to
theta 1,
1.
value of theta 1, it depends on value of E and VR, voltage across resistor.
Okay, sir.
Because if
Volt-
only inductor is there, then no problem. If only inductor is present in the circuit, then it is like for positive cycle, inductor will store the energy. But now in the
Okay,
circuit, we are having inductor, resistor, and E,
Yes,
So
sir.
your VL, when thyristor is in a conduction mode, your voltage across inductor is like a Vs minus voltage across resistor minus EMF,
Yes, sir. Yes, sir.
So that's why inductor will store energy only till this instant theta 1. Right?
Okay. Okay, sir. It means
And the theta
only
one
if
is the-
R load is there. Okay.
Only.
So only R is there, then it will store for the whole time, sir. Positive time.
Only resistor is there then? Means only RL you are saying?
Means we have studied in the previous case that only R load, it is storing for the one positive cycle.
Only R load or RL load you are saying?
Only R load.
If only R load is there, then whether the resistor stores energy?
Sorry, sir. RL load. RL
For
load is there.
RL load also, no, for RL load also, inductor will store energy till theta only.
Okay.
We discussed now that theta is not equal to your pi. It is near to pi. Okay.
Okay.
But
Okay.
it is less than the pi. Because
Okay.
the thing is, means corresponding to theta na, in RL load, if you check that corresponding to theta, your Vs is like equal to VR. Vs is equal to VR. We discussed, right? By showing the waveform of VR
Okay,
also.
sir. Okay.
Right? Please go through that
Okay.
once, you will understand. Right?
Okay. And sir, for
Yeah.
the last case we have discussed, the negative time for that is very less, sir. Means
Negative.
in the last case
Yes,
we have
yes.
discussed.
Yes.
For the
Pi
inductor,
to beta you are saying. In the last case
sir.
that pi to beta or 0 to that very small. Okay. Yes.
So the
That
in
will
that
be less.
so in that time the whole inductor will release energy, sir, in the short period.
No, the thing is in steady state, whatever the energy inductor is storing, na, the inductor is releasing the same energy.
Sir. Means in the short period, na, sir?
Yes, short period. Because the inductor value is less, na, so that's why it is storing the less energy.
Okay.
So that's why it requires a lesser time only to release the energy.
Sir.
Right?
Okay. Means because of E, sir, it is storing less energy, na, sir?
No. Because the value of L is less.
Okay.
That's why inductor is storing the less energy.
Okay, sir.
Right?
Sir. Okay.
Okay. Yes.
Sir, 27F.
27.
27.
Okay. Just a minute. Yes.
Sir, here on the primary side, we have marked IS. Sir, what is that IS?
That IS is your primary source current.
Okay. And sir, that IS which we have calculated, that is?
That is nothing but your secondary winding current. That is also IS because that is also flowing in the transformer winding, na?
Yes, sir.
Right?
Sir, but both are different, this IS and that we have calculated?
Both will be different in magnitude, but volt amperes will be same at both the sides. Whatever we calculated now here, that's right number. Yes, here it is, na?
Yes, sir.
Yeah. This is like if this is Vs by R, okay, then it is like secondary winding current.
Okay.
And if you multiply this with 2,
yes, sir. Primary
it will
winding.
be like a primary winding, right?
Yes, sir. And
So
sir,
volt ampere will be same. Yes.
and sir, in the first numerical, we did 2 numericals today. So second one, in that we took 230 volts as RMS.
Yes.
And sir, in that first question, they had given Vs equal to √2 V sin omega t. So
Yes.
sir, the first question they have given, sir, that Vs is equal to √2 V sin omega t. Sir, which current is that? Which voltage is that?
This is actually instantaneous value of the supply voltage. Means by using this expression, you can draw the Vs waveform, na? Omega t 0, right?
Yes.
You will be getting sin 0 will be 0 Vs. You can go on increasing omega t, your Vs go on increasing. At omega t pi by 2, it will be having a peak value of √2 V.
Yes, sir.
So the peak value of the supply is √2 V.
Yes, sir. Okay.
So RMS value will be √2 V by √2, na?
So sir,
Yes or
this
no?
yes, sir.
Huh.
So sir, this whole equation is instantaneous value.
Yeah. This whole equation is instantaneous only.
Okay, sir.
Generally,
Thank
RMS we specify in numbers, na?
Yes, sir.
If they show Vs is equal to V, na? If they show here Vs is equal to V, then it is like the RMS value is V.
Yes, sir. Okay.
If they give it in terms of sinusoidal, then it will be instantaneous.
Okay, sir. Thank you, sir.
Okay.
Yes, sir.
Yes,
sir.
please.
Sir, theta to.
Will you please speak a bit louder?
Yes, sir. Duration, sir, and theta to
theta to
ఆల్ఫా టు థీటా అండ్ థీటా టు పై ప్లస్ ఆల్ఫా రెండు డ్యూరేషన్ ఉన్నాయి కదా సార్, ఆ రెండు సేమ్ ఆల్ఫా టు థీటా అండ్ థీటా టు పై ప్లస్ ఆల్ఫా బోత్
alpha
డ్యూరేషన్
to theta and theta to pi plus alpha. Yes,
బోత్ డ్యూరేషన్ సేమ్ ఆర్ నాట్ సార్?
both are we cannot comment directly, but both are nearly same.
అప్పుడు అలాంటప్పుడు అంటే టైం ఫర్ రిలీజింగ్, టైం ఫర్ స్టోరింగ్ అండ్ టైం ఫర్ రిలీజింగ్ బోత్ ఆర్ డిఫరెంట్ కదా సార్?
Times can be different, but energy stored is equal to energy released. That we can say, because your times at all depends on, yes, it depends on your E value also na, and VR value also. Hello.
అంటే ఒక అంతకుముందు అంటే ఆఫ్ కంట్రోల్ లో అంటే
Please, will you speak in English? I don't know, Miss Telugu. I don't know actually. I don't understand.
సార్ అంటే in off control L load లో off control for L load for L load you said
Half wave.
in off wave control L load Off
Pure
wave
inductor.
control
Pure
rectifier
inductor.
pure inductor load. You said that time for storing energy is equal to time for releasing energy for inductor.
That is only in case of pure inductive.
Okay sir.
Are you getting the point? So you can
Yes,
check
sir.
pure inductive load for half wave uncontrolled as well as half wave controlled. What we discussed, because in that case, in that circuit, the only inductor is there, na.
Okay sir.
But now in this circuit, we are having a resistor, inductor, as well as EMF. So we are having the other elements also, and those elements are consuming the energy, na. But whereas if you check in the case of that pure inductive circuit, we only inductor is there. So inductor only that storing the energy, and that was releasing the energy. So another element was not there, not to consume the energy. So that's why there at that time, whatever we commented, that was only specifically for that load only, purely inductive, right?
Means even though time intervals are different, energy the amount of energy
Yes. Even though
storing
the
is
time
equal to
intervals are different, but resultant energy will be zero. Stored is equal to released.
okay sir. And
Even the
that's why
same point you will because the same logic or same knowledge we require in a DC to DC converter also. You can check the chopper circuitry. In that we are having on time and off time, both are not same, na, different. But then also in steady state, what is happening? Inductor is storing the same energy and releasing the same energy also.
in case of highly inductive load, because of that reason we are getting constant current sir.
Yeah,
Because of-
because of no, actually the thing is due to the high value of inductor is storing more energy, right? And actually the thing is high value of inductor means inductor opposes more to change in current. So now if inductor is opposing the more to change in current means what? Inductor is not allowing to change the current. Now not allowing to change the current means what? Current is constant.
Okay sir. Thank you sir.
Are you getting the point?
Yes sir. Thank you sir.
So current will be constant or not, it will be decided by your inductor value.
Okay sir. Thank you sir.
Right? Okay. Yes, please, next.
Hello, sir.
Yes, please.
Sir, in half wave control rectifier, could you explain its operation from alpha? What is happening once again?
Half wave
Control rectifier using RLE load.
RLE, na, this one.
Sir.
Okay. What is happening in the circuit? Okay. So from 0 to theta, if you
sir.
observe the waveform, Vs is less than E. If Vs is less than E, thyristor will be in a reverse bias mode.
Yes, sir.
So thyristor will be in a open circuit mode or off state.
Sir.
So your V0 is equal to E only. Theta to alpha, what is happening? Theta to alpha, thyristor is in a forward bias mode, but we have not applied the gate signal.
Yes, sir.
So that's why thyristor is again open state or off state.
Sir.
So that's why V current is not flowing. So V0 is equal to E only.
Yes, sir.
From alpha till theta 1, what is happening? From alpha till theta 1. Okay. Now we have applied the gate pulse. So thyristor T1 is in a conduction mode.
Yes, sir.
So current is flowing from Vs, thyristor, load, and again back to the Vs. V0 is equal to Vs, na?
Sir.
What about the I0? I0 will go on increasing slowly.
Okay, sir.
So this is till theta 1.
Sir.
Only till theta 1, why it is happening? Because at theta 1, your Vs becomes equal to Vr plus E. So after theta 1, it is like Vs is less than Vr plus E. So if Vs is less than Vr plus E, it is like your voltage across inductor will be negative, na?
Sir.
So voltage across inductor negative means after theta 1, your inductor starts releasing the energy.
Okay.
So that's why from theta 1 till pi, inductor will release the energy through thyristor T. But during that interval, what is happening? Inductor energy and supply energy both are adding. Because supply is also circulating current in this direction. Inductor is also circulating, trying to maintain the current in the same direction. So both will be adding, assisting, we can say, right? This will continue till pi. So during that interval, you can check V0 is again Vs, because when thyristor is in on state, your V0 will be Vs only, right? And after theta 1, here current is decreasing because inductor is releasing the energy. And after pi till beta, what is happening? Your inductor is go on continuing releasing the energy in opposition to that of the supply voltage and in opposition to that of the E also. Okay. So from pi to beta, it is like inductor is releasing the energy in opposition to that of the supply voltage as well as in opposition to that of the E also.
Is it because of reverse polarity, sir?
Yes, yes.
It is like in opposition because of the reverse polarity of Vs and E, sir?
No, why it is in opposition releasing the energy? Because in order to maintain the current same, na? At pi, what is the current? At pi, current is non-zero positive. So current is non-zero positive means current is in the downward direction, na? So inductor releasing energy means voltage across inductor is negative only. So voltage across inductor is negative means it is like a polarity will be plus here and minus here.
Okay.
So you can check inductor voltage is opposite to that of E as well as your supply voltage, because after pi supply voltage is negative, na?
Sir.
So these two are actually assisting. Now Vs and E will be adding. And our inductor is, yes, inductor is continually releasing the energy. Yes, in opposition to that of these two also. But the thing is near to the pi, Vs value is very less, na? As Vs value is very less, due to that your Vs plus E will be not that much high value. So that's why successfully our inductor can release the energy. Right? This will continue till beta. After beta, definitely your supply voltage energy and E energy will be more than that of your inductor energy. So that's why our inductor energy becomes less. So that's why resultant circuit current becomes 0. So at beta, it will become 0. Right?
Okay, sir.
Right. And
Sir,
till
and
2 pi plus alpha, it will be. Yes.
sir. Sir, and in this interval that is from the alpha to theta 1, we are telling that inductor voltage is positive now, sir. How can we tell that?
Alpha to theta 1 inductor voltage is positive.
Sir.
You can check now. Apply simply KVL to this loop. It is like a plus Vs.
Okay.
Minus voltage across resistor, that is VR. Minus voltage across inductor minus E is equal to 0, na?
Sir.
So what is voltage across inductor? It is a Vs minus VR minus E.
Sir.
So you can check at alpha, Vs is this much value. E is this much value.
Sir.
At alpha, what is the VR? VR is 0 because I0 is 0.
Okay.
Right? So that's why your Vs is greater than VR plus E, na? So that's why VL will be positive.
Sir.
After that, again, Vs is increasing only. So that is greater than that of this E plus this I0 into R. I am saying I0 into R. Okay. So that's why again Vs is greater. So that's why VL will be positive. This will continue till theta 1. At theta 1, actually, what is happening? Your Vs and VR plus E both are becoming same. Means Vs is equal to VR plus E. At pi minus theta, Vs and E both are same. Means at pi minus theta, Vs value is equal to E value.
Okay.
So above this means at theta 1, if you check, Vs is greater than this value, na?
Sir.
So what this indicates, this difference between Vs is nothing but your Vr indicates. It indicates Vr.
Sir.
So that's why it is a Vs is equal to Vr plus E, right?
But so till theta 1, Vr's value will not be very high, sir. It
Will you please repeat? Will
will be
you
low
please,
values only.
please
Till theta 1, that is from alpha till theta 1, the values of VR will not be very high. It will be small values, sir.
Yes, yes. VR value is actually, we are having a very small value because, yes, we are having current is, it is a finite. Okay, current we can say it is having a high value or a finite. But your register value in this type of loads is generally very less because it is a motor load, na? And you can check in the motor what is the resistance. It is a very less value.
Okay.
Right? So that's why generally in most of the books they have neglected simply, and they say that if we neglect R, then what happens? Theta 1 is equal to pi minus theta only.
Okay.
Right? So if we increase the, if you increase the resistance value, definitely your theta 1 will shift towards alpha, na?
Sir.
If register value increases, this theta 1 will be, instead of this point, theta 1 will be moving into the left side, na?
Sir.
Right? So like this, where everything. Okay.
Sir.
Yes.
Sir, and one more doubt in full wave control rectifier with RL load. Sir, when we are applying gate pulse to the T2 thyristor.
Okay.
Sir, at that time you told that like the inductor is again storing energy, but this inductor
Storing
is
energy.
a large value, na, sir. So before that interval, it was releasing energy. So it could not complete releasing energy by the time we gave pulse to T2, na, sir. So why won't it release the remaining energy rather than again storing?
Okay, okay. Now think here. In steady state, generally, if whatever the energy stored by the inductor is less, then definitely inductor will release less energy. Okay. So in steady state, what is happening here? Inductor is getting very small time to release the energy, that is from theta till pi plus alpha.
Sir.
So there, and that where inductor is storing the energy from alpha to theta. Okay. So you can check. Yes, in steady state, what is happening? Whatever the energy stored by the inductor from alpha to theta, it becomes equal to, yes, energy released by the inductor during theta to pi plus alpha. Yes.
Sir, theta or sir pi, sir? Alpha.
Storing energy.
Sir.
Storing energy is till theta. Till theta.
Okay.
We are having RL load, na?
Sir.
So till theta it stores energy.
Okay.
And after that it releases the energy.
Sir.
If only purely inductive circuit is there, purely inductive load, then definitely inductor will store energy from alpha to pi. But if resistor is present, that yes, theta will shift in the left side, na, left direction. So theta will be less than pi, right?
Sir. Sir, but like it will not, it is a large value of inductor, na, sir. So will it fully release by the time next pulse is given?
It doesn't matter here. Our main here, it is not like that. Whatever energy stored by the inductor, okay, from zero, suppose inductor has stored some millijoule energy, okay, then inductor should release that full amount of energy till reaching zero. No. My question is, suppose for very first cycle, our inductor is storing the energy from zero, let us consider from 0 till 10 millijoule.
Okay, sir.
And after that, inductor is releasing the energy from 10 millijoule to 5 millijoule. After that, next cycle, inductor is again storing the energy from 5 millijoule to the 10 millijoule. And again releasing from 10 millijoule to the 5 millijoule. Again, it is increasing from storing energy from 5 millijoule to 10 millijoule. Again, it is decreasing from 10 millijoule to 5 millijoule. Means what happening in steady state? Actually, very first cycle, it has started from 0 to 10 millijoule. But in steady state or in continuous, what we are observing, inductor energy, yes, is changing from 5 millijoule to 10 millijoule, again 10 millijoule to 5 millijoule, 10 again 5 to 10, 10 to 5, 5 to 10, 10 to 5. So can you say that here, as during when T1 conducts or during alpha to theta, if inductor energy is changing from 5 millijoule to 10 millijoule, so resultant energy stored is equal to 5 millijoule only.
Yes, sir.
And from theta to pi plus alpha, if inductor is releasing the energy from 10 millijoule to 5 millijoule, so what is the energy released by the inductor? 10 minus 5, again 5 millijoule. So it doesn't mean that from 0 my inductor storing the 10 millijoule means inductor is supposed to release 10 millijoule. No, it is not like that. Hi, in your discontinuous conduction, definitely that will happen. But in continuous conduction, it will not happen. Right? But inductor energy over an entire cycle, over a one cycle, definitely that will be 0.
Sir.
Yes.
Sir, my doubt is like if it is before triggering this T2, it was releasing energy, na sir?
Yes.
The inductor was. So when we trigger T2 also, rather than storing, why can't it release? Why is it like storing?
No, because you can check here when before T2, let us first discuss before T2. It is like a theta to pi plus alpha inductor was releasing energy like this, na? So what was the current flowing through the inductor? It was from right to left.
Yes, sir.
Now when I trigger the T2, what is happening when I trigger the T2? Again, your supply is like plus here, minus here. Here it is minus, here it is plus, na?
Yes, sir.
So supply is also circulating current in this direction. And inductor is also wanted to release the energy in this direction. Are you getting the point? Okay. So whether both the currents are in the same direction or opposite direction? Same direction. So what the inductor will do, from the same instant, inductor will again start storing the energy.
Okay.
If they would have opposite to each other, then there will be a concept like inductor go on releasing the energy, right?
So
you can take the same direction we're having the currents.
So it's equivalent to storing energy itself.
Yes, it will be equivalent to storing energy only.
Yes.
Right? Okay.
Sir, and one last doubt. In this itself, by finding out I naught average, we have taken it to be V0 average by R, sir. Is it because we are having a highly inductive load? Because in other cases, we cannot take it like that, no, sir.
No, it is not like that. In a case of inductor, average voltage is always 0. Okay. Because we discussed now from alpha to theta, inductor voltage is positive, na?
Yes, sir.
VL is positive, na?
Yes.
Alpha to theta. So due to that only inductor was storing the energy alpha to theta, VL is positive. And from theta to pi plus alpha, VL is negative.
Yes, sir.
So you can check whatever the average voltage, okay, of the inductor from alpha to pi plus alpha, it will be 0 only.
Yes, sir.
So
Sir,
that's
my
why-
doubt is not that, sir. Sir, I0 average, you've given that to find out I0 average, we can take it as V0 average by R
Yes.
in this case.
No. Yeah, the same thing I'm saying. If you recall the REL load, whatever we discussed in the previous case or the yesterday also, there also we wrote I0 average is equal to V0 average by R only.
Okay,
Because in the case of REL load, average voltage across inductor is 0. Because V0 means what? Voltage across resistor plus voltage across inductor.
Yes, sir.
And what is the average voltage across inductor? It is 0.
Yes, sir.
So V0 average is nothing but average voltage across resistor only.
Yes.
What is the average voltage across resistor? I0 average into R.
Yes, sir.
So what is the I0 average? V0 average by R.
Yes, sir.
Yes or
Sir,
no? Yes.
yes, sir. So for all values of inductor, we can take it to be like, even if it is
Yes,
higher,
yes,
low, we can
For-
take.
Yes. For all values of inductor, for REL load, for as well as for RLE load, always keep it in mind. Average voltage across inductor is always 0. Or you can check purely inductive load also. In that case also we wrote average voltage across inductor is 0. But in the case of pure inductive load, voltage across inductor is nothing but your voltage across load, na? So
Yes.
there we commented that V0 average is 0. Is nothing but V0 average means what? In the pure inductive load, if V0 is the load voltage, is nothing but voltage across inductor, na?
Yes, sir.
So that's why we wrote there V0 average is 0. right? So please keep it in my note it in your notebook. Okay, on the very first page. As an electrical engineer, we should know it. Average voltage across the inductor is always 0, right?
Okay, sir.
Right, in steady state. Okay. Okay. Yes.
Thank you, sir.
Yeah. Yes. Next.
Good evening, sir.
Good evening.
Sir, in RLE load, we have calculated that I0 average, sir. That point, sir.
RLE load I0 average.
Yes, sir.
This one, na?
No,
Hello?
sir. RLE, sir. RLE, sir.
Yes,
Full
this
wave.
is RLE only. Just a minute. RLE.
First problem, first, sir. First problem, sir. In control rectifier. Today, first problem.
Correct. I0 average. Yes. Yes, here it is.
Sir, here we have kept that by using KVL equation. Why, sir?
This
Instead
one.
of we can I0 average equal to V0 average by R.
Instead of that, what you are saying?
Sir, usually calculate that I0 average equal to V0 average by R, but we calculate that using KVL equations. Is there any reason, sir?
No, because the load is RLE load, na. Here we cannot write directly I0 average is equal to V0 average by R. Because EMF is there, na.
Oh, okay, sir. Because of presence of EMF, we are calculating, applying KVL I0 average.
Yes. Actually, we are writing I0 average with the help of V0 expression.
Yes, sir.
Means we are applying the KVL to the V0, na, that branch, load branch.
Okay, sir.
And from that, we are writing the I0 average expression. If the load is only resistive, it is like a V0 is equal to VR.
Okay, sir.
Yes or no? So that's why V0 average is equal to I0 average into R. So from that, I0 average is equal to V0 average by R, right? If the load is REL, then we need to write V0 is equal to VR plus VL.
Okay, sir. Okay.
So average value of inductor is 0. So V0 average is equal to VR average. So in that case also we wrote I0 average is equal to V0 average by R, right? And for RLE load, we need to consider E also, right?
Okay, sir. Okay. If any circuit we consisting E, we have to write like this only, sir.
Yes, correct.
Okay, sir. Thank you, sir.
For RE also we are having the same expression, right?
Yes, sir. Yesterday
If you
class.
recall the RE load.
Yes, sir. Yesterday class.
Same expression. Yes. Okay.
Thank you, sir.
Okay. Yes. Next.
Hello, sir.
Hi, MTH, please.
Sir, I sent that question, sir. Could you once see that?
Okay. These two questions you are saying?
Yes, sir. In 17th one, the junction
First one is the
capacitance.
junction capacitance of thyristor used in the circuit is 15 picofarad. Okay. The limiting value of the charging current to turn on thyristor is 5 milliampere. Okay. Limiting value of charging current. Okay. To turn on thyristor is 5 milliampere. Means they have given the limiting value of the that junction capacitor. That is a IC they have given. Okay. And the critical value dV by dt is 200 volt per microsecond. The value of capacitance CS so that the thyristor will not be turned on due to dV by dt. Okay. So here you can use dV by dt is 200 volt per microsecond. Critical value, the thyristor is 5 milliampere. Okay. So thyristor current is a 5 milliampere they have given directly, right?
Yes, sir. IL.
dV by dt they have given, right?
Yes, sir.
So I is equal to C into dV by dt you can do. Okay. And CS is equal to, yes, that thing we need to check, and if it is open. Okay.
He's given junction capacitance, sir.
Yeah, junction capacitance means simply thing is we need to replace that thyristor with a capacitor.
I
Do one
replace.
thing, remove that thyristor and put the capacitor.
Yes, sir, I did.
So it
Sir.
is like you will be having the supply voltage, resistor and two capacitors, na?
Yes, sir.
Okay. So now in that case, CJ they have given 15 picofarad. Our only task is to find CS.
Yes, sir. But VS is undefined, no,
Yes.
sir. VS is not given. If you find the
PS is
CS,
not required even. They have given the 5 milliampere here. Okay. And you can equate simply that 5 milliampere, but that dV by dt will be applicable to both, na? So C, I is equal to C into dV by dt. Okay. Do one thing. First find I is equal to, means current flowing through that junction capacitor. Huh? Please
Okay.
write, find the current flowing through the junction capacitor is equal to Cj 15 into 10 to the power minus 12 into dV by dt.
yes,
Yes
sir.
or no? Right?
Yes, sir. I see
So
equal to
that-
CJ into.
Yes, yes. How much you are getting? C into 200, na? Divided by 10 to the power minus 6. It is a 3 milliampere, na? Yes or no?
Yes, sir.
3 milliampere you are getting. And they have given the limit as 5 milliampere. Okay.
Yes, sir.
So do one thing, that 3 milliampere subtract from that 5 milliampere.
2
So it will be
milliampere.
2 milliampere, na?
Yes, sir.
So 2 milliampere divided by your dV by dt. Please do that thing.
Zero 0.01.
Yes, it's
Mm.
that.
It's coming in micro, sir.
No, 1 into 10 to the power minus 11 something, na? Take once. Or 5 milli, IC is equal to C into dV by dt. Okay. So 5
Yes, sir.
into 10 to the power minus 3 divided by that 200 divided by 10
0.1.
to the power minus 6. Okay. And 2.5, that is a 25 pico minus here it is a 15 pico, na? Okay. Okay. Capacitors connected in parallel, they will be generally getting added, na?
Yes, sir.
Yes or no?
Yes, sir.
So 15 they have given and 25. Okay. So that will be nearly your,
I'm getting 10, sir.
yeah, 10 picofarad is should be the answer.
But he's given the answer is 12, sir.
12 they have given.
Yes, sir.
12 nanofarad.
Nanofarad.
Okay, okay. I will send you the solution. Okay, on WhatsApp only.
Okay. Sir, one more, sir. In 16th one, I said no, sir. In
Oh,
that,
yes,
sir,
on that day also I think you would, yes, send me. For
No,
the
sir.
element values given in the circuit, the initial current through the inductor is.
turn
Yeah,
off time
initial-
is, sir, turn off time is a pi by omega, no, sir. There is asking for the find the turn off time, means TC, conduction time, sorry, commutation time.
Okay, huh.
TC is equal to pi by omega.
The capacitor voltage after thyristor. No, the value of conduction time of thyristor, na? That value, that is pi into root LC, that was only when your inductor and capacitor are not storing initially charge or the energy. Whatever we discuss, na? Pi root
Yes, sir.
LC.
Yes, sir.
That is like pi by omega 0, na?
Yes, sir.
That is only when your inductor and capacitor are not initially storing the energy. Then only that will be true. Now here they have given the inductor initially voltage is also given, and sorry, inductor current is given,
Inductor only.
and capacitor voltage is also given. So now we need to simplify it with the help of non-zero initial condition of the Laplace transform. So do one thing, simply first find the value of the current in the circuit. Suppose that T is equal to 0, your thyristor is turned on, na?
Yes, sir.
Right? And then find the current in the circuit. From that, you will be getting current is like a sinusoidal something. Okay. And check the
Okay.
instant from where the current is non-zero and till which instant the current, at what instant the current reaches 0. The difference between these two will be your conduction time of the thyristor.
Okay, sir. I
Right?
will check.
Just simply go through once that Laplace non-zero initial condition.
Okay. In the initial time, we can use a 250
Because
amps.
whatever we discussed now, that V pi into root LC, that was true only when your capacitor voltage is 0 initially.
Okay,
And
sir.
inductor initial current is 0. Then that is true. But we cannot use that expression here because they have given it is a 200 volt initial voltage and current also it is a non-zero, na?
Yes, sir.
Right? So we need to think about that, right? So in this way, means you need to use that Laplace transform with the non-zero initial condition.
Okay, sir.
Right?
I will solve. Thank you so much, sir.
Yes, yes.
Sir?
Yes. Yes, please.
Sir, slide number 37.
37.
Yes, sir.
Yes.
In that IS graph, during the interval pi plus alpha to 2 pi, why you have drawn that wave downwards?
Okay. Please listen. From pi plus alpha to 2 pi, which thyristor will be in a conduction mode?
T2, sir.
T2. When T2 conducts, how is the current that will be flowing through the transformer secondary? Upward or downward?
Downwards, sir.
Downward. From alpha to pi, which thyristor conducts?
T1, sir.
T1. When T1 conducts, current in the transformer secondary is upward or downward?
Upward.
So for upward, if we consider the positive value, then for downward, how we need to draw? Negative or positive only?
Okay, sir. Negative, sir.
Right? Okay.
Sir, another doubt.
Yes.
In the same topic, input power factor.
Input power factor. Okay.
Actually, one person asked the same doubt that why you have not multiplied with 2.
No, that 2 will be getting cancelled.
Can you once explain that, sir?
Yes, just a minute. Here it is.
After 37th slide, maybe 38 or 39, sir.
Okay. Yes, here it is. Right?
Yes, sir.
So, yes, please, your doubt is?
Why you have not multiplied with 2?
Simply the thing is, I have taken the secondary winding current here.
Okay, sir.
You can check the volt ampere of the transformer either at the secondary side or at the primary side. Whether both will be same or different.
Maybe same.
Both will be same only, na? The thing is, where having a transformer is a device like, suppose if the voltage is stepping up, na, current will step down.
Yes, sir.
Means if at the primary for having the voltage is Vs, then at the secondary will be having the voltage is 2 Vs.
Yes, sir.
Then and if at the secondary we're having the current is Is, then at the primary we'll be having the current is like 2 Is.
Okay, sir.
Because voltage is step up, current should be step down, na? So
Yes.
if you take the volt ampere, that will be same.
Oh, okay, sir.
Right? So that's why I have taken here Is RMS direct. Okay. Okay, right.
Sir, still how many topics are there to be discussed in this chapter, sir?
In this chapter, still tomorrow we'll discuss the full bridge converter, right?
Okay.
After that, how to find the input power factor for RL and RLE load. That we have not yet discussed. Okay, that we need to take the help of the Fourier series, right? And after that, the semi converter, that is a single phase half bridge rectifiers, and after that the 3-phase. So we require 3 to that is 3 into 4, 12 hours, 12 plus 3, 12 to 15 hours we require more for this chapter.
Okay.
Right?
Okay.
So our schedule will be till I think we'll be continuing till 9th of the September. Okay.
Yes, sir.
Yeah. And the remaining 2 chapters we are having, that is the inverter and DC to DC converter.
Yes.
Generally, the DC to DC converter is a comparatively less, or the lesser contents will be there. We're having hardly 3 circuits, buck boost and buck boost, and the numericals, whatever we have given, they have given in the booklet, right? So it will take around 6 to 8 hours for DC to DC converter. But for inverter, around 12 hours we require, because inverter is very important chapter. And it is very interesting actually. Strictly speaking, it is very interesting. And the last chapter, that is your AC voltage controller. Okay. That will be hardly 2 to 3 hours task is there. Okay.
Hello, good evening, sir.
Yes, please.
Yes, sir, in the same IRMS and VRMS, both are referred to secondary, na, sir?
Both are?
Means input power factor we are finding, you said in the denominator, ISRMS is the secondary referred, na, sir? Then VSRMS should also be referred to secondary, otherwise the balance equation will not be satisfied, na, sir?
Okay. No, this VSRMS is like your RMS value of the supply voltage.
Yeah, that's what I'm not getting, that VSRMS is supply voltage, then ISRMS should also be of supply, no, sir? Otherwise, it will not balance the equation, sir.
Okay, means you are saying in that way, if it is
Yeah.
not. Okay.
That's what I'm not.
Just a minute. Okay. I0 RMS and IS RMS were getting cancelled. Okay. So both are definitely same. If this is secondary, then this should be equal to, as per you, whatever you are saying, it should be 2 VS RMS you are saying.
Yeah, 2 VSRMS it should be there.
No, but it is not like that. If you check for the secondary winding, let us consider the first half part.
Okay,
For
sir.
the first half part, the voltage is VS.
Right, VS.
And what about the first half part current waveform?
Current waveform means upward direction.
No, but what is the RMS value of that? Whether it will be same as that of IT1 RMS?
Yes, it will be, sir.
Yes or no? I0 RMS divided by root 2, na?
Yeah.
So if you check, it is VS. So the first half part volt ampere rating is VS RMS into I0 RMS by root 2. Okay.
Right.
Similarly, what about the second half part?
Second half part will be also be something like that, sir.
Right. So if you add these two, okay,
yes, sir.
then we'll be getting it as a VS RMS of that part plus VS RMS of the second part. Okay. Right. So I think it will be
VSRMS into ISRMS.
Yes or no? Right.
Yes, total will be VSRMS into ISRMS.
Yes.
Yeah.
So that's why we're taking here VSRMS into ISRMS, because you cannot here simply multiply 2 into VSRMS into ISRMS, right? Because whether we are having the same current which is flowing in the secondary winding for all the intervals, no. For the first alpha to pi plus alpha, we are having the only first part current is non-zero.
Right.
Second part current is non-zero only from pi plus alpha to 2 pi plus alpha.
Yeah.
So that's why we need to think in other way here, right? But whereas in the machines whatever we discussed in transformer, there was like a steady state operation, and when transformer is on load, definitely your secondary current will be for all the time non-zero, na? But it is not like that. We're having the different parts here, right? Okay.
Yes, sir. Thank you. Understood.
Right. Right. Okay. Great. Thank you. Thanks to all of you.
Thank you, sir. Good night.
Yeah, good night.